Hello everyone, welcome to Pushpa classes. So today we will start our first chapter of digital electronics, and that is number system and codes. तो ये टॉपिक हम लोग का एक छोटा सा टॉपिक है और इजी सा टॉपिक है. अगर हम लोग इसके फ्रीक्वेंसी का बात करें तो ईएसई एग्ज़ाम में इस टॉपिक से क्वेश्चंस रेगुलर बेसिस में पूछे जाते हैं. आपको हर एक ईयर में इस टॉपिक से क्वेश्चंस मिल जाएंगे इफ़ वी आर टॉकिंग अबाउट ईएसई प्री एग्ज़ाम. अगर गेट एग्ज़ाम का बात करें तो गेट एग्ज़ाम में इस टॉपिक से क्वेश्चंस फ्रिक्वेंटली नहीं पूछे जाते हैं, बट बीच बीच में पूछे जाते हैं. लेकिन गेट एग्ज़ाम में जो क्वेश्चंस पूछे जाते हैं ना, वो स्लाइटली डिफ़िकल्ट रहता है एज़ कम्पेयर टू द क्वेश्चंस विच आर आस्क्ड इन द ईएससी एग्ज़ाम. तो कहने को तो ये टॉपिक ईजी है, बट इस टॉपिक में कुछ पोर्शंस है जो थोड़ा सा डिफ़िकल्ट है. तो गेट एग्जामिनर जब भी क्वेश्चंस फ्रेम करता है तो वो उसी टॉपिक को पकड़ता है या फिर उसी पोर्शन को पकड़ता है जो थोड़ा सा डिफ़िकल्ट टू अंडरस्टैंड है. ठीक है, तो हम लोग इस टॉपिक को अच्छे से करेंगे. हर एक पोर्शन को बहुत अच्छे से एंड डिटेल में करेंगे, जिससे आपको कभी भी कोई क्वेश्चन सॉल्व करने में दिक्कत ना आए, फिर चाहे वो ईएससी एग्ज़ाम में पूछा जा रहा हो या फिर गेट एग्ज़ाम में पूछा जा रहा हो. तो चलो हम लोग स्टार्ट करते हैं. नाउ टू स्टार्ट विथ नंबर सिस्टम. There are four types of number system, that is decimal number system, binary number system, octal number system, and hexadecimal number system. So before continuing further, we should be aware of a very important term, that is base or radix. That is base or radix. Base or radix is number of different symbols in a number system. Number of different symbols in a number system. In any number system with base R, we have R different symbols. We have R different symbols, and each symbol can be in the range of 0 to R minus 1. So this was about the theory part. Let's see what this point 1 and 2 is meant as. Suppose we have a decimal number system. Suppose we have a decimal number system. So for decimal number system, base is 10. So for decimal number system, base is 10. So coming back to it. So what is base or radix? It is number of different symbols in a number system. So in a decimal number system, what are the different symbols available? What are the different symbols available? It is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we will count it, see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So in a decimal number system, there are 10 symbols. In a decimal number system, there are 10 symbols. So its base is 10 or its radix is 10. Similarly, if I talk about binary number system, so what are the different symbols available? Only two symbols are available, 0 and 1. So it has two symbols, and that's why its base is 2. Now coming to octal number system. Now coming to octal number system, what are the different symbols available? It is 0, 1, 2, 3, 4, 5, 6, 7, not 8, only till 7. So what are the different, how many symbols are available? So how many symbols are available in octal number system? 8 symbols are there. 8 symbols are there. And that's why its base or radix is 8. Now coming to hexadecimal number system. Coming to hexadecimal number system, what are the symbols available? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 is represented as A, 11 as B, 12 as C, 13 as D, 14 as E, 15 as F in hexadecimal number system. So what are the, how many different symbols are available in hexadecimal number system? 16 symbols are available. 16 symbols are available, and that's why its base or radix is 16. So now see, now we can understand that what this serial number 1 is saying. That is, base or radix. Base or radix is number of different symbols. Number of different symbols in a number system. So first point is clear. Now coming to second point. In any number system with base r, in any number system with base r, we are having r different symbols. This we have already seen. Like if I talk about decimal number system, we are having 10 symbols. If I talk about binary number system, we have 2 symbols, and so on. Coming to the next statement, and each symbol can be in the range of 0 to r minus 1. This is important. This is important. And each symbol can be in the range of 0 to r minus 1. See, if I talk about decimal number system, so our symbols are from 0 to 9. It is 0 to 9. That is, it is from 0 to r minus 1. Here r is 10. So 10 minus 1, that is 9. That is 9. That is 9. Or we can write it in this way. Or we can write it in this way. 0 to 9. 0 to 9. And how we are getting 9? We are getting it by r minus 1. R minus 1, that is 10 minus 1. Similarly, if I talk about binary number system, then the symbols are 0 and 1, 0 and 1, 0 and 1. So its range will be, from 0. So its range will be from 0 to 1. How we are getting 1? R minus 1. R minus 1. R minus 1. Similarly, for octal number system, its range will be 0 to 7, 0 to 7, and from hexadecimal number system, its range will be from 0 to 15. From 0 to 15. So, this point is also clear that in any number system with base r, we have r different symbols, and each symbol can be in the range of 0 to r minus 1. In decimal number system, range is from 0 to 9. Range is from 0 to 9. In binary number system, range is from 0 to 1. In number system, range is from 0 to 7, and from hexadecimal number system, range is from 0 to 15. That we can see also. Here the maximum limit is, here the maximum limit is 9. Here the maximum limit is 1. Here the maximum limit is 7, and here the maximum limit is f. F means 15. 15 is represented as f in hexadecimal number system. 15 is represented as f in hexadecimal number system. Now coming to the third point. This we will discuss a little later. So now coming to the first number system, that is decimal number system. The first point we have already discussed, that is decimal number has a base 10. Second point we have already discussed, that it uses 10 symbols, and those 10 symbols are from 0 to 9. Now coming to the third part. While discussing this, my third point of this will also get covered. See what it is written. Any number can be represented with this R symbols by multiplying with its positional value. Any number can be represented with this R symbols by multiplying with its positional value. Let us see more in details. Here it is written, for forming decimal number, the coefficient is multiplied by the powers of 10, that is multiplying by its positional value. Suppose we are given three coefficient. 2, 3, 1, 2, 3, 1, and we are asked to find its decimal count. Decimal count. So how we can find it? See, its positional value is 10 to the power 0. Its positional value is 10 to the power 1. Its positional value is 10 to the power 2. Because this coefficient 2, 3, 1 are symbols of a decimal number system. These are symbols of decimal number system. So for its, the positional value will be 10 to the power 0, 10 to the power 1, 10 to the power 2. So what will be my decimal count? My decimal count will be 2 into 10 to the power 2 plus 3 into 10 to the power 1 plus 1 into 10 to the power 0. So it will come out to be 200 plus 30 plus 1. And finally, we will get 231. 231 in decimal. Fine. Now coming to second number system, that is binary number system. Here also the first point we have already discussed, that it has a base of 2. Second point also we have discussed, that it uses two symbols, that is 0 and 1. Now coming to the third point. Suppose we are given three coefficients. Suppose we are given three coefficients of binary number system. So for binary number system, the coefficients or symbols can have only two values, that is 0 and 1. Whereas in decimal, the coefficients or symbols can have any value from 0 to 9. So we are given three coefficients, 1, 0, 1 in binary number system. Now if we are asked to find its decimal count. So see, for forming decimal count, the coefficient is multiplied by powers of 2. That is multiplying by its positional value. So in case of binary number system, what will be my positional value of 1? It will be 2 to the power 0, because now we are discussing binary number system. What will be positional value of this 0? It will be 2 to the power 1. What will be positional value of this 1? It will be 2 to the power 2. So what will be my decimal count? My decimal count will be 1 into 2 to the power 2, 0 into 2 to the power 1, 1 into 2 to the power 0. That is, we will get 4 plus 0 plus 1. That is 5. This is in decimal. This is in decimal. Fine. Now coming to octal number system. So here also, first point we have already discussed, that it has a base of 8. Second point we have already discussed, that it uses 8 symbols, that is 0 to 7. Now coming to third point. For forming decimal number, the coefficient is multiplied by powers of 8. See, suppose if we are given a number 1, 2, 3. Not number, suppose we are given 3 coefficients or 3 symbols 1, 2, 3, and these are in octal number system. These symbols are in octal number system. So what will be positional value of 3? It will be 8 to the power 0. What will be positional value of 2? 2. It will be 8 to the power 1. What will be positional value of 1? It will be 8 to the power 2. So now what will be my decimal count? So now what will be my decimal count? Decimal count will be 1 into 8 to the power 2, 2 into 8 to the power 1, 3 into 8 to the power 0. So it will come out to be 64. It will come out to be 16. It will come out to be 3. That is 64 plus 19. 64 plus 19. What we will get? 83. We will get 83. It will be in decimal. It will be in decimal. It will be in decimal. Fine. Now coming to hexadecimal number. Here also, first 2 points we have already discussed. Coming to third point. Suppose we have a number like A, B, C. Sorry, not a number. Suppose we have 3 symbols or 3 coefficients. Suppose we have 3 symbols or 3 coefficients of hexadecimal number system. And we are asked to find its decimal count. So what will be positional value of C? It will be 16 to the power 0. What will be positional value of B? It will be 16 to the power 1. What will be positional value of A? It will be 16 to the power 2. So what will be my decimal count? It will be A into 16 to the power 2, B into 16 to the power 1, C into 16 to the power 0. In hexadecimal, A means 10, B means 11, C means 12. C means 12. So it will come out to be 16 to 256. That is 2560. 2560. Here it will come out to be 16 into 11. So 16, 16, 176, 176 plus 12, plus 12. So we will get 188 means 2560, 188. It will come out to be 2748. It will come out to be 2748. It is in hexadecimal. It is in decimal. It is in decimal. It is in decimal. So I hope this part is clear to you. So I hope this part is clear to you. We have seen the description of base or radix. Then we have seen few properties of each number system. Now we will start conversion. Now we will start conversion. Now coming to the conversion part. So in conversion part, I am going to first I am going to discuss in detail the conventional method of conversion. The conventional method of conversion. And after that I will give you some short tricks so that the choice will be yours, that whether you would like to go with the conventional method or with the short trick. But be very sure that with which method you want to solve in exam. Don't make a khichdi out of it, so that when you finally appear in exam, then you get confused in both the method and finally end up in wrong result. So first talking about the decimal to any. To convert a decimal to any other base, divide the integer part repeatedly with required base and multiply the fractional part repeatedly with required base. So let us take an example. So let us take an example. Suppose we want to convert 19 to 19.25, 19.25, which is in decimal, to binary, So first we will take the integer part. So see what it is written. Divide the integer part repeatedly with required base. So we will divide the integer part repeatedly with required base, that is 2. That is 2. So 9 to the 18. Remainder is 1. 4 to the 8. Remainder is 1. 2 to the 4. Remainder is 0. 2 ones are 2. Remainder is 0. Now we will write it in this order, from top to bottom. From bottom to top. We will write it in this order, that is from bottom to top. So our answer will be 10011. Bottom to top. Now we will take the fractional part. So fractional part is and multiply the fractional part repeatedly with required base. So now we will multiply the fractional part with required base, that is 2. That is 0.25 into 2. We will get 0.50. Now in this we always have to continue multiplying the fractional part. So we will again take 0.50, and we have to continue doing it until we get a 0 in fractional part, until we get a 0 in fractional part. So 0.50 into 2, this I will get 1.00. So we are getting 0 in fractional part. So now this multiplication will end here. So now this multiplication will end here. Now in the fractional part, we will consider the integer portion. We will consider only the integer portion, and this we have to take in the order top to bottom, and this we have to take in the order top to bottom, and this we have to take in the order from top to bottom. So we will get it as 0 1. So this is my answer. So this is my answer. So this is my answer. Suppose take one another example. Suppose let's take one another example. Suppose it is given 25.6, 25.6. It is in decimal. We have to convert it into binary. So first we will repeatedly divide the integer portion. First we will repeatedly divide the integer portion. So 2 into 12, 24, remainder 1. 2 into 6, 12, remainder 0. 2 into 3, 6, remainder 0. 2 into 1, 2, remainder 1. Now we will take it in bottom to top. Now we will take it in bottom to top order. Now we will write it from bottom to top order. So our answer will be 11001. 11001 dot. Now we will take the fractional part. Now we will take the fractional part. So 0.6, and we will repeatedly multiply it with required base, and we will repeatedly multiply it with required base. So 0.6 into 2, we will get 1.2. Now 0.2 into 2, we will get 0.4. Now 0.4 into 2, 0.8. Now 0.8 into 2, 1.6. Now again you can see that we have got 0.6 into 2, that it will come out to be 1.2. So here we can see that the fractional part will never get 0. That the fractional part will, so here we can see that the fractional part will never get 0. And after some multiplication, my same term will start repeating again. My same term will start repeating again. So we will not continue it further. So we will not continue it further. We will take this one. We will take the integer part. We will take the integer part. That too in top to bottom order. That too in top to bottom order. That too in top to bottom order. And we will write it as 1001 with a dash over it. With a dash over it. This dash is the meaning of this dash is that we are getting recurring numbers. We are getting recurring numbers. After 0.8 into 2, we are getting 1.6. That is again 0.6 is repeating. That is again 0.6 is repeating. That is we are getting recurring number. So that is we are getting recurring number. So this is how we can convert from decimal to binary. So this is how we can convert from decimal to binary. So this was my decimal to binary conversion. So this was my, I forgot to write the heading. You can write it. This was my decimal to binary conversion. This was my decimal to binary conversion. Now we will discuss decimal to octal conversion. Now we will discuss decimal to octal conversion. Suppose we have, suppose it is given, we are given 27.625 in decimal and we have to convert it into octal. So again, we will repeatedly divide integer part with given base, So it is 8, 8, 3, 24, remainder 3, remainder 3. So now again, we will take it from bottom to top order. So now again, we will take it from bottom to top order. So it will come out to be, 33. So it will come out to be 33 point. Now we will take the fractional part. It is, and we will repeatedly multiply it with required base, repeatedly multiply it with required base. So it will be 8. So what is this? So 0.6258, 40, 16, 20, 50. Yes. So we will get 5.000. So my fractional part has become 0. So no need to further multiply it. So we will take it in top to bottom order. Here only one digit is there. So it will be 33.5 base 8. So now see, we will conclude two important objective questions from here. Now see, we will conclude two important objective question from here. This was given in decimal and we have converted it into 33.5 into octal. So first objective, when base decreases, here we can see that base has decreased from 10 to 8. Then integer part increases. Integer part increases. These statements are very important for your objective point of view. Here we can see that integer part is 27 and here integer part is 33. So when base decreases, then integer part increases. Now coming to second statement. When base decreases, then fraction part decreases. Here we can see that fraction part is 0.625 and here we can see that fraction part is 0.5. So it is obviously less than this. So when base decreases, fraction part also decreases. So these two statements are very important. For your objective point of view. Now coming to third conversion, that is decimal to hexa conversion. Suppose we have taken the same example, that is 27.625. It is in decimal. It is in decimal, and we want to convert it into hexadecimal. And we want to convert it into hexadecimal. So again, we will repeatedly divide the integer part with 16. 16 into 1. So we will get here 11. So we will get here 11. But in hexadecimal, 11 is written as B. In hexadecimal, 11 is written as B. So now we will take it from bottom to top order. So now we will take it from bottom to top order. So we will get 1B, 1B dot. Now coming to the fractional part, so we will multiply it with the given base, that is 16, and you can calculate it. It will come out to be 10.00. So again, the fractional part has become 0, so no need to continue it further. And in hexadecimal, 10 is represented as A. And in hexadecimal, 10 is represented as A. So we will get dot A. This is my hexadecimal. This is my hexadecimal. This is my hexadecimal. So we have discussed decimal to any conversion. Now let us see any to decimal conversion. So to convert any base to decimal, multiply each digit or each symbol with required base. Let us take an example. Suppose we want to convert, first write the heading. Suppose we want to convert binary to decimal conversion. Binary to decimal conversion. Suppose we are given any binary number. Suppose it is this binary. We want to convert it into decimal. So what we have to do? Multiply each digit with required base, or we can write positional value or positional value or weight. So this conversion any to decimal, this we have already seen. See, if I talk about this binary number system, then we have already seen that if this binary coefficients are given, and if we want to convert it into decimal, then how we have to multiply it with its positional value or positional weight. Positional value or positional weight. Similarly, we have seen the same thing for octal number system. And similarly, we have seen it for hexadecimal number system. But anyways, let us take this example also. So the number given is, so the binary number given is 1101 dot 101 dot 101. So what is positional value or positional weight of this one? It is 2 to the power 0. Positional value of this is 2 to the power 1. Positional value of this is 2 to the power 2. Positional value of this is 2 to the power 3. Now after 0, what is positional value of this? 2 to the power minus 1. Be careful in this side, that is after decimal part, how we put the positional value or positional weight. Now positional value of this is 2 to the power minus 2 and 2 to the power minus 3. Now what will be my decimal? What will be my decimal count? What will be my decimal count? It will be 1 into 2 to the power 3 plus 1 into 2 to the power 2 plus 0 into 2 to the power 1 plus 1 into 2 to the power 0 dot 1 into 2 to the power minus 1, 0 into 2 to the power minus 2, 1 into 2 to the power minus 3. So after multiplication, what we will get? Here we will get 8. Here we will get 0. 4. Here we will get 0. Here we will get 0. Here we will get 1 dot. Here we will get 0.5. Here we will get 0. Here we will get 1 by 8. 1 by 8 is nothing but 0.125. 0.125. So after addition, we will get 8, 4, 12, 13. 13.0.5, 0.125, that is 0.625. So this will be my decimal number. 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 I would suggest that remember this part, that what is 2 to the power minus 1, what is 2 to the power minus 2, what is 2 to the power minus 3. Similarly, what is 2 to the power minus 4. Remember up to minus 4. If you want to remember one more, then you can go for 2 to the power minus 5. Remember up to 2 to the power minus 5, so that you can directly put the result and get the answer, and you can save much of the precious time in the exam. So remember up to this. So this was all about our binary to decimal conversion. Now coming to another one, that is octal, that is octal to decimal conversion, that is octal to decimal conversion. Suppose we are asked to convert 37.4 in octal to decimal, So how we can do it? First we will write the symbols or the digits. So 37.4. Then we will write the positional value or positional weight. So it is 8 to the power 0, 8 to the power 1, 8 to the power minus 1. Then we will write the decimal value. Then we will write the decimal value. It is 3 into 8 to the power 1, 7 into 8 to the power 0, 4 into 8 to the power minus 1. So what we will get? Here we will get 24 Here we will get 7, and here we will get 1 by 8. 4 divided by 8, 1 by 2, that is 0.5. 0.5. That is final answer we will get 31.5. 31.5 in decimal. So easy. This is easy. Now coming to the next part, that is hexa to decimal conversion. Hexa to decimal conversion. Suppose we are given 97.4 in hexadecimal and we have to convert it into decimal. So again, first we will write the symbols given. Then we will write the positional values. Then we will write the positional values. Then we will find the decimal value. Then we will find the decimal value. It is 9 into 16 to the power 1, 7 into 16 to the power 0, 4 into 16 to the power minus 1. So it will come out to be 16, 9, 54, 9, 5, 144. 144. Here we will get 7. Here we will get 4 divided by 16 means 1 by 4. That is 0.125. 0.125. So finally we will get the answer as 131.125. It is in decimal. It is in decimal. Now let us take one more example. That is, if it is given A, B, C, D in hexadecimal, and we are asked to find it in decimal. So how we can write it? We can write it as, first we will write the given symbols or digit. Then we will put the positional values. Then we will put the positional values. Then we will find the decimal equivalent. Then we will find the decimal equivalent. See, in hexadecimal, A is 10 is represented as A. In hexadecimal, 11 is represented as B. In hexadecimal, 12 is represented as C. In hexadecimal, 13 is represented as D. So this we will get the decimal equivalent. You can solve it and you can get the final result. I am not going to solve it. I just wanted to show that how A, B, C, D or how 10, 11, 12, 13 are represented in hexadecimal, and how we do calculation with it. So this was our conversion from any to decimal. So we have seen decimal to any conversion, and we have also seen any to decimal conversion. Now there is third category also, that is any to any conversion. There is third category also, that is any to any conversion. So let us see. What is this any to any conversion. First, let us see octal to binary conversion. octal to binary conversion. Octal to binary conversion. That is octal to binary. In octal number system, we very well know that what are the symbols or digits available. In octal number system, symbols available are 0, 1, 2, 3, 4, 5, 6, and 7. Now each of these octal symbols are represented with a group of 3 bits in binary. That is, I can write it like this way: octal symbol or digit. Octal symbol or digit and its binary equivalent and its binary equivalent. So each octal symbol or octal digit can be represented as a group of 3-bit binary equivalent. As a group of 3-bit binary equivalent. That is, we can write it like this: 0, 1, 2, 3, 4, 5, 6, and 7. So 0 is represented as a group of 3-bit binary equivalent, that is 000. 1 is represented as 001. 2 is represented as 010. 3 is represented as 011. 4 is represented as 100. 5 is represented as 101. 6 is represented as 110. 7 is represented as 111. So this is my binary equivalent. These are all my binary equivalent for each symbol or digit, for each octal symbol or digit. See, I have told you earlier also that either you can memorize it, or you can write it, or during examination, you can write this on your rough sheet, for easy reference, I prefer the second method, that is writing it in the rough sheet, because why to bog your head with so much of data? And while memorizing, it may happen that you may commit mistake, that is, in place of 1 you may write the binary equivalent of 2 in the exam, and then you will do silly mistake even if you know all the concept and method. So I prefer the second method, but it is up to you. If you can memorize it, then it is well and good. If you can memorize it, then it is well and good. So let's see. Take some example. Suppose we take some example. Suppose it is given 423.15. This is given in octal. This is given in octal. And we have to convert it into binary. So first we can write this equivalent here. The method which I always opt for. It is not that I have to write again and again. We get rough sheet in the exam. At the back side of the rough sheet, we can write this table. And during the course of my syllabus, I will also tell you that what all data you can write at the back side of the rough sheet for easy reference, while solving questions. It is 0, it is 1, it is 2, it is 3, it is 4, it is 5, it is 6, it is 7. See now, how easy it is. See, what is binary equivalent of 4? It is 100, 100. What is binary equivalent of 2? 010, 010. What is binary equivalent of 3? 011, 011. Dot. What is binary equivalent of 1? 001, 001. What is binary equivalent of 5? 101, 101. So this is my binary conversion. This is my binary conversion, that is just replace this octal symbol or octal digit by its binary equivalent, by its binary equivalent, by its binary equivalent, by its binary equivalent. So easy. Now similarly, now similarly, if we are asked to find binary, similarly, if we are asked to find binary to octal conversion, binary to octal conversion, binary to octal conversion. Suppose we are asked to find binary to octal conversion. It is the second type of any to any conversion. This was my first type, octal to binary conversion, and this is my second type, that is binary to octal conversion. So suppose we are given any number. Let us suppose we are given any number. One, one, zero, one. Any example we can take. Suppose this is in binary. We have to convert it into octal. So what we have to do? See, this is my point. Now, in the left hand side, we will form group of 3 bits. We will form group of 3 bits in this direction, in this direction, in this direction. Group of 3 bits in this direction, then group of 3 bits in this direction, or we can write it below only. Suppose I write the question here once again. So what we have to do? First, we will take decimal as the reference. First, we will take decimal as the reference. Then we will start forming pair of then we will start forming group of 3 bits. Group of 3 bits. We have to form group of 3 bits toward in the left hand side of decimal as well as in the right hand side of decimal. We have to form group of 3 bits in the left hand side of decimal as well as in the right hand side of decimal. Now in which direction or in which order we have to form the group. So if we take the left hand side portion of decimal, if we take the left hand side portion of decimal, then we have to form group of 3 bits in this direction. Group of 3 bits in this direction. Now again group of 3 bits in this direction. Now here only one bit is available. Here only one bit is available. So we can put 0 0 here. We can put 0 0 here. We can put 0 0 here. So after putting 0 0, we can again form a group of 3 bits. See, this part is important. That is, we can add any number of zeros. We can add any number of zeros before integer, before integer part. See, this is my integer part. Before decimal is my integer part, and after decimal is my fraction part. So in the integer part, we can write any number of 0 before the integer part. Before the integer part, it doesn't make any difference in the final result or the value. And similarly, we can add any number of zeros. And similarly, we can add any number of zeros after the fractional part. After the fractional part. That is, if I am talking about the fractional part, that is, if I am talking about the fractional part, then we can add any number of 0 in its right hand side, in its right hand side, in its right hand side. And similarly, if we are talking about the integer part, and similarly, if we are talking about the integer part, then we can add any number of zeros in the LHS of integer part. In the LHS of integer part, it is not going to affect our result or value. This is important concept which you already know, but still I am repeating it. So now see, we have formed a group of 3 bits in the integer part, and the direction is from right to left, from right to left, right to left. Now we have to replace it with its octal equivalent. Now we have to replace it with its octal equivalent. So what is octal equivalent of 110? 110 is 6. What is octal equivalent of 110? Again it is 6. What is octal equivalent of 001? It is 1. Now similarly, if I talk about the fractional part, then so now this time we again have to form group of 3 bits. We again have to form group of 3 bits, but this time the grouping will be in this direction. But in this time the grouping will be in this direction, that is from left to right, that is from left to right. Now here again one bit, so we can add 0. So we can add 0 to make it a group of 3 bit. To make it a group of 3 bit. Now what is octal equivalent of 110? It is again 6. What is octal equivalent of 100? Octal equivalent of 100 is 4. So my final result, is 166.64, and this is my octal to binary to octal conversion. This is my binary to octal conversion. Very easy, you must be knowing it, but still have a look once more. Now coming to the third conversion, and that is hexa, and that is hexa to binary conversion, and that is hexa to binary conversion. So similarly, in hexa, what are the symbols or digits available? Symbols or digits available are 0, 1, 2. It will go on. It will go on up to A, B, C, D, E, F. Now similarly, if I talk about the hexadecimal equivalent in binary, then each hexadecimal symbol or each hexadecimal digit is represented in binary as a group of 4 bit. It is represented in binary. It is represented in binary as a group of 4 bit. And what are the 4 bits? Same here also, it is up to you that either you can memorize it or you can write it at the back of the rough sheet which you get in the exam. I prefer the second one. there are many important data which you have to remember for exam. So why to bog your head by remembering this silly 1001 data? It is better to write it at the back of the rough sheet only. But still, the decision is up to you. So this is my binary. This is my binary. This is my binary equivalent. This is my binary equivalent. And what will be my hexadecimal? What will be my hexadecimal equivalent? So it is 0, it is 1, it is 2, it is 3, it is 4, it is 5, it is 6, 7, 8, 9, A, B, C, D, E, F. Fine. So suppose we take an example. Suppose we take an example like this only. A, B, C, D dot 2, 3. It is in hexadecimal. Now we have to convert it into binary. See how it is. See how easy it is. See how easy it is. What is binary equivalent of A? What is binary equivalent of A? It is 1010. What is binary equivalent of B? 1011. 1011. What is binary equivalent of C? It is 1100. 1100. What is binary equivalent of D? 1101. 1101. Dot. What is binary equivalent of 2? 0010. What is binary equivalent of 3? 0011. So this is my hexadecimal to binary conversion. Now similarly, if we are asked to find binary to hexadecimal conversion, so you can take this example only. Before decimal, we have to form, this time we have to form group of 4 bits. In octal, we were forming group of 3 bits, but now we have to form group of 4 bit, and its direction will be from right to left for before decimal. Right to left, right to left, right to left. And after decimal, the direction of forming group of 4 bits will be from left to right. Left to right. Now this is so now we have formed the group of 4 bit. Now we have to find its hexadecimal equivalent. Now we have to find its hexadecimal equivalent. So what is hexadecimal equivalent of 1010? 1010 is A. 1011, 1011 is B. 1100, 1100 is C. 1101, 1101 is D. 0010, 0010 is 2. 0011, 0011 is 3. So this is my hexadecimal. We can see that we again got the same result. So this was all about any to any conversion. So this was all about any to any conversion. We have seen four types of any to any conversion. Now the last one is or the second last one, we can say, that is octal to hexadecimal. Octal to hexadecimal conversion. Octal to hexadecimal conversion. So if we are asked to find octal to hexadecimal conversion, that is, suppose we are given octal number, suppose we are given octal number 765. 765, it is in octal, and we have to convert it into hexadecimal, So see what process you can follow. First convert the octal number into binary. First convert it into binary, and from binary convert it into hexadecimal. From binary convert it into hexadecimal. See how we can do it. See, these two things, that is this octal these two things, that is this binary equivalent of octal symbols and binary equivalent of hexadecimals symbol. These two things, either you have to remember it or you have to write it in the rough page. And after doing it, you can see that how simple your this all conversions will become. So see, what is the binary equivalent of octal symbol 7? It is 111. What is binary equivalent of 6? It is 110. What is binary equivalent of 5? It is 101. So now we have converted octal to binary. Now we have converted octal to binary. Now we have to convert binary to hexadecimal. Now we have to convert binary to hexadecimal. So how we can convert it? We can convert it by forming a group of 4 bits. By forming a group of 4 bits, and it is before decimal, so the bits will be grouped from right to left. From right to left. So take in the group of 4 bits like this. Now here we have only one bit, so we can add 30 here. We can add 30 here. We can add 30 here. Any number of zeros can be added in the LHS of integer part. So this. Now what is hexadecimal equivalent of 0101? 0101 is 5. What is hexadecimal equivalent of 1111? It is F. What is hexadecimal equivalent of 0001? It is 1. So final answer is 1F5. 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 So what we have done, first we have converted octal to binary. First we have converted octal to binary, and then we have converted binary to hexadecimal. And then we have converted binary to hexadecimal. Similarly, suppose we are asked Similarly, if we are supposed we are asked to find hexa to octal conversion, hexa to octal conversion. This is our last conversion also. This is our last conversion also. Suppose we are given ABC. ABC, it is in hexadecimal. We have to convert it into octal. So how we can do? Again, we have to first find hexadecimal to binary conversion. We have to first find hexadecimal to binary conversion, and then from binary we can find octal. And then from binary we can find octal. So see, what is the binary equivalent of A? Binary equivalent of A is 1010. What is binary equivalent of B? It is 1011. C 1100. Now if we want to convert it into see, this is already converted into binary. Now if we want to convert it into octal, so we have to group it as a group of 3 bits. So we have to group it as a group of 3 bits. So we have to group it as a group of 3 bits. So see, what is octal equivalent of 100? It is 4. What is octal equivalent of 111? It is 7. What is octal equivalent of 010? It is 2. What is octal equivalent of 101? 101, it is 5. So my final answer will be 5274. 5274. It is in oct. So this was all about our conversion technique. This was all about our conversion technique. That is conventional way of converting. That is conventional way of converting decimal to any to decimal, any to any. It is very easy part and asked in exam, which are frequently asked in exam. Now, coming to addition in number system. Now, coming to addition in number system. So, first we will look into binary addition. So, first we will look into binary addition. So, let's make a table first. Suppose we have two variables a and b, and after adding two variables a and b, what will be our sum and what will be our carry, and what will be our carry. So if a is 0, b is 0, sum will be 0, carry will be 0. If a is 0, b is 1, sum will be 1, carry will be 0. If a is 1, b is 0, sum will be 1, carry will be 0. If a is 1, b is 1, sum will be 0, carry will be 1. This is important. This is important. You all must be knowing about it, but still just have a relook into it. So if A is 1, B is 1, sum will be 0 and a carry will be 1. Fine. Suppose we take an example like this 1, 1, 1. If we have to add it, then what we will get? 1 plus 1 will be 0, carry 1. 1 plus 1 will be 0, carry 1. 0 plus 1 will be 1. So now this carry will come here. So this will be the sum. Suppose let us take another example. 1, 1, 1, 1. Now if we have to add it, then what we will get? 1 plus 1, 0, carry 1. 0 plus 1, 1. Now again 1 plus 1, 0 and carry 1. Now again 1 plus 1, 0, carry 1. Now this one will come here. So this will be my answer. This will be my answer. Now if we want to take another example, suppose we are given 1, 1, 1, 1, 1. And if we have to add it, what will be the result? 1 plus 1, 0, carry 1. 0 plus 1, 1. Now 1 plus 1, 0, carry 1. Now 0 plus 1, 1. Now here 1 plus 1, 0, carry 1. Now this one will come here. So if these three examples are clear to you, then you can do any binary addition. This is easy. You all must be knowing about it, but still we can recap it here. So these three examples are very important. Just have a look. Now we can take some examples. Like if it is given 1 0 1 1 0 1, we have to add it with 0 1 1 1 1 1. We have to add it. So what will be my answer? 1 plus 1 0, carry 1. 1 plus 0 1. 1 plus 1 0, carry 1. 1 plus 1 0, carry 1. 0 plus 1 1. Now 1 plus 1 0, carry 1. 0 plus 1 1. Now 1 plus 0 1. 1 plus 1 0, carry 1. Now 1 plus 1 0, carry 1. 0 plus 0 0. Now this carry will come here. So this is my answer. So I hope that now it is clear to you, and you can further take some more examples or on your own, or you can refer my capsule booklet. There you will find few more examples based on binary addition. Now come into one concept which is based on binary addition, and that is multiplication. Multiplication of two binary number. Multiplication of two binary number. Multiplication of two binary number. Fine. So see how we can achieve multiplication of two binary number. Suppose we are given two number 1101. It is in binary, and we have to multiply it with 011. This is also in binary, and we have to find the result in binary. So how we can solve it? First write 1101, then 011. So we can solve it as we do normal multiplication. That is, we will get 1 into 1 1, 0 1 1. Now again 1 0 1 1. Now again 0 0 0 0. Now we have to add it. 1 will come here. 0 plus 1 1. 1 1 1 0, carry 1. 1 1 0, carry 1. 1 plus 0 1. So this will be my answer. So this was a small concept, that is the multiplication of two binary number, which is based on the binary addition only, so you must know about it. Now coming to second one, that is octal addition. Octal addition. In octal number system, we have already seen that the symbols available are digit available are 0, 1, 2, 3, 4, 5, 6, 7. That is, we have already discussed that in any number system having base r, the symbols or digits ranges from 0 to r minus 1. We have already seen we have already seen and discussed also, that is in any number system, that is in any number system of base r, the symbols or digits ranges from 0 to r minus 1. 0 to r minus 1. Now let us see one very important chart here. Suppose here we take decimal number, decimal number, and here we will take its octal representation, its octal representation. So for decimal number 0, its octal representation is 0. For decimal number 1, octal representation will be 1. Similarly for 2, it will be 2, and so on. Up to 7, there is no problem. The fun begins from 8. The fun begins from 8. For decimal number 8, what will be its octal representation? What will be its octal representation? Its octal representation will be 1 0. Its octal representation will be 1 0. How we are getting 1 0? See, we have already seen that 8 is in decimal. If we want to convert it into octal, how we can convert it? Now we will move in this way. So 1 0. So for 8 it is 1 0. What will come for 9? It will come 1 1. What will come for 10? It will come 1 2. We can see again for 10 also 1 2. Fine. What will come for 11? 1 3. What will come for 12? 1 4. What will come for 13? 1 5. Let me delete it. I am continuing from here only. I am continuing from here only. What will be for 14? It will be 1 6. What will be? Let us take the another page. Otherwise, you will get confused. What will be for 15? What will be for 15? It will be 1 7. It will be 1 7. Now again the fun begins at 16. What will be octal representation of decimal number 16? It will be 2 0. See how we are getting it? 16 divided by 8, 2 0, moving in this direction. Now what will be for 17? It will be 2 1, 18, 2 2, 19, 2 3, 20, 2 4, 21, 2 5, 22, 2 6, 23, 2 7. Now for 24, the fun will begin. What will be for 24? It will be 3 0. See, 24, 8, these are 24, 3 0. So this is the way how we get octal representation. So this is the way how we get octal representation of different decimal number. From here we can see that the maximum number which we will get in octal representation is only 7. After 7, things will start getting changed. See, here also up to 17, 1 7, then thing changes. here 27, then things changes. So this table, you should be aware of that how we are getting this table. You should be aware of how we are getting this table, how we are converting decimal to octal, and then we are getting this table, because it will be useful for solving questions, So let us take some examples. Suppose we have an example. Take any example. Add 256 with 765. This is my addition in octal. This is my addition in octal. So what will be my result? See, you don't have to remember this table. If you had already remembered it, then it is fine. Otherwise, you can directly convert it. And get the result. You don't need to remember that table. See how we can do it. See here, 6 plus 5 11. That is, it is more than 7. That is, we have to convert it and see that what will be its octal representation. Then 8 1 3 1 3. That is 3 carry 1. Fine. Now 1 plus 5 6, 6 plus 6 12, greater than 7. So 12 divided by 8, 1 4. So we will get it as 4 carry 1. Now 3, 1 plus 2 3, 3 plus 7 10, greater than 7. So 1 2. 2 carry 1. 2 carry 1. So this will be my answer. So this will be my answer in octal. So this is how we do octal addition. We can take one more example. 2 3 4, 4 1 5. We have to do it. We have to do the addition, and it is in octal. So 4 plus 5 9, greater than 7. We have to convert it. Then we will get 1 1. So 1 carry 1. 1 plus 3 4, 4 plus 1 5. 5 is within the range. 5 is within the range of octal uh, symbols. So we will write it directly 5. Now 2 plus 4 6. 6 is also within the range. So this will be my result. In octal. So this is how we do. Our octal addition. Now coming to the third one, that is hexadecimal addition. Hexadecimal addition. So here also we have already seen in hexadecimal number system that what are the symbols available. Symbols available are 0, 1 up to 9, then A, B, C, D, E, F, where 10 is represented as A in hexadecimal, and so on. So here also we can see that as the base is 16, so the symbols or digits available ranges from 0 to R minus 1, that is 0 to 15. Or we can write it as 0 to F, because 15 is represented as F in hexadecimal number system. Now here also we can form a table, that is a decimal number, that is decimal number, and hexadecimal representation. Hexadecimal representation. So here for 0 it will be 0, for 1 it will be 1, it will go on, for 9 it will be 9, for 10 it is A, for 11 it is B, for 12 it is C, for 13 it is D, for 14 it is E, for 15 it is F. Fine up to here. Now fun begins at 16. Now fun begins at 16. What will be hexadecimal representation of decimal number 16? It is 10. It is 10. How we are getting? It is in decimal. We have to convert it into hexadecimal. So divide it by 16. 1, 0. Take it in this order. Fine. Similarly, for 17, we will get 1, 1. For 18, we will get 1, 2. For 19, we will get 1, 3. For 20, we will get 1, 4. For 21, we will get 1, 5. For 22, we will get 1, 6. For 23, we will get 1, 7. For 24, we will get 1, 8. For 25, we will get 1, 9. For 26, see, for 26, what we will get? Divided by 16, it is 10. Take it is in this order. 10 is represented as A in hexadecimal. So we will get 1A. Very important. For 27, we will get 1B. 28, we will get 1C. 29, we will get 1D. 30, we will get 1E. 31, we will get 1F. Now fun begins as 32. What will be hexadecimal representation of 32? It will be 20. It will be 20. Now again for 33, it will be 21 and so on. It will be 21 and so on. So this table is important. You should be aware of that how we are getting this table. You shouldn't remember it, but you should be aware of that how we are getting this table, so that you can easily evaluate it while solving addition problem based on hexadecimal. Addition problem based on hexadecimal. Now suppose take an example. Suppose take an example, that is 7, 8, 9, 9, 8, 7. We have to add it. We have to add it, and it is in hexadecimal. And it is in hexadecimal. Then see what we will get. 9 plus 7. 9 plus 7 is 16. 9 plus 7 is 16. How 16 is represented in hexadecimal? It is 10. That is 0, carry 1. Now 8 plus 1, 9. 9 plus 8, 17. 17. How 17 is represented in hexadecimal? It is 1, 1. That is 1, carry 1. Now 7 plus 1, 8. 8 plus 9, it is 17. It is 17. So again, it will be 1, 1. that is 1, carry 1, that is 6, 17. How we are represented in 17? It is 1, 1, taken it in this order, and this is our carry. So this will be the result. So this will be my result. So this will be my result in hexadecimal. So this will be my result in hexadecimal. See, it is very easy. See, it is very easy. You don't have to remember any table or anything like that. You don't have to remember anything. You can directly do the conversion at the time of solving the exam question. And generally, after practicing, see, you are going to practice many questions during my lectures also. You are going to solve many questions from my capsule booklet also. Then you will obviously solve a previous year question that I will only help you in solving the questions of previous year exams. Then you will take up test series, and after doing all this, no, for some basic result you will know the answers. That is, if it is asked that what is representation of 16 in hexadecimal, it will be on your tip that it will be 10. For 17 it is 11. By solving you will get it. But don't mug up, don't try to mug up any table. Even if you are not able to remember it, just do the conversion at the time of solving the question. It will hardly take 10 seconds, but the chances of committing mistake will reduce. So now we will take one more example based on this hexadecimal. Suppose it is AAA and BBB. Now we have to do its addition. Now we have to do its addition in hexadecimal. So we know that 10 is represented as A in hexadecimal, and 11 is represented as B in hexadecimal. So 10 plus 11, we will get 21. Now see how 21 is represented in hexadecimal. It is this 1, 5. So here we will get 5, carry 1. So now 1 plus A plus B, we will get 22. We will get 22. What will be 22? It will be 6, carry 1. Here again 22, it will be 6, carry 1. So this will be my result, and this will be my answer in hexadecimal. So this is the way by which we do hexadecimal addition, and previously we have seen that how we perform octal addition, and before that we have seen that how we perform binary addition. So I hope that now this addition method of all the three types of number system is clear to you. Now, coming to subtraction in number system. Subtraction in number system. So first we will start with subtraction in decimal. Subtraction in decimal number system. Subtraction in decimal number system. See, this subtraction in decimal number system, this subtraction we are doing right from our childhood. But still I want to, so I'm not going to teach you subtraction in decimal number system again. But from here I want to take one important concept which will be used in other number systems also. That is, suppose if we are given two number, that is 2, 3, and if we have to subtract it, and if we have to subtract it with suppose 1, 7, we have to subtract 1, 7, 17 from 23, and This whole operation is based on decimal number system. So see, 3 is less than 7. 3 is less than 7. That is, we have to take borrow. That is, we have to take borrow from here. That is, we have to take borrow from here. So when we take borrow in decimal number system, then what is the amount of borrow which we take? What is the amount of borrow which we take? We take 10 as borrow. We take 10 as borrow. What is this 10? 10 is the base of the number system. Here my number system is decimal number system having base 10. So we are taking 10 as borrow. So we are taking 10 as borrow. Then what it will become? It will become 10 plus 3, 13. It will become 10 plus 3, 13. And 13 is subtracted, and now 7, and now 7 will be subtracted from 13. 7 will be subtracted from 13. That is, we will get 6 here. That is, we will get 6 here. Now, after giving this borrow, what will be left here? What will be left here? Here 1 will be left. So 1 minus 1, it will be 0. This will be my answer. So the concept which I wanted to take from the decimal number system is that while doing while doing subtraction in any number system, in any number system, borrow taken is equal to base of number system, is equal to base of number system, is equal to base of number system. So this is an important concept which we already know in decimal number system, but we have to apply the same concept in other number system also. In other number system also. So now let us discuss subtraction in binary number system. Subtraction in binary number system. So let us form a table here also. So let us form a table here also. Suppose A and B are given. We have to perform A minus B. We have to perform A minus B. So what result will be? What result we will get? So what result we will get? So what result we will get, and what will be borrow taken, and what will be borrow taken? So if we are performing 0 minus 0, result will be 0, borrow will be 0. If we are performing 0 minus 1, this we will take little later. First, we will discuss this. If we have to perform 1 minus 0, 1 minus 0, so result will be 1, borrow will be 0. If we have to perform 1 minus 1, if we have to perform 1 minus 1, result will be 0, result will be 0, borrow will be 0, borrow will be 0. Now coming to this 0 minus 1, this is important. Only this is important in subtraction. You should have a clear concept regarding this operation. You should have a clear concept regarding this operation. Then everything else is easy. Then everything else is easy in subtraction. So see what we are doing it. So see what we are doing here. We want to perform 0 minus 1. We want to perform 0 minus 1 in binary number system. In binary number system. So see what will take place. Here 0 has to take borrow from here. Here 0 has to take borrow from here. So how much borrow 0 will take? It will take 2, because we have already discussed that while doing subtraction in any number system, borrow taken is equal to base of number system. So here base of number system is 2, so borrow taken will be 2. Now 2 minus 1, we will get answer as 1. 2 minus 1, we will get answer as 1. 2 minus 1, we will get answer as 1. 2 minus 1, we will get answer as 1. So what will be the result here? Here we will get 1. Answer is 1, and borrow taken will also be 1. And borrow taken will also be 1. And borrow taken will also be 1. So let us take one more example. So let us take one more example. Suppose we are given this number and we have to subtract it by this number. And this whole operation is in binary number system. And this whole operation is in binary number system. Then see what will take place. Let me write it a little lower. So we are given this number. We are given this number and we have to subtract it by this number. And this complete operation is in binary. And this complete operation is in binary. Now see 0 minus 1, 0 minus 1. If we will go by this table, then what is 0 minus 1? Result is 1, borrow is 1. Result 1, and here we will get a borrow. See, we will go by this method little later. First, let's discuss how the actual processing is taking place. First, let us discuss how the actual processing is taking place. And once you are comfortable with it, then we can write the result directly. Otherwise, if now I will start writing result directly, then you will not understand it properly. So see, now this 0 will take a borrow from here. This 0 will take a borrow from here. How much will be the borrow? The borrow will be 2. So now 2 minus 1, we will get 1 here. Now this 0 will take a borrow from here. Now this 0 will take a borrow from here. How much will be the borrow? 2. Now after taking borrow from here, this 0 will give borrow to this number also. This 0 will give borrow to this 0 also. after given borrow, what will be left here? What will be left here? It will be left, that is 2 minus 1. It will be left 1 here. It will be left 1 here. 2 minus 1. It will be left 1 here. So 1 minus 1. 1 minus 1 is 0. 1 minus 1 is 0. Now this 0 will take a borrow from here. It will take a borrow from here. What will be the borrow? 2 will be the borrow, which is equal to the base of number system. After taking borrow, this 0 will give borrow to this 0. This 0 will give borrow to this 0. So what will be left here? 2 minus 1, 1 will be left here. 2 minus 1, 1 will be left here. Now 1 minus 1, we will get 0 here. 1 minus 1, we will get 0 here. Here, after giving borrow to this 0, after giving borrow to this 0, what will be left here? What will be left here? Here 0 will be left. Here 0 will be left. Here 0 will be left. Now 0 minus 0, we will get 0. 0 minus 0, we will get 0. This will be our answer. This will be our answer. I hope now you are comfortable with it. Subtraction also you are solving it from high school, so I think that you must be knowing it, but still we can have a recap here. Now let us solve this subtraction. Now let us solve this subtraction in binary number system. So now we are comfortable in it, so we will solve it directly. See, 0 minus 1, we know answer is 1 and we have to take borrow. After taking borrow, what will be left here? 0 will be left here. So 0 minus 0, 0. Now coming to here, 0 minus 1, answer is 1. We have to take borrow. After taking borrow, what will be left here? 0 will be left here. So 0 minus 0, we will get 0. So this is our answer. So this is our answer. Now coming to third one, that is subtraction in octal number system. Subtraction in octal number system. Let us take an example. Suppose we take 743,265. We have to do its subtraction, and that too in octal number system. So see here, 3 is less than 5. We have to take borrow from here. What will be the borrow? Borrow will be 8. That is base of number system. Borrow will be 8. That is base of number system. So now 8 plus 3. 8 plus 3 is 11. 8 plus 3 is 11. 11 minus 5. 11 minus 5 will be 6. After giving borrow, what will be left here? After giving borrow, what will be left here? 3 will be left here. 3 will be left here. Now it will again, now 3 is less than 6. 3 is less than 6. So it will again take a borrow. So it will again take a borrow. What will be the borrow? Borrow will be 8. It will again take a borrow. What will be the borrow? Borrow will be 8. So 8 plus 3, 11. 8 plus 3, 11. 11 minus 6, 5. 11 minus 6, 5. 11 minus 6, 5. 11 minus 6 is 5. Now, what will be left here? Now, what will be left here? 6 will be left here. So, 6 minus 2. 6 minus 2 will be 4. See, so simple. Only important thing that we have to keep in mind, only important thing we have to keep in mind is that how much borrow is taken in each number system, how much borrow is taken in each number system, and that is equal to base of number system. If this concept is clear to you, then rest part of subtraction will be very easy, and for octal and hexadecimal it will be just like subtraction in decimal number system. And in octal and hexadecimal number system it will be similar to subtraction in decimal number system. For binary number system you should have a little more concept of this question. Refer this question 2 to 3 times, refer this question 2 to 3 times, and after that all your doubt of binary number system will also be resolved. So this was our subtraction in octal number system. I think one example is sufficient here. For other example, you can refer my capsule question bank. So now coming to the fourth one. So now coming to the fourth one, and that is subtraction, and that is subtraction in hexadecimal. Subtraction in hexadecimal number system. Subtraction in hexadecimal number system. Suppose we take an example. Let us take any example. 7, A, 6, 3, B, 7. Suppose we have to subtract both this, and this is in hexadecimal number system. So now 6 is less than 7. We have to take a borrow. What will be the borrow taken? It will be 16, that is equal to base of number system. So 16 plus 6, 16 plus 6 is 22. 22 minus 7. 22 minus 7 will be 15. 22 minus 7 will be 15. 15 is represented as F in hexadecimal number system. Now after giving borrow, what we will get here? We will get 10 minus 1, a minus 1, that is 10 minus 1, that is we will get 9 here. We will get 9 here. Now 9 is less than b, 9 is less than b. So we will take a borrow here. So we will take a borrow here. What will be the borrow? It will be 16. Now 16 plus 9, 16 plus 9 is 25. 16 plus 9 is 25. And 25 minus b, b is 11. 25 minus b, b is 11. So 25 minus 11, we will get 14. We will get 14. 14 is represented as E in hexadecimal number system. 14 is represented as E in hexadecimal number system. Now after giving borrow, what will be left here? Here 6 will be left. Now 6 minus 3, 6 minus 3, we will get 3 here. 6 minus 3, we will get 3 here. So this is the result. So this is the subtraction result in hexadecimal number system. So this is a subtraction result in hexadecimal number system. I hope this is also clear to you. I hope this is also clear to you. Once this funda is clear that how much borrow is taken, rest is very easy in subtraction. Rest is very easy in subtraction. So coming to next topic, that is complements. So for a given base, So for a given base, we have two types of complements. That is, if the given base is R, if given base is R, then we will have R complement, then we will have R complement, as well as we will have R minus 1's complement, R minus 1 complement. So for binary number system, having base 2, so for binary number system having base 2, so for binary number system having base 2, we will have two types of complements, that is 1's complement and 2's complement and 2's complement. Similarly, for octal number system, similarly for octal number system having base 8, having base 8, we have two types of complement, that is 7's complement and 8's complement. Similarly, for hexadecimal number system, similarly for a hexadecimal number system having base 16, we have two types of complement, that is F's complement or 16's complement or 16's complement. So this one, this one and this one are my R minus 1's complement, R minus 1's complement. And this one and this one are my R's complement, are my R's complement. So first we will discuss all the R minus 1's complement. First we will discuss all the R minus 1's complement. So starting with 1's complement. So what is the conventional way of finding 1's complement? What is the conventional way of finding 1's complement? Conventional way is to find to 1's complement subtract all the bits by 1. That is, for example, if we are given 1 0 1 0 1 and we are asked to find its one's complement, its one's complement. So how we can find it? We can find it by subtracting all the bits by 1. What will be my answer? My answer will be 1 minus 1 0 1 0 1 0. This is my answer. This is my answer. So this is the conventional way of finding one's complement, but we will always apply shortcut for finding one's complement. What is the shortcut? Complement complement each bit, complement each bits to find one's complement. See, suppose if I take this example only, that is 10101, 10101. This is the question. We are asked to find its one's complement. So we will complement each bit. So 1 will become 0, 0 will become 1, 1 will become 0, 0 will become 1, 1 will become 0. This is my answer. How we are getting it? We are getting it by complementing each bits. By complementing each bits. See, is this answer same as the previous one? 0 1 0 1 0, 0 1 0 1 0. So this is the method of finding one's complement. First one is the conventional method. Second one is the shortcut. Always go for shortcut. Now, coming to second, r minus 1's complement. That is, if we are talking about the octal number system, then we have to find 7's complement. Then we have to find 7's complement. Then we have to find 7's complement. So what is the method of finding 7's complement? Subtract each digit or symbols by 7. That is, suppose we are given a question, that is to find 7's complement. Find 7's complement of 5 to 4. So how we can find it? Subtract each digit or symbols by 7. So first write 777, then write the given number and then subtract it. What we will get? We will get 3, here 5, here 2. This is my answer. This is my answer. This is my answer. Now, coming to the third one, That is if hexadecimal number system is given, then what will be the r minus 1's complement? It will be f's complement. How to find f's complement? Subtract each digit, subtract each digit or symbol by f. So suppose we are given a question. Question given is find f's complement. Find f's complement of 9a6. How we can find it? First we will write f and then we will subtract 9a6 from f. So what will be my answer? 15 minus 6, 9. 15 minus 10, 5. 15 minus 9, 6. This will be my answer. This will be my answer. Fine. Now, coming to r's complement. So for r's complement, I can write a general statement. That is, for finding r's complement, first find r minus 1's complement, r minus 1 complement, and then add 1, and then add 1 at LSD, that is least significant digit, Now see, let us take an example. First question, find 2's complement, of 1011. So how we can solve it? First we will find r minus 1's complement, that is 1's complement. So how we can find 1's complement? Complement each bit. So we will get 0, 1, 0, 0. Then add 1 at LSD. So let's add 1 at LSD. We will get 1, 0, 1, 0. This is my answer. This is my 2's complement of 1011. This is my 2's complement of 1011. Similarly, if we are asked to find 8's complement of 6 to 7. So first we will find its 7 complement. First we will find its 7's complement, that is we will subtract 6 to 7 from 777. What we will get? We will get 0, 5, 1. Now we will add 1 at the LSD. So what we will get? We will get 151. This is my answer. Now coming to the next one. find 16's complement of A, B, C. So first we will find F's complement. First we will find F's complement. It will be F, F, F. Now we will subtract A, B, C from F, F, F. So 15 minus 12, 3. 15 minus 11, 4. 15 minus 10, 5. Now we will add 1 at LSD. So we will get 544. This is my answer. So this is the way of finding R minus 1's complement and then finding R's complement. Now see, you may ask that, sir, what is the significance? What is the significance of complement method? What is the significance of complement method? Significance of complement method. So its significance is that by complement method, by complement method, we can perform subtraction. We can perform subtraction from addition. So you may say that what we are achieving by performing this subtraction from addition. Then see, for if we want to do addition of two numbers, then we will require hardware for addition. That is, we may require some adder circuit. Similarly, if we will perform subtraction, then we will require some other hardware also for subtraction. So, if we can perform subtraction from addition, then it means that my same circuit, which or the same not circuit, the same hardware, the same adder hardware, which is performing addition, same hardware can perform subtraction also. So there is no requirement of any additional hardware for subtraction. So the ultimate aim of a developer of a circuit is that everyone wants to develop a circuit using the minimum possible hardware. First, because it will be related to cost. The cost will be high because you all know that cost is directly proportional to the number of components or number of hardware attached with a system. So cost will drastically reduce if we are having less hardware, and less hardware will also give us good speed. So by using complement method, we can perform subtraction from addition. So there is no requirement of any separate hardware for subtraction method. So this is the significance of complement method. And if you get an objective question based on it, either in ESE or in PSU exam, then you can easily solve it. In our coming sessions, we will look into that how we are performing the subtraction using 1's complement and 2's complement, where by using complement method, we will be actually doing addition, but the result will be that of subtraction. So we will look into that in details. Now, coming to next topic, that is difference between unsigned magnitude representation and signed magnitude representation. Very important for your exam point of view. It is little complex also. Students generally have doubt on this topic, mainly the signed magnitude representation part. So listen it carefully. Signed magnitude representation can be further divided into three parts. That is, first is signed representation. Second is one's complement representation. Third is two's complement representation. Fine. Now, if I talk about signed magnitude representation, then if I talk about unsigned magnitude representation, signed magnitude representation we will take a little later. First, if we talk about unsigned magnitude representation, then then unsigned magnitude representation is used only for positive numbers. Is used only for positive number. Now, if we talk about the range, the range of unsigned magnitude representation, then what will be the range? Suppose we have 3 bits, that is n is equal to 3. Then what will be its range? We already know that if n is equal to 3, then range will be from 0, 0, 0, 0, 0, 1 to 1, 1, 1. Similarly, if we have 4 bits, n is equal to 4, then what will be the range? Range will be from 0, 0, 0, 0 to 1, 1, 1, 1. So if we want to generalize it, So if we want to generalize it, then we can say that range of unsigned magnitude representation, range of unsigned magnitude representation for n bits will be, for n bits will be from 0 to, from 0 to 2 to the power n minus 1, 2 to the power n minus 1. See, if I talk about n is equal to 3, then what will be the range? Its range will be from 0 to 111, that is, it is 7. Similarly, if we talk about n is equal to 4, then what will be the range? Its range will be from 0000, that is from 0 to 1111, that is 15. That is 50. So this part we already know. This unsigned magnitude representation part we already know, because we have been writing it previously, all the details in unsigned magnitude part only, in unsigned magnitude form only. Now we will look into the signed magnitude representation, because this is the new thing which we are going to learn. Now, coming to signed magnitude representation. Signed magnitude representation. First is signed representation. Listen carefully. Now see, signed representation is used to represent, it is used to represent, it is used to represent both positive, both positive and negative numbers. In unsigned magnitude representation, we have discussed that it is used to represent only for positive numbers. But in a signed magnitude representation, it is used to represent both positive and negative number. So how it is represented? How it is represented? See, in signed magnitude representation, the MSB bit, suppose we have two numbers in binary. Then in signed representation, how we can differentiate that which number is positive and which number is negative? How we can differentiate which number is positive and which number is negative? Then, if MSB, then if MSB, if MSB bit is 0, if MSB bit is 0, then number is positive. Then number then number is positive. If MSB bit is 1, if MSB bit is 1, then number is negative. Then number is negative. That is, MSB bit differentiates which number is positive or which number is negative. That is, MSB bit in signed magnitude representation, MSB bit denotes the sign of a number. That is, in signed magnitude representation, MSB bit will denote the sign of the number, and it will be same, for all three. It will be same for all three. That is, in signed representation, in 1's complement representation and 2's complement representation, from MSB bit we can easily conclude whether my number is positive or negative. Then what is the difference between signed 1's and 2's? That we will discuss. So I hope that this part is clear. That is, for signed magnitude representation, we can represent both positive and negative number. And how we can represent positive and negative number? We have to conclude from the MSB bit. If MSB bit is 0, number will be positive. If MSB bit is 1, then number will be negative. Now, let us take an example. That is, represent plus 5. In signed representation, in 7-bit format. In 7-bit format. Now listen to me carefully. So we have to represent plus 5. We have to represent plus 5 in signed representation, and that too in 7-bit format. So first we have to convert a decimal 5 into binary 5. So first we have to convert a decimal 5 into binary 5. So we very well know from our shortcut method that how we can convert a decimal 5 into binary 5, and that too in 7-bit format, Now see, is this my conversion of plus 5 of decimal number plus 5 into binary? See, it will be 2 to the power 0, 2 to the power 2. So we will get 5. Fine. This all we know. We have already discussed it in details in our earlier discussion. So first we have to convert decimal 5 into binary 5. Now it is my positive number. It is my plus 5. So for plus, we have already discussed that for signed representation, the MSB bit represents sign of the number. MSB bit represents sign of the number. So it is plus 5. So we will add the sign bit or the MSB bit, and that will be 0. This is called our sign bit, or this is called our MSB bit. We can say it as a sign bit or MSB bit. Sign bit or MSB bit. And as it is 0, it means it is denoting a positive number. and as it is 0, it means it is denoting a positive number. Now the rest bits denote my magnitude part. Rest bit will denote my magnitude part. MSB bit will give us the information whether my number is positive or negative, and the remaining bit will give the magnitude. Now, and the remaining bit will give the magnitude. Now, suppose we have to represent -5. Now suppose we have to represent -5 in signed representation, and that too in 7-bit format, and that too in 7-bit format. So how we can do it? Again, first we have to convert decimal 5 into binary 5. So the magnitude portion will be same. The magnitude portion will be same as it is here. Magnitude portion will be same as it is here. This is my magnitude portion. The change which we will get will be in our MSB part. Will be our MSB part. Now it is negative. That is, we have to add a sign bit. That is, we have to add a sign bit or MSB bit as 1. Because in signed magnitude representation for a negative number, MSB has to be 1. So we will add one more bit 1 here. So we will add one more bit 1 here. So this will be my -5 representation. So this will be my -5 representation. Suppose let us take another example. Suppose we want to represent +7. Suppose we want to represent +7 in sign magnitude representation and in 8-bit format. So first we will convert a decimal 7 into binary 7. So we know the shortcut of this conversion. It will be 111. Then we will add 40. See how many bit we have written. 1, 2, 3, 4, 5, 6, 7. Yes. Now we have to add the 8th bit or the MSB bit or the sign bit. And what will be that bit? That will be 0. Because my number is positive. Similarly, if we want to denote -7, same in signed representation and in 8-bit format. So my magnitude part will be the same. Now only difference will be the sign bit or the MSB bit. It will be 1. Because we are having negative number. So this is how we represent positive and negative numbers in signed representation. So this is how we represent positive and negative numbers in signed representation. Now, coming to the next one, that is one's complement representation. One's complement representation. Now suppose we want to represent +5 in one's complement representation and in 7-bit format. So again, we will first convert decimal 5 into binary 5. So it will be 101, 101. Now we have to represent it. Now we have to represent it in 7-bit. So we will add 4 zeros here. So we will add 4 zeros here. This is my MSB bit. MSB bit is 0. That is, it is denoting that number is positive, and rest is the magnitude portion. Same as the previous one. Same as the previous one. Now where is the twist? The twist is in finding the negative number. Twist is in finding the negative number. That is, suppose we are asked to find one's complement representation of -5, and that too in 7-bit. That too in 7-bit format. How we can write it? How we can write it? Simply take one's complement of it. Simply take one's complement of it. Simply take one's complement of it. What we will get? We will get 1, 1, 1, 1, 0, 1, 0. So this is -5 representation in one's complement form. In one's complement form, having 7-bit. Having 7-bit. So here we can write a statement. Here we can write a statement. In one's complement representation, in one's complement representation, for denoting negative numbers, for denoting negative numbers, first find its positive representation. First find its positive representation, and then take its one's complement, and then take its one's complement. Very easy. See what I told you? +5, representation of +5 in one's complement is same as that of the signed representation. The only difference is in representing the negative part. That is, if we want to represent -5 in one's complement representation, then first we will write +5 in one's complement representation, and then we will take its one's complement, and then we will take its one's complement, and then we will take its one's complement. Now let us take another example. Suppose we want to denote -7. Suppose we want to denote -7 in one's complement representation, in one's complement, in one's complement representation, and format is 8-bit format, and format is 8-bit format. See how we can do it? First we have to find +7. First we have to find +7. So how we can represent it? It will be 111, 3-bit. We have to find it in 8-bit. So we will add 5 zeros here. 1, 2, 3, 4, 5, 6, 7, 8. So this is my +7 representation in one's complement. This is my +7's plus 7 representation in ones complement, and that too in 8-bit format. Now to find minus 7, we will just take its ones complement. So it will be 1 1 1 1 1 0 0 0. This will be my answer. This will be my answer. Fine. Now coming to the third one. That is 2's complement representation. That is 2's complement representation. That is 2's complement representation. Here also the funda is same. Suppose we want to find plus 5 in 2's complement representation in 7-bit format. So it will be same as the previous two. That is 101. We will add 40, 7-bit. Now if we want to find minus 5, same in 7-bit format in 2's complement, then what we will do? We will take its 2's complement. We will simply take its 2's complement. So what we will get? We will first get one's complement 1 1 1 1 0 1 0. Then we will add 1. We will get 1 1 0 1 1 1 1. This will be my minus 5 representation in 2's complement form. Let us take one more example. Suppose we want to represent minus 7 in 2's complement representation, and bit format is 8-bit. So here also first we will find plus 7, so it will be 1 1 1 and 5 0. Then for finding minus 7, we have to take 2's complement of this. So first we will take 1's complement and then we will add 1. So we will get 1 0 0 1 1 1 1 1. This will be my answer. So we can write one statement in 2's complement also, that is in 2's complement representation, for representing negative number, first find its positive equivalent and then take its 2's complement and then take its 2's complement. Fine, easy. So this is the way how we represent positive and negative number in signed representation, in one's complement representation, and in 2's complement representation. Fine. Now let us discuss range. Range of signed magnitude representation. Range of signed magnitude representation. First we will discuss signed First we will discuss signed representation. So suppose n is equal to 3. Suppose n is equal to 3. So what will be my range? My range will be from plus 3, plus 2, plus 1, plus 0, minus 0, minus 1, minus 2, minus 3. How plus 3 is denoted in signed representation? It will be 1, 1, 0. How 2 is denoted? It will be 0, 1, 0. How 1 is denoted? It will be 1, 0, 0. How 0 is represented? It will be 0, 0, 0. Now how minus 0 is represented? If we talk about the magnitude part, it will be same. Only change will be in the MSB bit or the sign bit. Similarly, for minus 1, the magnitude will be same. Only change will be the sign bit. For minus 2, the magnitude part will be same. Only change will be my sign bit. For minus 3, the magnitude part will be same. Only change will be my sign bit. Only change will be my sign bit. Fine. Now suppose n is equal to 4. Suppose n is equal to 4. So what will be my range? So what will be my range? It will be from plus 7, plus 6, plus 5, plus 4, plus 3, plus 2, plus 1, plus 0, minus 0, minus 1, minus 2, minus 3, minus 4, minus 5, minus 6, minus 7. How plus 7 is represented? It will be 1, 1, 1, and my MSB bit will be 0 because it is plus 7. Because it is plus 7. Similarly, how minus 7 will be represented? How minus 7 will be represented? It will be magnitude part will be same. Only change will be my MSB bit, that is 1. Only change will be my MSB bit. Only change will be my MSB bit, and that is 1. This part you can fill on your own. This will be a homework for you. You can fill it on your own. So if I want to conclude, so how I can conclude? Range for n bit signed representation is minus 2 to the power n minus 1 minus 1 to 2 to the power n minus 1 minus 1. See, if I put n is equal to 3, what we will get? We will get minus 3 to plus 3. Same that we have written here. Same that we have written here. Similarly, for n is equal to 4, what will be my range? My range will be minus 7 to plus 7. See, from minus 7 to plus 7. So this is very important for your objective point of view. See, this is very important for your objective point of view. Now see, one more observation from here. Now see, one more observation. See, in signed representation, for plus 0, its representation is 0, 0, 0. For minus 0, its representation is 1, 0, 0. Similarly, if you will write it here, similarly, if you will write it here, you will get 0, 0, 0, 0 and 1, 0, 0, 0. That is in signed representation. We are having two representation for 0. That is in signed representation. We are having two representation for 0. This is an disadvantage of signed representation. This is an disadvantage of signed representation because for same number, we are having two representation. Because for same number we are having two representation. So we can write it here, disadvantage. We can write 0 is having two representation. 0 is having two representation. Now, coming to one's complement. Representation. If we talk about a range of one's complement representation, then suppose here again n is equal to 3, then what will be its range? Its range will be from plus 3, plus 2, plus 1, plus 0, minus 0, minus 1, minus 2, minus 3. How we can write plus 3? We can write it as 1, 1, 0, plus 2, 0, 1, 0, plus 1, 1, 0, 0, plus 0, 0, 0, 0. Now how we can write minus 0? Take its ones complement. Take its ones complement, that is 1, 1, 1. Now for minus 1, take ones complement of plus 1, that is 1, 1, 0, 1, 1, 0. Now for minus 2, take ones complement of plus 2, that is 1, 0, 1, that is 1, 0, 1. Now for minus 3, take ones complement of this plus 3, that is 1, 0, 0. Fine. Similarly, for n is equal to 4, we will get plus 7, plus 6, plus 0, minus 0, then minus 6, minus 7. This you can complete it on your own as a homework. So here also we can conclude that range for one's complement representation for n bit is minus 2 to the power n minus 1 minus 1 to 2 to the power n minus 1 minus 1. That is, for n is equal to 3, we will get minus 3 to plus 3. For n is equal to 4, we will get minus 7 to plus 7, and so on. Here also you can observe the same disadvantage which we observed in signed representation, that is for 0 we are having two representation. That is for 0 we are having two representation. So here also we can write as a disadvantage. Here also we can write as disadvantage, that is there is two representation. There is two representation for 0. For 0. Fine. Now coming to the third one, that is 2's complement representation. That is range of 2's complement representation. Now suppose for n is equal to 3. For n is equal to 3. So for n is equal to 3, it will be plus 3 plus 2 plus 1 plus 0 minus 0 minus 1 minus 2 minus 3. So how we can represent plus 3? It will be 1 1 0 plus 2 0 1 0 plus 1 1 0 0 plus 0 0 0 0. Fine. Now how we can write minus 0? Take its 2's complement. Take its 2's complement. If we will take its 2's complement, what we will get? We will get 0 0 0. Now similarly for minus 1, take its 2's complement. It will be 1 1 1. For minus 2, take its 2's complement. What it will be? It will be 1 0 1 1 1 1 0 1 1 0. Similarly for minus 3, take its 2's complement. That is, it will come out to be 1 0 1 1 0 1. Now see an interesting difference in 2's complement representation as compared to the previous one. See, here the disadvantage which we were discussing in the previous two, it is eliminated here. Here we can see that we have only one representation for 0. We are having only one representation for 0, that is plus 0 is also 0 0 0 and minus 0 is also 0 0 0. Whereas in earlier cases we were having two different representations for 0. Two different representation for 0. So we can first write it here, the advantage in 2's complement. What is the advantage? There is only one representation. There is only one representation for plus 0 and minus 0. Okay, this is the advantage. Now coming back to it. So see how many combinations are present here. See 1 2 3 4. These two are same, so we will not count it. So 5, 6, 7. So total 7 combinations are there. That is still one combination is remaining. That is still one combination is remaining, because we very well know that for n is equal to 3, how many combinations we will get? We will get 8 combinations. But here we are having only 7 combinations. That is one combination is remaining. That is one combination is remaining. So what is that one combination? So what is that one combination? See, 000 is present. Yes, it is present here. 001 is present. Yes, it is present. 010 is present. Yes. 011 is present. Yes. 100. No. 100 is not present. 101. Yes. 110. Yes. 111. Yes. So which combination is not present? 100 is not present. 100 is not present. See, in 2's complement, what is denoted by 100? In 2's complement, so in 2's complement, what is represented by 100? See, first we will check the MSB bit. It is 1. That is, this number will be negative, because we are dealing in 2's complement representation. So first we will check the MSB bit. MSB bit is 1. That is, it is in 2's complement. That is, it is in negative. That is, it is a negative number. That is, it is a negative number. Now to find the actual value of this number, we will take its 2's complement. So what will be its 2's complement? Its 2's complement will be 0, 0, 1. Now take its decimal equivalent. That is, 2 to the power 2 we will get here. 2 to the power 2. That is 4. That is minus 4. That is 100 represents minus 4. That is 100 represents minus 4. That is, here we can add one more combination, minus 4. That is, here we can add one more combination, that is minus 4. Now see, what will be my range now? Now see, what will be my range? Range in 2's complement representation. Range in 2's complement representation for n bits. It will be minus 2 to the power n minus 1 minus 1 2. 2 to the power n minus 1. This is very important. See, minus 1 is not present here. This is the very important difference between 2's range in 2's complement representation and range in 1's complement and signed representation. Very important for your objective point of view. Suppose n is equal to 3, then what will be my range? My range will be minus 3. No, sorry. I just did the reverse of it. Now range in 2's complement representation for n bit will be minus 2 to the power n minus 1. 2 to the power n minus 1 minus 1. Minus 1 will be present here in the positive part, and minus 1 will not be present in the negative part. So for n is equal to 3, what will be our answer? Our range will be from minus 4 to plus 3. See, plus 3 minus 4. This is my range. This is my range. Similarly, for n is equal to 4, what we will get? My range will be 2 to the power 4, that is minus, what we will get here? What we will get here? We will get here 2 to the power 4, 4 minus 1 to the power 8, that is minus 8 to, here we will get plus 7, minus 8 to plus 7. So this was all about the range of this 3. This was all about the range of this 3. Now, after discussing all these concepts, let us take an interesting question. Let us take an interesting question. Suppose we are given a binary number. Suppose we are given a binary number like this. Suppose we are given a binary number like this, and we are asked to find decimal equivalent. We are asked to find its decimal equivalent first in signed representation. First in signed representation. Suppose we are given a binary number 11011, and we are asked to find its decimal equivalent in signed representation. In signed representation. So see how we will proceed. First we will check the MSB. First we will check the MSB. MSB is 1, that is this number is going to be negative. That is this number is going to be negative. Now we will see the magnitude portion. Now we will see the magnitude portion. So what will be its magnitude? Its magnitude will be 2 to the power 0, 2 to the power 1, 2 to the power 3. That is 8 plus 2 plus 1. My answer will be minus 11. My answer will be minus 11. Fine. I hope you understood it. Now, suppose we are given the same question. Suppose we are given the same question. We have to find decimal equivalent, but this time we have to find it in one's complement representation. But now we have to find it in one's complement representation. One's complement representation. So how we can proceed? Again, first we will check the MSB bit. MSB bit is 1. That is my number is negative. That is my number is negative. And it is in one's complement form. And it is in one's complement form. So to find its actual value, we have to take one's complement of this entire binary bits. So to find its actual value, actual decimal value, we will take one's complement of this entire binary part. So what will be one's complement? It will be 00100. Now, what will be its value? 4. Minus 4. Minus 4 will be my answer. Minus 4 will be my answer. I hope this is clear. Now coming to the third one, that is If again we are given the same binary bits, we are asked to find decimal equivalent, but in 2's complement, representation. So how we can do it? Again we will check the MSB. MSB is 1, that is my answer is negative. Now it is in 2's complement form. So to find its actual value, we have to take its 2's complement. So take its 2's complement, 0, 0, 1, 0, 0, add 1. We will have 0, 0, 1, 0, 1. Now take its decimal equivalent. It will be 2 to the power 0, 2 to the power 2. That is minus 5. That is minus 5. So this is the way that how you should proceed if you are given such question. That is, if you are given some binary forms and you are asked to find decimal equivalent in signed magnitude representation, that is in signed representation, 1's complement representation, 2's complement representation, then this way you have to proceed. You can see that we are getting different answers in different representation. We are getting different answers in different representation. Very important concepts we have discussed, and an important interesting question also we have discussed. So I hope that now all your doubt must be over. Now coming to next topic, that is 1's complement arithmetic. That is 1's complement arithmetic. We very well know that complement method is used for subtraction. Complement method is used for subtraction. So before taking some questions, we will write a few statements, and then through questions we will look into the insight of these statements. So first statement, in 1's complement subtraction, add 1's complement of subtrahend. Subtrahend means number which is to be subtracted. To the median. Median means number from which subtrahend is to be subtracted. Coming to next statement. If there is carry out bring the carry. Just look into the statement. Don't apply much brain to it. If you are able to understand it, well and good. And if you are not able to understand it, then also there is no problem. We are shortly going to take an example, and then everything will be clear. But before that, I want to write some statements regarding ones complement arithmetic. Bring the carry around and add it to LSB. LSB means least significant bit. Least significant bit. This is called and around carry. This is called and around carry. Come into next statement. Look at the sign bit. Look at the sign bit. What is the sign bit? MSB, most significant bit. If this is 0, whose sign bit which we are checking? The result which we have got after addition. Um, that for that sign bit is to be checked. If this is 0, then result is positive and it is in true binary and it is in true binary. Come into next statement. If MSB is 1, if MSB is 1, whether there was carry or not, whether there was carry or not. Then result is negative. Then result is negative and it is in one's complement form and it is in one's complement form. Come into the last statement. To find true result, take its one's complement. Take its one's complement. Fine. Now see. What's my first statement is saying that we are performing subtraction in one's complement. We are performing subtraction in one's complement. Then there we will have two things, subtrahend and miniand. Subtrahend and miniand. Suppose we want to perform A minus B operation. Suppose we want to perform A minus B operation, then A is my maniand and B is my subtrahend. So what we will do, we will perform it in this way: A plus minus B. That is, we will first take one's complement of subtrahend and then we will add it to the maniand. First we will take one's complement of subtrahend and then we will add it to maniand. Fine. Now after adding it, if we get a carry, after adding it, if we get a carry, then we have to bring that carry, and add it to LSB. Then we have to bring that carry and add it to LSB. Now after performing it, we will check our result. If the MSB of result is 0, then my result is positive and it is in true binary. If MSB is 1, whether there was carry or there was no carry, then result is negative and it is in one's complement form. Then result is negative, and it is in one's complement form. So let us take an and if it is and if the MSB is 1, then then to find the true result in binary, we have to take again its one's complement. Now let us take an example. Subtract 14 from 25 using 8-bit one's complement arithmetic. So what we have to perform? We have to perform this operation. We know what will be its result. Its result will be 11. But this thing we have to perform using one's complement arithmetic. So how we can perform it? First we will write 25 into binary. So first we will do decimal to binary conversion. I am taking the long cut. I am not going for shortcut. So it is 1, 1, 0, 0, 1. So see how many bits are there? 5 bits. But we want answer in 8-bit. So we will add 30 here. Now, how we can write minus 14? So for minus 14, first we have to convert 14 into binary. And then we have to take its ones complement. This all we have already discussed. So converting it to binary. So 1110. 1110. No, I will not write it here. I will write it here. 1110. but we want it in 8-bit, so we will add 4 zeros here. Now this is plus 14. Now this is plus 14. Now we have to take minus 14. What will be minus 14? Take its ones complement. Take its ones complement. This is minus 14. This is minus 14. This is minus 14. Now we have to add it. Now we have to add it. Now we have to add it. See what we will get? 0, 1, 0, 1, 0, 0, 0, 0, carry 1, carry 1. So what we discussed? We have to bring this carry at LSB. We have to bring this carry at LSB and add it. So what we will get? We will get 1, 1, 0, 1, 0, 0, 0, 0. This is my result. This is my result. Now what I have to do? I have to check the MSB. My MSB is positive. My MSB is positive. That is, my MSB is 0. My MSB is 0. My MSB is 0. That is, my result is positive and it is in true binary form. My result is positive. My result is positive. My result is positive and it is in true binary form. So now I can write it. So now I can write the final result. So it will be 2 to the power 0, 1, 3. Means 8 plus 2 plus 1, that is plus 11. This is the result which we have got from ones complement arithmetic, and this is the same result as this. So this is how we perform subtraction using ones complement method. Using ones complement method. Now let us take one more example. Now let us take one more example. Add minus 25 to plus 14 using 8-bit ones complement method. Using 8-bit ones complement method. So what we have to find? We have to find this. What answer we will get here? We will get answer as minus 11. We will get answer as minus 11. Now see how we can perform it using ones complement method. So first we will convert 14 into binary. First we will convert 14 into binary. I am taking the long cut. You can take shortcut also, which I have taught you. So it will come out to be 1, 1, 1, 0. but we have to find answer in 8 bit. So we will add 4 zeros here. So we will add 40 here. Right. Let me write it like this way. 0 0 0 0 1 1 1 0. Now, how to find minus 25? First, we will convert 25 into binary. Then we will take 1's complement of it to find minus 25. So, 25. So, we will get 1 1 0 0 1. 5 bit, we have to find answer in 8 bit. We will add 30. This is plus 25. This is plus 25. We have to find minus 25. Take its 1's complement. This is minus 25. Now put it here. Now add it. Now add it. What we will get? 0, 0, carry 1, 1, 1, 0, carry 1, 0, 1, 1. 1 1 0, carry 1 1 1 1 1. There is no carry out. There is no carry out. So there is no need of bringing any carry out bit at LSB. Now we will check the result. Now we will check MSB of result. MSB of result is 1. MSB of result is 1. That is, our answer is negative. That is, result is negative. And it is in 1's complement form. Result is a negative and it is in 1's complement form. So to find its true value, we have to take its complement, 1's complement. We have to take its 1's complement. So this is my 1's complement. Now this is my result, actual result. So what will be it? 0, 1, 3. That is minus 11. This is same as this. So this is how we perform subtraction using 1's complement method. This is how we perform subtraction using 1's complement method. Now, coming to 2's complement arithmetic. So for 2's complement arithmetic, I will do changes here only. I am not going to write it again. I am going to do changes here only. So 2's complement arithmetic. In 2's complement subtraction, add 2's complement of subtrahend to the median. That is, in 1's complement, we were taking 1's complement of subtrahend. Now we will take 2's complement of subtrahend. If there is a carry out, here there will be a difference. Here there will be a difference. If there is a carry out, then ignore the carry. Then ignore the carry. If there is a carry out, ignore the carry. as against in ones complement where we were adding the carry. Now, look at the sign bit MSB. If this is 0, then result is positive and it is in true binary. If MSB is 1, whether there was carry or no carry, then result is negative and it is in 2's complement form. It is in 2's complement form. So now to find a true result, take its 2's complement. To find a true result, take its 2's complement. Now let us solve some example. Suppose we are given a question like this. Subtract 14 from 46 using 8-bit 2's complement method. That is, we have to perform this. What will be our answer? Our answer will be this. But how we can solve it in 2's complement method? So again, first convert 46 into binary. So we will get 1 0 1 1 1 0 1 1 1 0. 6-bit, we want answer in 8-bit, so we will add 2 more 0. Now how we can write minus 14 in 2's complement? First we will write 14 into binary and then we will take its 2's complement. And then we will take its 2's complement. So 14 1 1 1 0, add 4 more 0 to make it in 8-bit. This is plus 14. Now for minus 14, take its 2's complement. Plus 1, that is, it will come out to be 0 1 0 0 1 1 1 1. This will be my minus 14. Now we have to add it. What we will get? We will get 0 0 0 0 0 1 0 0 carry 1. But in 2's complement, we will ignore this carry. And this is my result. Now I will check the MSB bit. MSB bit is 0. That is, my result is positive and it is in true binary form. So we will convert it into decimal. So 0 1 2 3 4 5 2 to the power 5. It is coming out to be plus 32. And this is same as this. So this is how we perform subtraction using 2's complement method. Now take one more example. Add minus 75 to plus 26 using 8-bit two's complement method. So what we have to perform? We have to perform 26 minus 75. It will be 1. Minus no, sorry, I have done a mistake. So we have to perform 26 minus 75. What we will get? We will get minus 49. But we have to perform it in 2's complement form. So first we will convert 26 into binary. One, one, 0, 1, 0. 5-bit add 3, 0. Now, how we can write minus 75? First, we will find binary equivalent of 75 and then we will take its 2's complement. So 1, 0, 0, 1, 0, 1, 1. Add one more 0. This is plus 75. How we can write minus 75? Take its 2's complement. Take its 2's complement. So it will be 1, 0, 1, 1, 0, 1, 0, 1. Now put it here. 1, 0, 1, 1, 0, 1, 0, 1. Now add it. Now add it. What we will get? We will get 1, 1, 1, 1, 0, 0, 1, 1. No carry. Anyhow, carry doesn't make any changes in 2's complement method. Now we will check the MSB bit. MSB bit is 1. That is, my answer is going to be negative. And this result is in 2's complement form. So first we have to find its 2's complement to bring it in true binary form. So its 2's complement will be 0, 0, 1, 1, 0, 0, 0, 1. Now convert it into decimal. 0, 1, 2, 3, 4, 5. 32 plus 16 plus 1 minus 49. Minus 49. This is same. This is same. So this was all about ones and twos complement arithmetic. This was all about ones and twos complement arithmetic. I hope that it is now clear to you that how we use the carry about in case of ones and twos complement, and how by check-in from the MSB bit we decide whether the number is positive or negative, and if it is negative then again how we have to convert it in ones complement and twos complement respectively to get the desired result. Now अब चलो हम लोग अपने नेक्स्ट टॉपिक में आते हैं, दैट इज ओवरफ्लो कंडीशन। बहुत इंटरेस्टिंग टॉपिक है, तो चलो इसे हम लोग देखते हैं। तो देखो, सबसे पहले हम लोग कुछ चीज़ रिवाइज कर लेते हैं, ठीक है। देखो, हम लोगों ने ये डिस्कस किया था कि अगर मेरे पास एक अनसाइंड मैग्नीट्यूड रिप्रेजेंटेशन है तो हम लोगों को रेंज मिलता है 0 to 2 to the power n minus 1, where n is number of bits। इसी तरह अगर हम लोगों के पास एक साइंड मैग्नीट्यूड रिप्रेजेंटेशन है तो मेरा रेंज क्या होता है? मेरा रेंज होता है -2 to the power n minus 1 -1 to 2 to the power n minus 1 -1। ये भी हम लोगों ने देखा था। इसी तरह अगर हम लोगों के पास वंस कॉम्प्लीमेंट रिप्रेजेंटेशन है तो मेरा रेंज होगा सेम -2 to the power n minus 1 -1 to 2 to the power n minus 1 -1। इसी तरह अगर हम लोगों के पास टूज कॉम्प्लीमेंट रिप्रेजेंटेशन है तो हम लोग का रेंज क्या होगा? -2 to the power n minus 1 to 2 to the power n minus 1 -1, ठीक है। सो आई होप कि ये जो मेरा रिप्रेजेंटेशन है एंड रेंज है ये आप रिकॉल कर पा रहे हैं, ठीक है। अब आप बोलोगे कि सर ये ओवरफ्लो कंडीशन में ये हम लोग रिप्रेजेंटेशन एंड रेंज में कहाँ आ गए? तो देखो, ओवरफ्लो कंडीशन में हम लोग रिप्रेजेंटेशन एंड रेंज में इसलिए आ गए क्योंकि मेरा जो ये डिफरेंट रिप्रेजेंटेशन है एंड डिफरेंट रेंज है। बेसिकली मेरा जो ये रेंज है ये एक बहुत इम्पॉर्टेंट रोल अदा करता है कि मेरा ओवरफ्लो होगा कि नहीं। ये जो रेंज है मेरा फॉर डिफरेंट रिप्रेजेंटेशन, यही मेरा जज करेगा कि मेरा किसी भी कंडीशन में ओवरफ्लो करता है, होगा या नहीं होगा, ठीक है। तो आई होप कि ये जो मेरा रिप्रेजेंटेशन एंड रेंज है ये तो आप रिकॉल कर पा रहे हो, ठीक है। चलो अब हम लोग कुछ एग्जांपल्स देखते हैं, उसके बाद हम लोग अपने ओवरफ्लो कंडीशन को समझेंगे, ठीक है। देखो, सबसे पहले मान लो हम लोगों के पास नंबर ऑफ बिट्स है 4, ठीक है। नंबर ऑफ बिट्स मेरा है 4। रिप्रेजेंटेशन आप ले लो, मान लो हम लोग टूज रिप्रेजेंटेशन में काम कर रहे हैं। टूज कॉम्प्लीमेंट रिप्रेजेंटेशन में हम लोग काम कर रहे हैं। तो हम लोग को पता है कि अगर मेरा जो n है वो 4 है और हम लोग टूज कॉम्प्लीमेंट रिप्रेजेंटेशन में काम कर रहे हैं, तो देखो इस केस में मेरा रेंज क्या होगा? इस केस में मेरा रेंज हो जाएगा -8 से 7, ठीक है। ये हम लोगों ने यहाँ पे देखा था। टूज कॉम्प्लीमेंट रिप्रेजेंटेशन में मेरा रेंज होता है -2 to the power n minus 1 से 2 to the power n minus 1 -1। यहाँ पे n हम लोग का इस केस में हम लोग 4 ले रहे हैं, ठीक है। तो ये आ गया मेरा रेंज, ठीक है। अब चलो मान लो मेरे पास एक डेसिमल नंबर है, मान लो मेरे पास एक डेसिमल नंबर है +4, ठीक है। तो देखो इस डेसिमल नंबर का अगर हम लोग बाइनरी इक्विवेलेंट लिए तो क्या आ जाएगा? ये आ जाएगा 0 1 0 0। इसी तरह मान लो हम लोग के पास एक डेसिमल नंबर है +5। इस +5 का अगर हम लोग बाइनरी इक्विवेलेंट लिए तो ये आ जाएगा मेरा 0 1 0, ठीक है। अब चलो हम लोग इसको ऐड कर देते हैं। अब हम लोग इसको ऐड कर देते हैं, ठीक है। हम लोग ऐड कर रहे हैं इसे टूज कॉम्प्लीमेंट रिप्रेजेंटेशन में। तो ये क्या आ जाएगा? 1 0 1 1 0, यहाँ पे देखो मेरा कैरी आ रहा है 1, यहाँ कैरी आ रहा है 1, ठीक है। और ये यहाँ पे आएगा मेरा रिजल्ट 1, ठीक है, मेरा यहाँ पे रिजल्ट आ गया 1, ठीक है। ठीक है, अब यहाँ पे हम लोग एक कैरी आउट ले लेते हैं 0। अभी हम लोग बस इसको ले लिए, अभी आप इस पे फोकस मत करो, हम लोग इसको बाद में फोकस करेंगे। तो यहाँ पे देखो क्या है, ये मेरा कैरी इन है, ठीक है 1, ये मेरा कैरी आउट है 0, ठीक है। अब चलो ये हम लोगों ने +4 का जो बाइनरी रिप्रेजेंटेशन है वो ले लिए, +5 का बाइनरी रिप्रेजेंटेशन ले लिए, इसको हम लोग प्लस कर दिए, तो हम लोग को रिज़ल्ट आ गया, 1 0 0 1। अब बताओ ये जो 1 0 0 1 आया, ये जो आपका 1 0 0 1 आया, टूज कॉम्प्लीमेंट रिप्रेजेंटेशन का बात कर रहे हैं, तो ये देखो 1 0 0 1 हम लोग को क्या दे देगा, जो मेरा ये साइन बिट है वो 1 है, इट मीन्स कि ये नेगेटिव आ गया, ठीक है, ये मेरा नेगेटिव आ गया। अब मैग्नीट्यूड के लिए हम लोग इसका टूज कॉम्प्लीमेंट लेंगे, इट मीन्स इसका अगर हम लोग टूज कॉम्प्लीमेंट ले लिए तो ये आ जाएगा 0 1 1 0 +1, तो 0 1 1 1, इट मीन्स कि ये आ गया 2 to the power 0 2 to the power 1 2 to the power 2 4 2 6 7 -7 ये आ गया आपका, ठीक है, ठीक है। अब आप बताओ कि क्या ये आपका रिज़ल्ट सही है, अब आप बताओ कि क्या ये आपका रिज़ल्ट सही है। तो आप बोलोगे कि सर ये रिज़ल्ट तो सही नहीं है। देखो हम लोगों ने लिया था +4, हम लोग लिए +5, इन दोनों को हम लोग ऐड कर रहे हैं, इन दोनों को हम लोग ऐड कर रहे हैं, तो मेरा एक्सपेक्टेशन था +9 आने का, मेरा एक्सपेक्टेशन था +9 आने का, लेकिन आ गया मेरा -7, आ गया मेरा -7। ये ऐसा क्यों हो गया? आप बोलोगे कि सर ये ऐसा क्यों हो गया? देखो ये ऐसा इसलिए हो गया क्योंकि मेरा देखो जो टूज कॉम्प्लीमेंट का रेंज है, मेरा जो टूज कॉम्प्लीमेंट का रेंज है फॉर n = 4 बिट, वो रेंज है मेरा -8 से 7, वो रेंज है मेरा -8 से 7। मेरा जो रिज़ल्ट आ रहा है वो आ रहा है +9, तो मेरा +9 तो मेरा इस रेंज के बाहर आ गया, मेरा जो +9 है वो तो देखो मेरा इस रेंज के बाहर आ गया, इसीलिए देखो हम लोग को इनकरेक्ट रिज़ल्ट मिल रहा है। देखो अगर यहाँ पे देखो हम लोगों ने ये 4 बिट लिया था, तो ये 4 बिट मेरा -7 आ गया, ठीक है। अगर मान लो हम लोग के पास 5 बिट का ऑप्शन रहता, अगर मेरे पास 5 बिट लेने का प्रोविज़न रहता, अगर मेरे पास 5 बिट लेने का प्रोविज़न रहता, तो हम लोग क्या करते, देखो मेरा +4 है +5 है, मीन्स मेरा जो रिज़ल्ट है वो तो पॉजिटिव आना चाहिए, इट मीन्स कि देखो मेरा आया 1 0 0 1, लेकिन +4 +5 रिज़ल्ट आएगा मेरा पॉजिटिव, तो यहाँ पे हम लोग एक 0 बिट को ऐड करते हैं, ठीक है। अब अगर हम लोग यहाँ पे 0 बिट को ऐड कर दिए, तो अब आप यहाँ पे रिज़ल्ट निकालो, तो देखो अब आपका ये रिज़ल्ट आ जाएगा +9, ये मेरा बिल्कुल सही रिज़ल्ट है। ये सही रिज़ल्ट क्यों है? क्योंकि यहाँ पे हम लोगों ने नंबर ऑफ बिट्स 5 लिया, यहाँ पे हम लोगों ने नंबर ऑफ बिट्स 5 लिया, और नंबर ऑफ बिट्स अगर हम लोग 5 ले रहे हैं, तो उस केस में मेरा टूज कॉम्प्लीमेंट का जो रेंज है, उस केस में मेरा टूज कॉम्प्लीमेंट का जो रेंज है वो क्या आ जाएगा मेरा, वो आ जाएगा मेरा -16, वो आ जाएगा मेरा -16 से 15 तक, और मेरा जो +9 है वो मेरे इस रेंज में लाई कर रहा है, इसलिए हम लोगों को बिल्कुल सही रिज़ल्ट मिल रहा है जब हम लोग n = 5 बिट लिए। लेकिन यहाँ पे क्या हो रहा है, यहाँ पे देखो हम लोग का जो n = 4 बिट है, ठीक है, 4 बिट में जो हम लोगों को रिज़ल्ट आ रहा है वो मेरा आउट ऑफ रेंज आ रहा है, इसलिए हम लोगों को इनकरेक्ट रिज़ल्ट मिल रहा है, ठीक है। और यही मेरा कंडीशन है ओवरफ्लो का, यही मेरा कंडीशन है ओवरफ्लो का। क्या कंडीशन है कि अगर हम लोग दो पॉजिटिव नंबर को ऐड किए, अगर हम लोग दो पॉजिटिव नंबर को ऐड किए और मेरा जो रिज़ल्ट है वो आउट ऑफ रेंज चला जाता है, मेरा जो रिज़ल्ट है वो आउट ऑफ रेंज चला जाता है, जैसे कि यहाँ पे +9 है, ये रिज़ल्ट मेरा आउट ऑफ रेंज है -8 से 7 का, तो उस केस में मेरा ओवरफ्लो कंडीशन एग्जिस्ट करेगा। आई होप दिस इज़ क्लियर टू यू। चलो एक और एग्जांपल लेते हैं। अब चलो फिर से वही ले लेते हैं। n है मेरा 4 बिट, फिर से हम लोग अपना 2's कॉम्प्लीमेंट ही लेकर चलते हैं, 2's कॉम्प्लीमेंट रिप्रेजेंटेशन। तो n = 4 बिट है, तो मेरा रेंज क्या आ जाएगा, मेरा रेंज आ जाएगा -8 से 7, मेरा रेंज आ गया -8 से 7, ठीक है। अब चलो हम लोग एक एग्जांपल लेते हैं, इस बार हम लोग ले लेते हैं +4, इसका बाइनरी इक्विवेलेंट क्या हो गया 0 1 0 0। अब ले लेते हैं +3, इसका बाइनरी इक्विवेलेंट क्या हो गया 0 0 1 1। अब इसको आप ऐड कर दो, अब इसको आप ऐड कर दो, तो हम लोग को क्या मिल जाएगा 1 1 1 0। यहाँ देखो अगर हम लोग कैरी इन का बात करें तो देखो कैरी इन मेरा 0 है, अगर हम लोग कैरी आउट का बात करें तो कैरी आउट 0। आप बोलोगे कि सर ये हम लोग कैरी इन कैरी आउट क्यों ले रहे हैं, ज़बरदस्ती क्यों ले रहे हैं, अगर होता तो फिर तो सही था, ज़बरदस्ती क्यों ले रहे हैं, तो देखो ज़बरदस्ती क्यों ले रहे हैं, क्योंकि कैरी इन एंड कैरी आउट से हम लोग ओवरफ्लो कंडीशंस को कंक्लूड करेंगे, वो अभी हम लोग आगे चल के करेंगे। फॉर द टाइम बिन आप बस देखते जाओ। तो ठीक है, ये मेरा रिज़ल्ट आ गया, मेरा फाइनल रिज़ल्ट क्या आ गया, मेरा फाइनल रिज़ल्ट आ गया 0 1 1 1, कैरी इन 0 कैरी आउट 0, ठीक है। अब देखो मेरा यहाँ पे MSB 0 है, इट मीन्स कि नंबर पॉजिटिव है, और अगर हम लोग इसको कन्वर्ट करें तो ये हम लोग को मिल जाएगा +7। अब देखो मेरा एक्सपेक्टेशन क्या था, +4 था, इसको ऐड कर रहे थे +3 से, तो +7 आना चाहिए था। मेरा एक्सपेक्टेशन था +7, यहाँ से भी हम लोग को +7 मिला। तो इस बार हम लोग को दिक्कत क्यों नहीं आया, इस बार देखो हम लोग को दिक्कत इसलिए नहीं आया क्योंकि देखो मेरा जो +4 है +3 है, इसको ऐड करके हम लोग को +7 जो रिज़ल्ट मिला, ये देखो +7 मेरे इस रेंज का पार्ट है, ये देखो मेरे इस रेंज के बाहर नहीं जा रहा है, रेंज के बाहर नहीं जा रहा है, इट मीन्स कि मेरा ओवरफ्लो नहीं हो रहा है, रेंज के बाहर नहीं जा रहा है, इट मीन्स कि मेरा ओवरफ्लो कंडीशन नहीं हो रहा है, इसलिए यहाँ पे हम लोग को बिल्कुल सही रिज़ल्ट मिल रहा है, ठीक है। चलो एक और एग्जांपल ले लेते हैं। अब चलो एक और एग्जांपल लेते हैं, फिर से n मेरा 4 बिट है, 2's कॉम्प्लीमेंट रिप्रेजेंटेशन में है, रेंज मेरा -8 से 7 आ जाएगा, ठीक है। अब चलो हम लोग अपना एक नंबर ले लेते हैं, इस बार लेते हैं -4। तो -4 को हम लोग कैसे रिप्रेजेंट करेंगे 1 1 0 0, ठीक है। इसको हम लोग रिप्रेजेंट करेंगे 1 1 0 0। अब ले लेते हैं -5, -5 को हम लोग रिप्रेजेंट करेंगे एज 1 0 1 1। ठीक है, चलो सही है। अब चलो हम लोग इसे अब ऐड करते हैं, इसे हम लोग ऐड करते हैं, तो हम लोग को क्या मिल जाएगा 1 1 1 1 1 0 कैरी आउट 1। यहाँ पे कैरी आउट 1 हो रहा है, कैरी इन कितना था 0, कैरी इन 0 है, कैरी आउट 1, ठीक है। अब देखो हम लोग को रिज़ल्ट क्या मिला, हम लोग को रिज़ल्ट मिला 0 1 1 1। ये क्या रिप्रेजेंट करेगा, ये रिप्रेजेंट करता है +7। तो अब देखो यहाँ पे हम लोग क्या कर रहे थे, -4 को ऐड कर रहे थे -5 से, तो हम लोग का एक्सपेक्टेशन था कि -9 मिले, लेकिन मिल रहा है +7, तो ये तो बिल्कुल गलत है। अब ये ऐसा हो क्यों गया? ये ऐसा इसलिए हो गया क्योंकि देखो, जब हम लोगों ने यहाँ पे 2 नेगेटिव नंबर को ऐड कर दिया, तो मेरा जो एंड रिज़ल्ट मिला वो देखो फिर से मेरा इस रेंज के बाहर चला गया। इट मीन्स कि मेरा अब ओवरफ्लो कंडीशन हो रहा है, और इसी ओवरफ्लो कंडीशंस के वजह से हम लोगों को यहाँ पे गलत रिज़ल्ट मिल रहा है। अब सही रिज़ल्ट मिलने के लिए हम लोगों को क्या करना पड़ेगा? अब हम लोग को अपना बिट्स बढ़ाना पड़ेगा। मान लो अब हम लोग अपना नंबर ऑफ बिट्स ले लेते हैं 5। अगर हम लोग अपना नंबर ऑफ बिट्स ले लेंगे 5, तो उस केस में हम लोग क्या करेंगे? देखो 0 1 1 1 मिला, यहाँ पे हम लोग एक और ये जो कैरी आउट आया था 1 ऐड कर दिए। तो अब देखो ये हम लोग को सही रिज़ल्ट देगा, ये हम लोग को -9 देगा। तो यहाँ से हम लोग एक चीज़ और क्या कंक्लूड कर सकते हैं? देखो फर्स्ट में हम लोगों ने क्या कंक्लूड किया था कि अगर हम लोग 2 पॉजिटिव नंबर को ऐड करते हैं तो वहाँ पे हम लोग का ओवरफ्लो कंडीशन हो सकता है। देखो यहाँ पे देखो हम लोगों ने 2 पॉजिटिव नंबर को ऐड किया, जो ओवरऑल रिजल्ट था वो रेंज के बाहर गया, तो ओवरफ्लो कंडीशन बना। सेकंड केस में क्या है? हम लोगों ने 2 पॉजिटिव नंबर को ऐड किया, लेकिन जो एंड रिजल्ट है वो इस रेंज के अंदर है, तो ओवरफ्लो कंडीशन नहीं बना। अब इसी तरह तीसरा क्या है? अगर हम लोग 2 निगेटिव नंबर को ऐड कर रहे हैं और मेरा एंड रिजल्ट रेंज के बाहर जा रहा है, तो मेरा ओवरफ्लो कंडीशन बनेगा। ठीक है, अब चलो एक लास्ट एग्जाम्पल ले लेते हैं, उससे आपको कंप्लीट क्लैरिटी मिल जाएगा। अब चलो इस बार हम लोग सेम वही ले लेते हैं, 4 बिट 2's कॉम्प्लीमेंट रेंज पता ही है। अब हम लोग लेते हैं -4। -4 को आप रिप्रेजेंट करोगे 1 1 0 0। अब ले लो -3। -3 को आप रिप्रेजेंट करोगे 1 1 0 1। ठीक है, अब देखो इसको अगर हम लोग ऐड किए तो ये आ गया 1 0 1 1 0। यहाँ पे देखो आपका एक कैरी इन आएगा। ठीक है, 1 1 0 1, और यहाँ पे आपका कैरी आउट आएगा, ये आपका कैरी आउट आ गया। ठीक है, अब देखो हम लोग को रिजल्ट क्या मिला? 1 0 0 1। ये क्या रिप्रेजेंट कर रहा है? ये रिप्रेजेंट -7 कर रहा है। तो देखो मेरा एक्सपेक्टेशन क्या था कि -4 -3 को ऐड करें तो -7 आया, और यहाँ पर भी हम लोग को -7 मिल रहा है। तो यहाँ पे मेरा एक्सपेक्टेशन मीट हो रहा है। क्यों? क्योंकि -4 -3 को जब हम लोग ऐड कर रहे हैं तो मेरा जो एंड रिजल्ट आ रहा है वो इस रेंज के अंदर आ रहा है, इसलिए मेरा कोई ओवरफ्लो कंडीशन हो नहीं रहा है, जिसके वजह से हम लोग को यहाँ पे आंसर का मिसमैच नहीं मिल रहा है। ठीक है, तो अब देखो हम लोग चीज़ों को कंक्लूड कर सकते हैं। पहला कंक्लूजन क्या है कि अगर हम लोग 2 पॉजिटिव नंबर को ऐड करते हैं तो आप बताओ क्या हम लोग को हमेशा ओवरफ्लो मिलेगा या नहीं मिलेगा? तो आप बोलोगे कि अगर हम लोग 2 पॉजिटिव नंबर को ऐड करते हैं तो ज़रूरी नहीं है कि हम लोग को हमेशा ओवरफ्लो कंडीशन मिले। अगर मेरा एंड रिज़ल्ट रेंज के बाहर जाएगा तो ओवरफ्लो कंडीशन मिलेगा, अगर मेरा एंड रिज़ल्ट रेंज के अंदर रहेगा तो ओवरफ्लो कंडीशन नहीं मिलेगा। सेम हम लोगों ने एग्जाम्पल 1 और 2 में देखा। यहाँ देखो एंड रिज़ल्ट रेंज के बाहर गया, ओवरफ्लो कंडीशन बना, ओवरफ्लो कंडीशन बना। अब यहाँ देखो मेरा एंड रिजल्ट रेंज के बाहर नहीं गया, तो ये मेरा नो ओवरफ्लो कंडीशन बना, ये मेरा नो ओवरफ्लो कंडीशन बना। अब देखो, अब आप ये बताओ, अगर हम लोग 2 निगेटिव नंबर को ऐड करते हैं कि तो क्या हमेशा हम लोग को ओवरफ्लो कंडीशन मिलेगा? तो आप बोलोगे कि हमेशा नहीं मिलेगा। अगर हम लोग 2 नेगेटिव नंबर को ऐड कर रहे हैं और अगर मेरा एंड रिजल्ट रेंज के बाहर जा रहा है तो देखो यहाँ पे मेरा ओवरफ्लो कंडीशन बना। अब इस केस में देखो, अगर हम लोग 2 नेगेटिव नंबर को ऐड कर रहे हैं और मेरा एंड रिजल्ट रेंज के बाहर नहीं जा रहा है तो ये मेरा नो ओवरफ्लो कंडीशन बनेगा। ठीक है, सो आई होप कि आपको ये समझ में आ गया कि ओवरफ्लो कंडीशन होता क्या है और ये कब मिलता है हम लोग को। ठीक है, तो चलो हम लोग अब कुछ स्टेटमेंट लिखते हैं। अब चलो ओवरफ्लो कंडीशन का जो लिटरेचर है वो हम लोग देखते हैं। तो यहाँ पे देखो क्या कह रहा है, when we add 2 positive numbers or 2 negative numbers and if the result is greater than range of the representation, then it results in overflow condition. ये वही कह रहा है कि अगर हम लोग दो पॉजिटिव नंबर को ऐड कर रहे हैं या दो नेगेटिव नंबर को ऐड कर रहे हैं और मेरा जो एंड रिजल्ट है वो मेरे रेंज से बड़ा हो जा रहा है, तो उस समय हम लोग का ओवरफ्लो कंडीशन होगा। फिर ये क्या कह रहा है, when overflow condition occurs, then we need to increase the range of system, by taking carry out as MSB of the result। यही हम लोगों ने देखा भी था कि जैसे देखो फर्स्ट केस में जो हम लोगों को देखो यहाँ पे जब हम लोगों का n=4 बिट में ओवरफ्लो हो रहा था, तो हम लोगों ने फिर अपना n=5 बिट लिए, हम लोगों ने अपने रेंज को बढ़ा लिया, जब रेंज को बढ़ाए तो जाके हम लोग को करेक्ट रिजल्ट मिला। इसी तरह जब हम लोग नेगेटिव पार्ट को ले रहे थे, तो देखो यहाँ पर भी हम लोगों को n=4 में ओवरफ्लो मिल रहा था, तो हम लोगों ने n=5 बिट लिया। दैट मीन्स कि हम लोगों ने अपने रेंज को बढ़ा लिया। ठीक है, वही यहाँ पे ये हम लोग को कह रहा है कि when overflow occurs then we need to increase the range of system by taking carry out as MSB of the result। बेसिकली देखो carry out as MSB of the result क्या कह रहा है कि देखो अगर हम लोग n=5 बिट लिए, तो हम लोगों ने कौन से बिट को ऐड किया, 0 को ऐड किया, और ये 0 है क्या मेरा, देखो ये जो कैरी आउट का बिट है वो है। सेम जब हम लोग नेगेटिव नंबर को लिए, तो देखो यहाँ पे जब हम लोगों ने n=5 बिट लिया, तो हम लोगों ने यहाँ पे एक्स्ट्रा बिट क्या लिया, 1 लिया। ये 1 क्या है मेरा, ये कैरी आउट ऑफ द रिजल्ट। ठीक है, सो आई होप कि जो ओवरफ्लो कंडीशन क्या होता है वो समझ गए, इसका जो स्टेटमेंट है वो समझ गए। अब हम लोग समझते हैं कि ओवरफ्लो कंडीशन से आपको एग्जाम में क्वेश्चन किस तरह से पूछा जाता है। ठीक है, किस फॉर्म में आपसे एग्जाम में क्वेश्चन पूछेंगे, तो चलो वो देख लेते हैं। अब चलो हम लोग देखते हैं कि एग्ज़ाम में आपसे किस तरह से क्वेश्चंस पूछेंगे। तो एग्ज़ाम में आपसे बेसिकली वो क्वेश्चन पूछेंगे हाउ टू चेक ओवरफ्लो कंडीशंस। ठीक है, तो चलो हम लोग देखते हैं हाउ टू चेक ओवरफ्लो कंडीशन। तो देखो इसमें क्या है, देखो पहले स्टेटमेंट देख लेते हैं, फिर उसे समझ लेंगे कि ये क्या कहना चाह रहे हैं। देखो, इफ़ कैरी इन टू द MSB इज़ नॉट इक्वल टू कैरी आउट ऑफ MSB, then we get overflow condition, or if carry out is not equal to MSB then it results in overflow condition। चलो इसे हम लोग एग्जाम्पल से समझते हैं, तब जाके आपको समझ में आएगा। फर्स्ट एग्जाम्पल लेते हैं हम लोग ये वाला। ठीक है, तो देखो आप फोकस करो इस वाले पार्ट में, आपको फोकस करना है इस वाले पार्ट में। ठीक है, देखो यहाँ पे सबसे पहले आप ये बताओ कि मेरा कैरी इन क्या है। देखो ये जो आया ये है मेरा कैरी इन। अब आप बताओ मेरा कैरी आउट क्या है, ये जो आया ये है मेरा कैरी आउट। ठीक है, अब आपका क्या, अब देखो हम लोग का कंडीशन क्या कह रहा है कि मेरा जो कैरी इन है और जो कैरी आउट है, ये अगर आपको डिफरेंट मिल रहा है तो आपका ओवरफ्लो कंडीशन होगा। देखो कैरी इन 1 है, कैरी आउट 0 है, दोनों हम लोग का कैरी इन कैरी आउट डिफरेंट है, तो हम लोग को देखो ओवरफ्लो हो रहा है। अदर वे अराउंड क्या हो सकता था, मान लो आपका कैरी इन 0 होता, कैरी आउट 1 हो जाता, तो उस केस में भी मेरा कैरी इन और कैरी आउट डिफरेंट था, तो हम लोग को ओवरफ्लो कंडीशन मिलता। लेकिन मान लो मेरा कैरी इन एंड कैरी आउट दोनों सेम है, मान लो कैरी इन कैरी आउट दोनों 0 0 है या दोनों 1 1 है, तो उस केस में मेरा ओवरफ्लो कंडीशन नहीं होगा। जैसे कि फॉर एग्जांपल इस केस में देख लो, देखो यहाँ पे देखो मेरा कैरी इन 0 है, मेरा कैरी आउट 0 है, तो मेरा कैरी इन कैरी आउट सेम है, तो देखो मेरा नो ओवरफ्लो कंडीशन। इसी तरह यहाँ देखो मेरा जो कैरी इन है वो 0 है, कैरी आउट 1 है, तो मेरा कैरी इन कैरी आउट डिफरेंट है, तो मेरा ओवरफ्लो कंडीशन हो रहा है। अब यहाँ देख लो मेरा जो कैरी इन है वो 1 है, कैरी आउट मेरा 1 है, तो कैरी इन कैरी आउट मेरा सेम है, तो नो ओवरफ्लो कंडीशन। तो आपको थंब रूल क्या याद रखना है? थंब रूल ये याद कर रखना है कि मेरा जो कैरी इन है, मेरा जो कैरी इन है और मेरा जो कैरी आउट है, ठीक है, अगर वो दोनों नॉट इक्वल है तो मेरा ओवरफ्लो कंडीशन होगा, और अगर दोनों मेरा इक्वल है तो मेरा वो ओवरफ्लो कंडीशन नहीं होगा। इस चीज़ को हम लोग जनरलाइज करके इस तरह से भी लिख सकते हैं, अगर मेरा जो कैरी इन है, कैरी इन एक्सॉर, कैरी इन एक्सॉर कैरी आउट, ये अगर मेरा 1 आ जाता है तो ये होगा मेरा ओवरफ्लो कंडीशन, ये होगा मेरा ओवरफ्लो कंडीशन। और अगर मेरा कैरी इन एक्सॉर कैरी आउट 0 आ जाता है तो ये हो जाता है मेरा नो ओवरफ्लो कंडीशन, ठीक है। देखो एक्सॉर गेट अभी हम लोग पढ़े नहीं है, अभी हम लोग आगे चल के पढ़ेंगे। बेसिकली देखो एक्सॉर का अगर हम लोग ट्रूथ टेबल बनाए ना, तो देखो एक्सॉर का ट्रूथ टेबल आपका इस तरह से बनता है 0 0 0 1 1 0 1 1। देखो ए और बी सेम रहेगा तो रिजल्ट 0 मिलता है, ए और बी डिफरेंट रहेगा तो रिजल्ट 1, यहाँ ए और बी डिफरेंट रहेगा तो रिजल्ट 1, ए और बी सेम रहेगा तो रिजल्ट 0। ये मेरा एक्सॉर गेट का रिजल्ट है, ये देखो मेरा एक्सॉर गेट का रिजल्ट है, ये मेरा एक्सॉर गेट का रिजल्ट है। तो वहीं पे यहाँ पर भी वही चीज़ है कि कैरी इन एक्सॉर कैरी आउट मेरा 1 है तो ओवरफ्लो कंडीशन है, कैरी इन कैरी आउट मेरा 0 है तो नो ओवरफ्लो कंडीशन है। या फिर अगर कैरी इन कैरी आउट मेरा डिफरेंट आ रहा है तो ओवरफ्लो होगा, कैरी इन कैरी आउट मेरा सेम आ रहा है तो ओवरफ्लो नहीं होगा, ठीक है। अब चलो इसमें सेकेंड पार्ट क्या कह रहा है, सेकेंड पार्ट को फिर से समझते हैं एक एग्जाम्पल से। अब देखो हम लोग फोकस करते हैं अपने कैरी आउट पे और MSB में। देखो ये मेरा MSB है, अब इसमें देखो वही है, अगर मेरा कैरी आउट और MSB डिफरेंट है तो ओवरफ्लो होगा, अगर मेरा कैरी आउट और MSB सेम है तो नो ओवरफ्लो। देखो कैरी आउट MSB डिफरेंट ओवरफ्लो, कैरी आउट MSB सेम नो ओवरफ्लो। तो वही देखो यहाँ पे ये लिख रहा है कि दूसरा है कि और इफ कैरी आउट इज नॉट इक्वल टू MSB देन इट रिजल्ट्स इन ओवरफ्लो कंडीशन। इट मीन्स कि इसको देखो हम लोग जनरलाइज इस तरह से भी कर सकते हैं कि कैरी आउट एक्सॉर MSB अगर 1 आया तो ये आ जाएगा मेरा ओवरफ्लो कंडीशन। इसी तरह कैरी आउट एक्सॉर MSB ये अगर मेरा 0 आ गया तो ये होता है मेरा नो ओवरफ्लो कंडीशन, ठीक है, ठीक है। सो आई होप दिस इज़ क्लियर टू यू। तो एग्ज़ाम में आपसे यही सब एज ए थ्योरेटिकल क्वेश्चन पूछ सकता है वो, ठीक है। अब देखो इसका एक और कंडीशन होता है, इसका एक और कंडीशन क्या होता है, देखो इफ़ x एंड y रिप्रेजेंट्स साइन ऑफ 2 नंबर्स एंड z रिप्रेजेंट्स साइन ऑफ रिजल्ट then overflow condition is given by x bar y bar z plus x y z bar। चलो इसे भी हम लोग एग्जाम्पल से समझते हैं। ये वाला एग्जाम्पल है, देखो देखो हम लोग +4 को कैसे रिप्रेजेंट कर रहे थे, देखो +4 को रिप्रेजेंट कर रहे थे 0100, तो इसका देखो साइन बिट क्या है 0, मीन्स यहाँ पे देखो अगर हम लोग कहते हैं कि x मेरा क्या है साइन बिट है, देखो यहाँ पे हम लोग क्या कह रहे हैं, x एंड y रिप्रेजेंट द साइन बिट ऑफ 2 नंबर। देखो इसको आप ऐसे ही समझ लो, देखो +4 है, +4 का साइन बिट कितना होगा, देखो +4 का साइन बिट मेरा हो जाएगा 0। देखो +5 का साइन बिट क्या हो जाएगा 0, ठीक है। जब हम लोग इसको ऐड कर रहे थे तो मेरा रिजल्ट जो मिल रहा था उसका साइन बिट कितना हो जा रहा था 1, उसका साइन बिट हो जा रहा था 1, उसका साइन बिट हो जा रहा था 1, ठीक है। तो इट मीन्स कि देखो यहाँ पे क्या आ जाएगा, देखो x बार आ जा रहा है, ठीक है। देखो यहाँ पे क्या आ रहा था, देखो मेरा जो x है उसका साइन बिट आ जा रहा था मेरा 0, y है उसका साइन बिट आ जा रहा था 0, z है उसका साइन बिट आ जा रहा था मेरा 1, ठीक है। तो इस केस में मेरा ओवरफ्लो कंडीशन हो रहा था, इस केस में मेरा ओवरफ्लो कंडीशन हो रहा था, ठीक है। अब देखो फिर हम लोग को ओवरफ्लो कंडीशन कहाँ पे मिल रहा था, देखो फिर हम लोग को ओवरफ्लो कंडीशन यहाँ मिला था। तो देखो यहाँ पे -4 का साइन बिट क्या है 1, -5 का साइन बिट क्या है 1, और ओवरऑल रिजल्ट का साइन बिट क्या है 0। तो देखो यहाँ पे क्या मिल जाएगा, यहाँ पे देखो क्या मिल जाएगा, देखो अगर x हमें मिलता है 1, y मिलता है 1 और z मिल जाता है हमें 0, तो उस केस में भी मेरा ओवरफ्लो होगा, उस केस में भी मेरा ओवरफ्लो होगा। अब देखो इसी दोनों को कंबाइन करके यहाँ पे हम लोग उसे जनरलाइज कर दिए हैं कि अगर मेरा x y मेरा 2 नंबर के साइन को रिप्रेजेंट करता है और z मेरा ओवरऑल रिजल्ट को ओवरऑल रिजल्ट के साइन को रिप्रेजेंट करता है, तो मेरा जो ओवरफ्लो कंडीशन है वो हम लोग लिखते हैं एज x बार y बार z प्लस x y z बार। ये क्या है, ये है मेरा ओवरफ्लो कंडीशन, ये है मेरा ओवरफ्लो कंडीशन। अब देखो जहाँ पे मेरा ओवरफ्लो कंडीशन नहीं आ रहा था वहाँ पे देखो हमें क्या मिल रहा था, देखो यहाँ पे नो ओवरफ्लो है, तो देखो यहाँ पे क्या है मेरा, देखो x 0 है, y 0 है, यहाँ देखो मेरा जो साइन रिजल्ट का साइन बिट है वो भी 0 है। इसी तरह देखो इस वाले में भी नो ओवरफ्लो होता, तो देखो x मेरा यहाँ 1 है, y मेरा 1 है और जो z है ये भी मेरा 1 है, इसलिए यहाँ पे ये मेरा नो ओवरफ्लो आ रहा है, ठीक है। सो आई होप दिस इज़ क्लियर टू यू कि ओवरफ्लो कंडीशन क्या होता है वो हम लोगों ने समझ लिया, और ओवरफ्लो कंडीशन से हम लोग कैसे चेक करेंगे वो हम लोग समझ गए, ठीक है। सो आई होप दिस इज़ क्लियर टू यू। तो चलो आगे चलते हैं। अब चलो एक क्वेश्चन देखते हैं रिलेटेड टू ओवरफ्लो कंडीशन। एक बहुत अच्छा क्वेश्चन पूछा गया था अपना ESE एग्ज़ाम में, तो चलो इसको देखते हैं। नीचे से स्टार्ट करते हैं, थर्ड स्टेटमेंट से लिखते हैं। देखो, इफ़ द कैरी इनटू द साइन बिट पोजीशन एंड कैरी आउट ऑफ द साइन बिट पोजीशन आर, ये देखो यहाँ पे लिखा हुआ है आर नॉट इक्वल एंड ओवरफ्लो कंडीशन इज प्रोड्यूस्ड। बिल्कुल सही है। अगर मेरा कैरी इन एंड कैरी आउट दोनों डिफरेंट है तो मेरा ओवरफ्लो कंडीशन होगा। सेकेंड स्टेटमेंट क्या है, एन ओवरफ्लो डज नॉट अकर, एन ओवरफ्लो डज नॉट अकर इफ द, यह है टू, इफ द टू नंबर्स एडेड आर बोथ नेगेटिव। ये गलत है। हम लोगों ने ये देखा भी था कि अगर हम लोग दो नेगेटिव नंबर को ऐड कर रहे हैं तो भी हम लोगों को ओवरफ्लो मिल रहा था, ठीक है। अब ये देखो, when two unsigned numbers are added, ये है एंड, यहाँ पे हम लोग दो अनसाइंड नंबर को ऐड कर रहे हैं, एंड ओवरफ्लो इज डिटेक्टेड फ्रॉम द कैरी इनटू द मोस्ट सिग्निफिकेंट पोजीशन। ये गलत है। देखो, अगर हम लोग अनसाइंड नंबर को ऐड कर रहे हैं ना, तो ओवरफ्लो कंडीशन कब होगा? जब हम लोग का कैरी आउट हो रहा है फ्रॉम मोस्ट सिग्निफिकेंट पोजीशन। यहाँ पे क्या दे रहा है? ये आपको कह रहा है कैरी इनटू द मोस्ट सिग्निफिकेंट पोजीशन। ऐसा नहीं है, यहाँ पे हम लोग लिख भी सकते हैं इन केस ऑफ unsigned numbers, overflow condition will occur when there is carry out from MSB and not when there is carry in MSB। ठीक है, तो करेक्ट ऑप्शन क्या होगा? ऑप्शन डी इज द करेक्ट ऑप्शन। ठीक है, आई होप दिस इज क्लियर टू यू। तो चलो आगे चलते हैं। अब चलो हम लोग कुछ प्रीवियस ईयर क्वेश्चंस देखते हैं, जिससे आपको और क्लैरिटी मिल सके जो भी अभी हम लोगों ने थ्योरी पार्ट में देखा है। तो चलो इस क्वेश्चन को देखते हैं। इस क्वेश्चन में क्या कह रहा है? ए नंबर इन 4-bit 2's complement representation is x3, x2, x1, x0. This number when stored using 8 bits will be। देखो, ये हम लोगों ने ऑलरेडी डिस्कस कर रखा है। मान लो फॉर एग्जाम्पल आपके पास एक पॉजिटिव नंबर है ऑफ 4-bit। मान लो फॉर एग्जाम्पल आपके पास एक पॉजिटिव नंबर है ऑफ 4-bit दिस, ठीक है। अब देखो, इस पॉजिटिव नंबर ऑफ 4-bit को अगर आपको 8-bit में कन्वर्ट करना है, तो हम लोगों ने ये डिस्कस किया था। हम लोग क्या करेंगे? हम लोग का जो MCB है, MCB जो है, जो अपना मोस्ट सिग्निफिकेंट बिट है, उसी को हम लोग एक्सटेंड कर देंगे। तो ये हो जाएगा 0 0 0 0 0 1 0 1, ठीक है। तो देखो, हम लोग के पास 4-bit था, 4-bit पॉजिटिव नंबर था, इसे हम लोगों ने 8-bit पॉजिटिव नंबर में कन्वर्ट कर दिया। इसके लिए हम लोग क्या किए? बेसिकली मेरा जो MSB था, मोस्ट सिग्निफिकेंट बिट था, उसे ही हम लोगों ने यहाँ पे एक्सटेंड कर दिया। अब देखो, मान लो हम लोग के पास अब एक निगेटिव नंबर है ऑफ 4-bit, दैट इज 1 0 1 0। ऐसे हम लोग एक रैंडम एग्जांपल ले रहे हैं समझने के लिए। तो देखो, हम लोग का जो मोस्ट सिग्निफिकेंट बिट है वो 1 है। इट मीन्स कि ये मेरा एक निगेटिव नंबर है। अब इस निगेटिव नंबर को अगर हम लोगों को 4-bit से 8-bit में कन्वर्ट करना है, तो हम लोग को क्या करना पड़ेगा? फिर से मेरा जो मोस्ट सिग्निफिकेंट बिट है उसे ही आप एक्सटेंड कर दो। इट मीन्स आपको मिल जाएगा 1 1 1 1 1 0 1 0। तो देखो, मेरे पास एक 4-bit निगेटिव नंबर था, उसे हम लोगों ने 8-bit निगेटिव नंबर में कन्वर्ट कर दिया। और उसके लिए हम लोगों ने किया क्या? मेरा जो मोस्ट सिग्निफिकेंट बिट था उसे ही हम लोग एक्सटेंड कर दिया, ठीक है। अब चलो वापस इस क्वेश्चन में आते हैं। तो ये क्वेश्चन भी वही कह रहा है। ये कह रहा है कि आपके पास एक नंबर है, 4-bit नंबर है, और हम लोग 2's कॉम्प्लीमेंट रिप्रेजेंटेशन लेकर चल रहे हैं, और हम लोग इस 4-bit नंबर को रिप्रेजेंट कर रहे हैं एज x3, x2, x1, x0। अब अगर हमें इस नंबर को 8 बिट में कन्वर्ट करना है तो हम लोग को क्या करना है, बेसिकली मेरे पास जो मोस्ट सिग्निफिकेंट बिट है, उसे ही आप एक्सटेंड कर दो। मीन्स अब ये हो जाएगा x3 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 x3, यहाँ आ गया x3 x2 x1 x0। तो देखो ये हम लोग के पास एक 4 बिट नंबर था। फिर मान लो ये पॉजिटिव नंबर हो या नेगेटिव नंबर हो, कुछ भी हो, अगर x3 मेरा 0 है तो पॉजिटिव नंबर हो जाएगा, x3 मेरा 1 है तो मेरा ये नेगेटिव नंबर हो जाएगा। तो ये बेसिकली मेरा 4 बिट नंबर है। इसे अगर हम लोगों को 8 बिट में कन्वर्ट करना है तो हम लोगों को क्या करना पड़ेगा, मेरा जो MSB या मोस्ट सिग्निफिकेंट बिट है उसे ही हम लोगों को फर्दर एक्सटेंड कर देना पड़ेगा। ठीक है, तो मेरा जो करेक्ट ऑप्शन है वो हो जाएगा ऑप्शन सी। ठीक है, तो चलो आगे चलते हैं। अब चलो नेक्स्ट क्वेश्चन में आते हैं। ये क्या कह रहा है, 2 4 बिट 2's complement numbers 1011 and 0110 are added। 1011 and 011 को हम लोग ऐड कर रहे हैं इन 2's complement रिप्रेजेंटेशन। अब ये कह रहा है द रिजल्ट एक्सप्रेस्ड इन 4 बिट 2's complement नोटेशन इज। तो चलो इसको सॉल्व करते हैं। 1011 और 0110, इस दोनों नंबर को हम लोगों को ऐड करना है इन 2's complement रिप्रेजेंटेशन। तो ये क्या हो जाएगा, 101, ये हो गया 0 1 कैरी, यहाँ 0, यहाँ 1 कैरी, यहाँ 0 और यहाँ पे मेरा 1 कैरी। तो हम लोगों ने ये डिस्कस किया था कि अगर हम लोग 2's complement रिप्रेजेंटेशन में एडिशन कर रहे हैं तो ये जो मेरा कैरी होगा इसको हम लोगों को इग्नोर कर देना है। ठीक है, इस कैरी को इग्नोर कर दिए। अब हम लोगों को रिजल्ट में क्या मिल गया, अब हम लोगों को रिजल्ट में मिल गया 0001। तो यहाँ पे हम लोग देख सकते हैं कि मेरा जो MSB है या मोस्ट सिग्निफिकेंट बिट है वो हम लोग को 0 मिल रहा है। इट मीन्स कि ये मेरा एक पॉजिटिव नंबर है और ये अपने ट्रू सेंस में है। ठीक है, तो इसमें हम लोग को और कोई चेंजेस करने का ज़रूरत नहीं है। तो हम लोग का जो करेक्ट ऑप्शन है वो आ जाएगा 0001। ठीक है, तो चलो आगे चलते हैं। अब चलो इस क्वेश्चन को देखते हैं। द बेस ऑफ द नंबर सिस्टम फॉर द एडिशन ऑपरेशन 24 + 14 = 41 टू बी ट्रू। देखो आपको एक रिलेशन दे दिया है 24 + 14 = 41 और आपको कह रहा है कि यार आप इसका बेस बताओ कि क्या बेस होना चाहिए। तो हम लोग मान लेते हैं कि इसका बेस r है। तो हम लोग को देखो ये इक्वेशन कैसा मिलेगा, 24 बेस r + 14 बेस r = 41 बेस r। ठीक है, अब हम लोग इसको डेसिमल में कन्वर्ट कर देते हैं। तो हम लोग को क्या मिल जाएगा, देखो हम लोगों ने इसको ऑलरेडी देख रखा है। जैसे फॉर एग्जांपल मान लो आपके पास एक नंबर है 101, ये आपका बाइनरी में है। इसको अगर आपको डेसिमल में करना है, तो आपको क्या करना रहेगा, 2 to the power 0, 2 to the power 1, 2 to the power 2, ये आपको मिल जाएगा 4 + 1। इट मीन्स डेसिमल में आपको मिल गया 5। तो सेम फंडामेंटल यहाँ पे लगाते हैं। यहाँ पे देखो सभी नंबर का जो बेस है वो r है। तो इसको अगर हम लोग को डेसिमल में कन्वर्ट करना है तो हम लोग को क्या मिलेगा, हम लोग को मिल जाएगा 2r + 4 + r + 4 = 4r + 1। अब इसको अगर हम लोग सॉल्व किए तो हम लोग का r क्या मिल जाएगा, r is 7। इट मीन्स कि जो यहाँ पे बेस है वो है बेस हम लोग का 7। दैट इज ऑप्शन बी इज द करेक्ट ऑप्शन। इस तरह के क्वेश्चंस बहुत पूछे जाते हैं ESE एग्ज़ाम में। तो आपको करना क्या है, कि आप जो ये गिवन इक्वेशन दिया गया है उस इक्वेशन के लिए आप एक बेस कंसिडर कर लो और फिर उस बेस को कंसिडर करके आप पूरे रिज़ल्ट को डेसिमल में कन्वर्ट करने का ट्राई करो। वहाँ से आपको एक इक्वेशन मिल जाएगा, उस इक्वेशन को आप सॉल्व करोगे तो आपको फाइनल रिज़ल्ट मिल जाएगा। आई होप दिस इज़ क्लियर टू यू। तो चलो आगे चलते हैं। अब चलो नेक्स्ट क्वेश्चन देखते हैं। ये क्या कह रहा है, द रिजल्ट ऑफ 45 बेस 10 माइनस 45 बेस 16 एक्सप्रेस्ड इन 6 बिट 2's कॉम्प्लीमेंट रिप्रेजेंटेशन। ठीक है, तो हम लोग को दिया गया है, ये हम लोग को निकालना क्या है, 45 बेस 10 माइनस 45 बेस 16। इसको कह रहा है कि आप इस रिजल्ट को निकालो इन 6 बिट 2's कॉम्प्लीमेंट रिप्रेजेंटेशन, इन 6 बिट 2's कॉम्प्लीमेंट रिप्रेजेंटेशन। तो देखो यहाँ पे बेस 10 है, यहाँ पे बेस 16 है, तो सबसे पहले तो हम लोग को बेस सेम करना पड़ेगा। तो हम लोग क्या करते हैं, जो 10 वाला है उसे तो वैसे ही रहने देते हैं, हम लोग इसे कन्वर्ट कर लेते हैं, हेक्साडेसिमल को कन्वर्ट कर लेते हैं इन बेस 10। ठीक है, तो इसको कैसे कन्वर्ट करेंगे, हम लोग अपना इसमें वही फॉर्मूला यूज़ कर लेते हैं, 16 टू द पावर 0, 16 टू द पावर 1, तो ये आ जाएगा 4 इंटू 16 प्लस 5, मीन्स 69 मीन्स हम लोग को क्या मिल जाएगा, हम लोग को मिल जाएगा 45 बेस 10 माइनस 69 बेस 10। ठीक है, तो देखो हम लोगों ने अपना बेस सेम कर लिया। अब आप इसको इजीली इसे सब्ट्रैक्ट कर दो। इसे अगर आप सब्ट्रैक्ट करोगे तो आपको क्या मिल जाएगा, माइनस 24 बेस 10, ये आपको मिल जाएगा। अगर आप इसको सब्ट्रैक्ट करोगे तो आपको मिल जाएगा माइनस 24 बेस 10। तो आपको ये क्या कह रहा है कि माइनस 24 बेस 10 को आप 6 बिट 2's कॉम्प्लीमेंट फॉर्म में रिप्रेजेंट करो। इसे आप 6 बिट 2's कॉम्प्लीमेंट फॉर्म में रिप्रेजेंट करो। तो चलो इसको रिप्रेजेंट करते हैं। सबसे पहले तो हम लोग प्लस 24 निकाल लेते हैं। सबसे पहले हम लोग प्लस 24 निकाल लेते हैं। तो प्लस 24 क्या आ जाएगा, प्लस 24 हम लोग निकालते हैं इन बाइनरी, प्लस 24 हम लोग निकालते हैं इन बाइनरी, क्योंकि रिजल्ट हम लोग का यहाँ पे बाइनरी में पूछा गया है। तो ये आ जाएगा आपका 1 1 0 0 0। ठीक है, अब ये प्लस 24 है, इट मीन्स कि यहाँ पे हम लोग को एक साइन बिट भी इंसर्ट करना है। इट मीन्स कि ये आप 0 कर दो। अब देखो मेरे पास कितने बिट्स आ गए, मेरे पास 6 बिट्स आ गए। पूछा कितना था, 6 बिट में ही आपको कन्वर्ट करना है, तो इतना ही रहने दो। इसमें आपको अब और कोई एडिशन करने का ज़रूरत नहीं है, मतलब आपको कोई और भी बिट्स ऐड करने का ज़रूरत नहीं है, क्योंकि 6 बिट यहाँ पूछा गया था, 6 बिट में मेरा रिजल्ट ही आ गया। तो प्लस 24 आ गया। अब माइनस 24 निकालना है। माइनस 24 निकालने के लिए हम लोग को 2's कॉम्प्लीमेंट लेना पड़ेगा, क्योंकि यहाँ पे वो लिख रखा है कि जो भी आप करो आप 2's कॉम्प्लीमेंट रिप्रेजेंटेशन में करो। ठीक है, तो ये आपका आ जाएगा 1 0 0 1 1 1, यहाँ फिर से 1 ऐड करो, ये हो गया 0 0 0 1 0 1। ये आ गया आपका माइनस 24 का बाइनरी रिप्रेजेंटेशन इन 6 बिट 2's कॉम्प्लीमेंट फॉर्म। तो ये आपका रिजल्ट क्या आ जाएगा, 1 0 1 0 0। ऑप्शन सी इज द करेक्ट ऑप्शन। आई होप दिस इज क्लियर टू यू। तो चलो आगे चलते हैं। अब चलो नेक्स्ट क्वेश्चन देखते हैं। यहाँ पे क्या है, द सब्सट्रैक्शन ऑफ ए बाइनरी नंबर y फ्रॉम अनदर बाइनरी नंबर x done by adding the 2's complement, done by adding the 2's complement of y to x result in a binary number without overflow. This implies that the result is, देखो ये चीज़ हम लोगों को पता है, ये चीज़ हम लोगों ने डिस्कस कर रखा है, लेकिन यहाँ पे क्या है ना, आपको जो ऑप्शंस दिया है आपको ये थोड़ा सा लिटरेचर के फॉर्म में दे दिया है, तो यहाँ पे आप कंफ्यूज हो सकते हो। इसमें देखो बेसिकली आपको क्या कह रहा है, इसमें देखो आपको क्या कह रहा है कि आपको कह रहा है, आपको कह रहा है कि आप निकालो x माइनस वाई। ठीक है, x माइनस वाई हम लोग कैसे निकालते हैं, इन टूज कॉम्प्लीमेंट रिप्रेजेंटेशन हम लोग निकालते हैं इसको कुछ इस तरह से, x प्लस माइनस वाई। यही हम लोगों ने डिस्कस किया था ना कि अगर हम लोगों को y को सब्ट्रैक्ट करना है x से, तो सबसे पहले तो हम लोग माइनस वाई निकाल लेते हैं और फिर माइनस वाई निकाल के उसे हम लोग x के साथ ऐड कर देते हैं, और ये जो भी कर रहे हैं ये हम लोग टूज कॉम्प्लीमेंट फॉर्म में कर रहे हैं। तो इसमें हम लोग को बेसिकली टूज कॉम्प्लीमेंट में जो हम लोगों ने अपना सब्सट्रैक्शन का जो हम लोगों ने पॉइंट्स लिखे थे वही हम लोग को यहाँ पे फॉलो करना है। तो इसमें हम लोगों ने क्या देखा था कि y x माइनस वाई करना है, तो सबसे पहले माइनस वाई निकालो और फिर माइनस वाई को x के साथ ऐड कर दो। अब आपका देखो ये क्या कह रहा है, अब आपने यहाँ पे ऐड किया, मान लो आपको रिजल्ट मिला पॉजिटिव, मान लो कि आपको यहाँ से रिजल्ट मिल गया 0101, तो यहाँ पे मेरा जो MCB बिट है वो 0 है, इट मीन्स कि रिजल्ट पॉजिटिव है। तो हम लोगों ने डिस्कस किया था कि अगर मेरा MCB बिट 0 है तो मेरा रिजल्ट पॉजिटिव होगा, और वो जो रिजल्ट मिला है वो मेरा ट्रू फॉर्म में है या नॉर्मल फॉर्म में है। तो देखो यहाँ पे वही है, ऑप्शन सी में देख लो कि अगर आपका रिजल्ट पॉजिटिव है तो वो आपका ट्रू फॉर्म या नॉर्मल फॉर्म में दिया गया है। ठीक है, अब वही मान लो कि ये जो मेरा रिजल्ट आया ये मेरा नेगेटिव आ रहा है, इट मीन्स कि मेरा 1010 आ रहा है। अब देखो मेरा MCB 1 है, मेरा जो मोस्ट सिग्निफिकेंट बिट है वो 1 है, MCB 1 है, इट मीन्स कि मेरा रिजल्ट नेगेटिव है। और अगर रिजल्ट नेगेटिव है तो ये रिजल्ट मेरा ट्रू फॉर्म या नॉर्मल फॉर्म नहीं है, ये मेरा टूज कॉम्प्लीमेंट फॉर्म में है। तो अब इसका ट्रू फॉर्म या नॉर्मल फॉर्म लेने के लिए हम लोगों को इसका टूज कॉम्प्लीमेंट लेना पड़ेगा, यही तो हम लोगों ने डिस्कस किया था थ्योरी में। तो यहाँ पे देखो वही लिखा है, ऑप्शन बी भी मेरा यहाँ पे सही होगा कि अगर मेरा वो रिजल्ट नेगेटिव है तो वो मेरा टूज कॉम्प्लीमेंट फॉर्म में है। ठीक है, तो हम लोगों ने थ्योरी में तो देख रखा है, लेकिन आप देखो एग्जामिनर ने उसी चीज़ को कैसे घुमा कर आपसे क्वेश्चन पूछा है। तो अगर आपके थ्योरी में पकड़ है तो आप दिक्कत नहीं आएगा, आप क्वेश्चंस को इजीली सॉल्व कर लोगे, आप समझ लोगे कि एग्जामिनर आपको कहाँ पे घुमाना चाह रहा है। ठीक है, सो आई होप दिस इज़ क्लियर टू यू। तो ऑप्शन बी एंड सी इज़ द करेक्ट ऑप्शन। तो चलो आगे चलते हैं। अब देखो यहाँ पे क्या कह रहा है, एन इक्विवेलेंट टूज कॉम्प्लीमेंट रिप्रेजेंटेशन ऑफ द टूज कॉम्प्लीमेंट नंबर 1101। देखो आपको नंबर दिया गया है 1101। तो देखो ये आपका किस में है, 4 बिट में, ये आपका 4 बिट में। आपको कह रहा है कि इसका आप इक्विवेलेंट 6 बिट रिजल्ट निकालो। देखो यहाँ पे आपको जो ऑप्शन है सब आपको 6 बिट दे रहा है, इट मीन्स कि बेसिकली आपको क्या कह रहा है कि आपका ये 1101 है, 4 बिट में है, इसका आप इक्विवेलेंट 6 बिट रिजल्ट निकालो, और ये आप करना है हम लोग को टूज कॉम्प्लीमेंट रिप्रेजेंटेशन में। तो बहुत इजी है, देखो ये इस नंबर को देखें तो हम लोग देख सकते हैं कि मेरा जो MCB है दैट इज़ मोस्ट सिग्निफिकेंट बिट वो मेरा 1 है, इट मीन्स कि ये नंबर मेरा निगेटिव है। तो अब एक निगेटिव नंबर को अगर हम लोग को 4 बिट से 6 बिट में कन्वर्ट करना है तो हम लोग को करना क्या है, जो मेरा मोस्ट सिग्निफिकेंट बिट है उसी को आप एक्सटेंड कर दो, इट मीन्स कि 111101। तो आपका करेक्ट ऑप्शन हो जाएगा ऑप्शन डी। ठीक है, तो चलो आगे चलते हैं। अब चलो नेक्स्ट क्वेश्चन देखते हैं, द टूज कॉम्प्लीमेंट रिप्रेजेंटेशन ऑफ -17। ये है आपका -17। आपको देखो -17 का टूज कॉम्प्लीमेंट रिप्रेजेंटेशन पूछ रहा है। ठीक है, तो सबसे पहले तो देखो हम लोग +17 निकालते हैं, सबसे पहले हम लोग +17 निकालते हैं। ये आ जाएगा आपका 10001, ठीक है। तो 10001 प्लस 17 निकालना है, तो यहाँ पे हम लोग अपना एक MCV साइन बिट लगा दो 0, साइन बिट लगा दो आप 0, ठीक है। अब देखो क्वेश्चन में आपका कितने बिट में रिजल्ट पूछ रहा है, 1 2 3 4 5 6, 1 2। अब तो देखो यहाँ भी हम लोग, हाँ ठीक है, रिजल्ट भी हम लोग का 6 बिट में पूछ रहा है, और यहाँ पे साइन बिट लगाने के बाद हम लोग का ये 6 बिट पे आ गया। तो अब हम लोग को और कोई एक्सपेंशन करने का ज़रूरत नहीं है। तो अब हम लोग निकालते हैं -17, 2's कॉम्प्लीमेंट रिप्रेजेंटेशन में करना है, तो +17 से -17 करने के लिए इसका 2's कॉम्प्लीमेंट ले लो। तो ये हो गया 1 0 1 1 1 0, 1 ऐड कर दो, तो ये हो गया 1 0 1 1 1 1। तो ये आ गया आपका -17 का 2's कॉम्प्लीमेंट रिप्रेजेंटेशन इन 6 बिट, 1041। तो आपका ऑप्शन बी इज द करेक्ट ऑप्शन। अब देखो यहाँ पे क्या कह रहा है, 4 बिट 2's कॉम्प्लीमेंट रिप्रेजेंटेशन ऑफ ए डेसिमल नंबर इज दिस। आपको कह रहा है कि एक आपका डेसिमल नंबर है, कुछ भी हो, उसका आपको 4 बिट 2's कॉम्प्लीमेंट रिप्रेजेंटेशन दे दिया है, दैट इज 1 0 0 0। अब आपसे कह रहा है कि यार आपका डेसिमल नंबर क्या है, तो चलो इसको देखते हैं। तो देखो ये आपका क्या है, जो मोस्ट सिग्निफिकेंट बिट है वो 1 है। इट मीन्स कि ये आपका एक निगेटिव नंबर है, ठीक है। मोस्ट सिग्निफिकेंट बिट से हम लोगों ने साइन तो निकाल लिया कि ये आपका एक नेगेटिव नंबर है। अब मैग्नीट्यूड के लिए हम लोग को क्या करना पड़ेगा, मैग्नीट्यूड के लिए हम लोगों को इसका 2's कॉम्प्लीमेंट निकालना पड़ेगा, क्योंकि यहाँ पे हम लोगों को 2's कॉम्प्लीमेंट रिप्रेजेंटेशन दिया है। तो मैग्नीट्यूड के लिए हम लोग को यहाँ पे इसका 2's कॉम्प्लीमेंट निकालना है। इट मीन्स कि 0 1 1 1 और 1 ऐड कर दो, तो ये आ जाएगा आपका 0 0 0 1। ओके, सॉरी, ठीक है, मतलब कि ये ठीक है, ये करने का ज़रूरत नहीं था, क्योंकि ये तो हम लोगों को ऑलरेडी क्वेश्चन में दे ही दिया है। देखो हम लोग को तो क्वेश्चन में ऑलरेडी दे ही दिया है कि 4 बिट 2's कॉम्प्लीमेंट रिप्रेजेंटेशन हम लोग को दे दिया है। 4 बिट 2's कॉम्प्लीमेंट रिप्रेजेंटेशन क्या है, 1 0 0 0, ठीक है। तो देखो ये नंबर होगा क्या, देखो मोस्ट सिग्निफिकेंट बिट से हम लोग निकाल सकते हैं कि ये नंबर तो नेगेटिव है, और ये नंबर है क्या, इस नंबर को निकालने के लिए हम लोग इसको डेसिमल में कन्वर्ट कर लेते हैं। तो ये आ जाएगा 1 × 2 to the power 3, दैट इज -8। -8 इज द करेक्ट आंसर, ठीक है। तो चलो आगे चलते हैं। अब देखो यहाँ क्या कह रहा है, x आपका दिया गया है 0 1 1 1 0, y आपका दिया गया है 1 1 0 0 1, R2 5 बिट बाइनरी नंबर्स, R2 5 बिट बाइनरी नंबर्स रिप्रेजेंटेड इन 2's कॉम्प्लीमेंट फॉर्म। The sum of x plus y represented in 2's complement form using 6 bit, using 6 bit, ठीक है। तो देखो आपको x क्या दे दिया है, आपको x दे दिया है 0 1 1 1 0। तो x आपका एक पॉजिटिव नंबर है, लेकिन है ये 5 बिट में। रिजल्ट वो चाहता है आपसे 6 बिट में, तो इसको पहले ही 6 बिट में कन्वर्ट कर लो, 0 को एक्सटेंड कर दो। अब जो y है, y आपका दिया है 1 1 0 0 1। y देखो आपका एक निगेटिव नंबर है, क्योंकि MSB जो है वो मेरा 1 है, लेकिन है ये 5 बिट में। तो इसको अब हम लोग 6 बिट में कन्वर्ट करना चाहते हैं, क्योंकि रिजल्ट 6 बिट में पूछ रहा है। तो यहाँ पे हम लोग 1 को एक्सटेंड कर देंगे। अब हम लोग को क्या करना है, अब हम लोग को x प्लस वाई निकालना है इन 2's कॉम्प्लीमेंट रिप्रेजेंटेशन, तो चलो निकाल लो। ये 1 1 1 0 0 0, यहाँ 1 है कैरी में, तो इसको हम लोग टूज कॉम्प्लीमेंट रिप्रेजेंटेशन में इग्नोर करते हैं। अब अपने रिजल्ट को देखो, तो रिजल्ट देखो मेरा MSB 0 है, इट मीन्स कि मेरा रिजल्ट पॉजिटिव है और ये मेरा ट्रू फॉर्म में है या नॉर्मल फॉर्म में। तो ये हो जाएगा मेरा 0000111, ऑप्शन सी इज द करेक्ट ऑप्शन। ठीक है, अब चलो नेक्स्ट क्वेश्चन में चलते हैं। तो यहाँ पे क्या कह रहा है, PQR आर द डेसिमल इंटीजर्स कॉरेस्पॉन्डिंग टू द 4-bit बाइनरी नंबर। आपका जो बाइनरी नंबर है वो है 1100। ठीक है, कंसिडर्ड इन साइन मैग्नीट्यूड वंस कॉम्प्लीमेंट एंड टूज कॉम्प्लीमेंट रिप्रेजेंटेशन respectively, the 6-bit 2's complement representation of PQR is। अच्छा क्वेश्चन है ये। देखो आपको क्या कह रहा है, आपको कह रहा है कि आपके पास एक 4-bit बाइनरी नंबर है 1100। आपके पास एक 4-bit बाइनरी नंबर है 1100। आपको कह रहा है कि आपका जो P है वो क्या है, वो है आपका आपका देखो जो P है, आपका जो P है वो क्या है, डेसिमल इक्विवेलेंट ऑफ 1100 इन साइंड मैग्नीट्यूड फॉर्म। Q क्या है, Q है आपका डेसिमल इक्विवेलेंट ऑफ 1100 इन वंस कॉम्प्लीमेंट फॉर्म, और आपका R क्या है, डेसिमल इक्विवेलेंट of 1100 in 2's complement form। ठीक है, आपके पास एक 4-bit बाइनरी नंबर है 1100 और आपको कह रहा है कि P क्या है, डेसिमल इक्विवेलेंट ऑफ 1100 इन साइंड मैग्नीट्यूड फॉर्म। Q क्या है, डेसिमल इक्विवेलेंट ऑफ 1100 इन वंस कॉम्प्लीमेंट फॉर्म। R क्या है, डेसिमल इक्विवेलेंट ऑफ 1100 इन 2's कॉम्प्लीमेंट फॉर्म। ठीक है, तो सबसे पहले तो हम लोग PQR ये निकाल लेते हैं। ठीक है, तो चलो हम लोग PQR निकालते हैं। तो देखो हम लोग का P कैसे निकलेगा, देखो हम लोग का P कैसे निकलेगा, P निकालने हम लोग को पता है। देखो 1100 है तो ये मेरा साइंड मैग्नीट्यूड फॉर्म में है। तो साइंड मैग्नीट्यूड फॉर्म में क्या होता है, मेरा जो MSB होता है वो मेरा साइन बताता है। तो यहाँ पे MSB क्या है 1, इट मीन्स कि मेरा ये हो गया नेगेटिव। अब मेरा जो मैग्नीट्यूड है, MSB बताता है साइन, तो यहाँ पे 1 है तो ये हो गया नेगेटिव। अब जो मैग्नीट्यूड है वो ये वाला पोर्शन बताएगा। साइंड मैग्नीट्यूड में हम लोगों ने यही बात किया था कि जो मेरा जो मोस्ट सिग्निफिकेंट बिट होता है वो मेरा साइन बता देता है, और उसके बाद जो मेरे रिमेनिंग बिट्स है वो मेरा मैग्नीट्यूड बताता है। तो ये वाला पार्ट मेरा बताएगा मैग्नीट्यूड। तो ये कैसे बताएगा, इसको कन्वर्ट कर लेते हैं हम लोग बाइनरी टू डेसिमल। तो ये हो जाएगा दिस, इट मीन्स ये आ गया P आ गया -4। ठीक है, बढ़िया है, P आ गया -4। अब आ जाते हैं हम लोग Q में। Q क्या है, वंस कॉम्प्लीमेंट फॉर्म। तो इसमें क्या होगा, देखो 1100 MSB 1 है, इट मीन्स कि ये आ गया नेगेटिव, ये आ गया नेगेटिव। अब वंस कॉम्प्लीमेंट फॉर्म है तो इसका अगर हम लोग को ट्रू वैल्यू निकालना है तो इसका आप वंस कॉम्प्लीमेंट निकाल दो, तो ये हो जाएगा 0011। अब इसको आप डेसिमल में कन्वर्ट कर दो तो ये आ जाएगा आपका -3। ठीक है, अब हम लोग फोकस करते हैं R पे। R क्या है, 2's कॉम्प्लीमेंट फॉर्म। तो MSB 1 है, इट मीन्स कि हो गया ये नेगेटिव। अब इसका जो मैग्नीट्यूड है उसके लिए इसका 2's कॉम्प्लीमेंट निकाल दो, मीन्स 0 0 1 1, यहाँ 1 ऐड करो, 0 0 1 और 0। अब इसको हम लोग बाइनरी टू डेसिमल कर देते हैं, तो ये हो गया, ये भी हो गया -4, ये भी हो गया -4। तो देखो PQR मेरा आ गया, मेरा PQR आ गया। अब हम लोग निकाल लेते हैं P + Q + R, यही निकालना है, P + Q + R। तो ये क्या हो जाएगा, ये आ गया -11। अब आपको क्या कह रहा है कि -11 को आप 2's कॉम्प्लीमेंट फॉर्म में रिप्रेजेंट कर दो, हैविंग 6 बिट। -11 को आप 6 बिट 2's कॉम्प्लीमेंट फॉर्म में रिप्रेजेंट कर दो। तो चलो रिप्रेजेंट करते हैं। सबसे पहले तो हम लोग +11 निकालते हैं, हम लोग +11 निकालते हैं इन 6 बिट फॉर्म। तो ये आ जाएगा आपका ये आ गया आपका 1011। अब इसके +11 है तो यहाँ पे एक 0 डाल दो। कितना बिट बन गया, 5। 6 बनाना है तो एक और 0 डाल दो। अब हम लोग को निकालना है -11 इन 2's कॉम्प्लीमेंट फॉर्म। तो इसके लिए हम लोग क्या करेंगे, इसका अब 2's कॉम्प्लीमेंट ले लो, 1 1 0 1 0 0, यहाँ 1, इट मीन्स कि 1 1 0 1 0 1 1 1 0 1 0 1 1 1 0 1 0 1। ऑप्शन बी इज़ द करेक्ट ऑप्शन। तो एक बहुत अच्छा क्वेश्चन था, एग्जामिनर ने बहुत अच्छे से घुमाकर आपसे पूछा है, लेकिन अगर आपका कॉन्सेप्ट क्लियर है तो आप इस तरह के क्वेश्चंस को इजीली सॉल्व कर लोगे। ठीक है, तो चलो आगे चलते हैं। अब चलो इस क्वेश्चन को देखते हैं। इफ़ ए नेगेटिव बाइनरी नंबर इज टू बी रिप्रेजेंटेड बाई n बिट्स, देन द स्टैंडर्ड फॉर्मेट विल बी। इफ़ ए नेगेटिव बाइनरी नंबर इज टू बी रिप्रेजेंटेड बाई n बिट्स। तो देखो क्या होगा, देखो अगर मेरा साइन बिट 0 है ऑन लेफ्ट एंड मैग्नीट्यूड राइट, लेकिन मेरा नेगेटिव बाइनरी नंबर है, इट मीन्स कि मेरा साइन बिट 1 होना चाहिए। नेगेटिव बाइनरी नंबर है, इट मीन्स कि मेरा साइन बिट 1 होना चाहिए। इट मीन्स कि ऑप्शन बी एंड ऑप्शन डी पे हम लोगों को फोकस करना है। तो यहाँ देखो क्या है, साइन बिट 1 ऑन लेफ्ट, मैग्नीट्यूड ऑन राइट, सही है। ये क्या है, साइन बिट 1 ऑन राइट एंड मैग्नीट्यूड ऑन लेफ्ट, ये गलत है। ये तो हम लोगों ने देखा है ना कि अगर देखो 1 0 1 0 है, MSB मेरा 1 है, इट मीन्स कि मेरा नंबर नेगेटिव हुआ, और ये MSB मेरा हमेशा लेफ़्ट पार्ट में है, ठीक है, और जो रिमेनिंग पार्ट है वो हम लोगों का जो मैग्नीट्यूड है वो बताता है। तो ऑप्शन बी इज़ द करेक्ट ऑप्शन। अब चलो इस क्वेश्चन को करते हैं। इसमें क्या कह रहा है, आपको एक रिलेशनशिप दिया गया है, 2.3 बेस 4 प्लस 1.2 बेस 4 इज इक्वल टू y बेस 4। आपको कह रहा है फाइंड द वैल्यू ऑफ y। तो चलो इसको सॉल्व करते हैं। बेस 4 को लेकर ही सॉल्व कर लेते हैं डायरेक्ट। देखो एक ऑप्शन आपके पास क्या है, देखो हम लोग इस क्वेश्चन को 2 मेथड से सॉल्व कर सकते हैं। मेरा मेथड, पहला मेथड आप लोग क्या कर सकते हो, देखो ये आपका 2.3 बेस 4 दिया है, इसको आप डेसिमल में कन्वर्ट कर दो। ये आपको देखो 1.4 बेस 4 दिया है, इसको भी आप डेसिमल में कन्वर्ट कर दो, ठीक है। फिर डेसिमल में कन्वर्ट करके इनको आप ऐड कर दो, आपको एक फाइनल रिजल्ट मिल जाएगा जो आपको डेसिमल में मिल जाएगा। अब आप क्या करो, देखो ये आपको जो भी आपको ये ऑप्शंस दिए गए हैं ये सब आपके बेस 4 के ऑप्शंस हैं, ये सारे आपके बेस 4 के ऑप्शन हैं। तो फिर आपको क्या करना है, आप 1 बाय 1 ऑप्शन को पकड़ो, बेस 4 है तो इन सबको आप डेसिमल में कन्वर्ट करो, फिर देखो कौन सा ऑप्शन आपका इस वाले रिजल्ट से मैच कर रहा है, ठीक है। एक ऑप्शन तो ये है, आप इस तरह से भी इस क्वेश्चन को सॉल्व कर सकते हो, लेकिन हाँ इस तरह से इस क्वेश्चन को सॉल्व करने में आपको टाइम लग जाएगा। क्वेश्चन आपका पूछा भी ESE में दिया है, जहाँ पे आपका टाइम कंस्ट्रेंट रहता है। तो इस तरह के ईजी क्वेश्चन को अगर आप इस तरह से लॉन्ग फॉर्म में सॉल्व करने जाओगे तो आप टाइम वेस्ट करोगे, आप 1-2 क्वेश्चन जो आप सॉल्व कर सकते थे एक्स्ट्रा वो आप नहीं कर पाओगे। तो एक ऑप्शन तो ये है, बट मैं आपको ये ऑप्शन प्रेफर नहीं करूँगा। हम लोग क्या है, डायरेक्ट अपना बेस कंसिडर करते हुए इसको सॉल्व करते हैं, ठीक है। तो देखो यहाँ पे क्या है, बेस 4 है। तो देखो बेस 4 है, इट मीन्स कि मेरे पास कितने सिंबल्स होंगे, 4 सिंबल्स होंगे। वो 4 सिंबल्स क्या होंगे, 0 1 2 3। मीन्स देखो 0 होगा, 1 होगा, 2 होगा, 3। अब बेस 4 में अगर आपका 4 आ गया तो इसको आप कैसे रिप्रेजेंट करोगे, इसको आप रिप्रेजेंट करोगे 1 0 से। अगर 5 आ गया तो इसको आप रिप्रेजेंट करोगे 1 1 से। अगर 6 आ गया इसको आप रिप्रेजेंट करोगे 1 2 से, एंड सो ऑन। ठीक है, तो अब देखो यहाँ पे क्या आया, 3 + 2 5। 5 इट मीन्स कि इसको आप लिखोगे 1, यहाँ पे कैरी 1। अब देखो ये 1 + 2 + 1 4 आ गया, यहाँ डेसिमल है, इसको यहाँ पुट कर दो। 4 मतलब 4 को आप लिखोगे 1 0 1 0, मीन्स आपका रिजल्ट आ गया 10.14 बेस 4। करेक्ट ऑप्शन इज ए। तो हम लोग देख सकते हैं कि मेथड 2 मेरा कितना सिंपल है। अगर हम लोग का जो कॉन्सेप्ट है वो क्लियर है विथ रेस्पेक्ट टू बेस एंड ऑल, तो हम लोग इजिली इस क्वेश्चन को सॉल्व कर सकते हैं। तो चलो आगे चलते हैं। अब देखो इस क्वेश्चन में क्या कह रहा है, बाइनरी डेटा इज बिन रिप्रेजेंटेड इन साइज ऑफ बाइट and in 2's complement form. The number of zeros present in the representation of -127 base 10. तो आपको कह रहा है कि -127 बेस 10 इसमें आपके कितने ज़ीरो हैं। इसको अगर आप बाइनरी में कन्वर्ट कर रहे हो टेकिंग 2's कॉम्प्लीमेंट फॉर्म, तो आपके कितने ज़ीरो आएंगे। तो चलो सबसे पहले तो हम लोग +127 ले लेते हैं। इसको हम लोग निकालते हैं कि ये क्या है। तो ये आ जाएगा 1 1 1 1 1 1 1 1 2 3 4 5 6 7 1 2 3 4 5 6 7 +127 है, मीन्स यहाँ पे आपको इसका साइन बिट 0 भी ऐड करना पड़ेगा। अब इसको आप कन्वर्ट कर दो। अब हम लोग को निकालना है -127, इट मीन्स इसका आप 2's कॉम्प्लीमेंट ले लो। तो ये आ जाएगा 1 ऐड कर दो, तो ये आ गया आपका -127। तो हम लोग यहाँ पे देखो, यहाँ पे आपको कितने ज़ीरोज़ मिल गए, 3 3 6, मीन्स -127 को अगर हम लोग कन्वर्ट कर रहे हैं इन 2's कॉम्प्लीमेंट फॉर्म, तो वहाँ पे हम लोग को 6 ज़ीरो मिलेगा। ठीक है, तो चलो आगे चलते हैं। वी विल स्टार्ट विथ अवर नेक्स्ट टॉपिक, दैट इज कोड्स। सी, this table itself is very important for your objective exam point of view. You may get direct questions in ESE or in PSU exam based on this table. So if we talk about this table, then it is divided into two parts, that is codes are divided into two parts, numeric and alphanumeric. In numeric we will discuss weighted codes. Here we have already discussed and we already have a better understanding of binary codes. So we will start with the BCD codes. We will discuss 8421, 2421. This all is not part of your syllabus, that is 3321, 4221 and all this. It is not part of your syllabus. 84 -2 -1 is part of the syllabus. We will discuss it. Then we will look into non-weighted codes. Famous examples are XS3 and gray codes. Then we will look into self-complementing code, that is XS3 code. Then we will look into sequential code, that is XS3 code. Then we will look into error detecting and correcting code, that is parity and Hamming respectively. Then we will look into reflective and cyclic codes, that is gray codes. In digital electronics part, we are not going to deal with the alphanumeric codes, This I will see. I will try to cover it in computer organization, or I will take a separate class on this. Now moving forward, as we have seen in the previous table that codes can be divided into two parts, that is numeric and alphanumeric. Further, numeric codes can be divided into two parts, that is weighted and non-weighted codes. Further, weighted codes can be divided into two parts, that is binary and BCD code. And further, BCD codes can be divided into three parts, that is 8421, 2421, 84 minus 2 minus 1. And non-weighted codes can be divided into two parts, that is XS3 code and gray codes. Okay? So till now we have already covered our binary codes. Binary codes are already covered by us. So now we will cover BCD code. Further branches of BCD code we will discuss, that is along with BCD code we will also discuss 8421, 2421 and 84 minus 2 minus 1, and we will also discuss non-weighted codes, that is XS3 codes and gray code. And during this entire discussion we will also understand what is the meaning of weighted codes and non-weighted codes. So let's move forward, and we will start our first code, that is BCD code. So see, full form of BCD code is binary coded decimal. Full form of BCD code is binary coded decimal. See, what is BCD code, or what is the purpose of BCD code? See, we already know that in a decimal number system, the total symbols we have are 10. Symbols of total symbols of decimal number system are 10, and it ranges from 0 to 9. This already we know. Now see, if we want to represent each decimal number with a binary code, then that code is said to be binary coded decimal. That is, if we are representing decimal BCD. See, if we are representing decimal symbol or decimal number 0 as a binary equivalent 0000, then this representation is said to be in BCD form. Similarly, if we are representing decimal symbol or decimal number 1 as binary equivalent 0001, then this representation is said to be in BCD form. So what is the purpose of binary coded decimal or BCD code? That it helps us to convert or represent a decimal number or decimal symbol into a binary equivalent. So if we want to have so if we want to have a complete representation, so if we want to have a complete representation of all the 10 decimal number into BCD form, then we can form a table like this. Here you write decimal, here you write its BCD equivalent. So for decimal number 0, it can be represented in BCD form as 0 0 0 0. Similarly, we can represent 1 as 0 0 0 1. Similarly, 2 can be represented as 0 0 1 0. 3 can be represented as 0 0 1 1. 4 can be represented as 0 1 0 0. 5 can be represented as 0 1 0 1. 6 can be represented as 0 1 1 0. 7 can be represented as 0 1 1 1. 8 can be represented as 1 0 0 0. And 9 can be represented as 1 0 0. So see, here we have represented all the 10 decimal number or decimal symbol into its binary equivalent, or into its BCD code. Now you will get you can get one question that sir, when we are converting a decimal number into its binary, into its BCD form, then why we are using 4-bit binary representation? Then why we are using 4-bit binary representation? See, we already know that if we have n bits, then we have 2 to the power n binary representation. We have 2 to the power n binary representation. So for 4 bits, there will be 16 binary representation. Okay, I hope this is clear to you. Now see, total symbols in a decimal number system is 10. Total symbols in a decimal number system is 10. So if we want to represent our decimal number system into BCD form, then we require 4 bits, because with 4 bits we are getting 16 binary representation. Whereas if we will use 3 bits, assume you are using 3 bits to represent a decimal number system into BCD code, then with 3 bits, how many binary representation we will get? With 3 bits, we will get only 8 binary representation. We will get only 8 binary representation. And with 8 binary representation, we can only represent 8 symbols of decimal number system. But in decimal number system, we are not having 8 symbols. In fact, in decimal number system we are having 10 symbols. So to represent 10 decimal symbols or decimal number, minimum number of binary bits which we require is 4 to convert a decimal number system into its BCD equivalent. Okay, I hope this much is clear to you. Now you will get one doubt. Now you will get one more doubt. What doubt you will get? That sir, it is fine that for converting a decimal number system into its BCD equivalent, we want 4 bits, because with 4 bits there will be 16 binary representation, and with this 16 binary representation we can represent 0 to 9 decimal 0 to 9 symbols of decimal number system. Now see, out of 16 representation, here we have seen the 10 representation. Out of 16 representation, 10 representation we can see here. 10 representation we can see here. So what is happening with the remaining 6 representation? See, with 4 bit we have 2 to the power 4, that is 16 binary representation. 10 representation is in front of us. 10 binary representation is in front of us. So what is happening with the remaining 6 binary representation? Now see, what are my remaining 6 binary representation? See, what are my remaining 6 binary representation? My remaining 6 binary representation will be 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. Okay, see, these are my remaining 6 binary representation. So see, in BCD code what we get is this 10 binary representation is said to be the used states. And remaining this 6 binary representation is said to be the unused states or don't cares of BCD number system. It means finally we can write something like this. In BCD code there are 10 used states. Second point we can write, in BCD code there are 6 unused states. These 6 unused states are also known as don't cares. And what are my 6 unused states? And what are my 6 unused states? My 6 unused states are 1 0 1 0 1 0 1 1 1 1 0 0 1 1 0 1 1 1 1 0 1 1 1 1. So these are my 6 unused states or don't care conditions of BCD code. See, in objective exams, they can ask you questions related to this discussion. They can simply frame a question like which are the unused states of BCD code, and they will give you 4 options. So if you are familiar with this discussion, then you can easily solve those kind of questions, and if you are not familiar with this kind of discussion, then it will be difficult for you to solve such kind of questions. Okay, so now till now I hope this is clear to you. First, what we understood, we understood that how we can convert a decimal number into its BCD equivalent. Then we understood what are the used states of BCD code and what are the unused states of BCD code. Okay, I hope this much is clear to you. So now let's move forward. So now assume that you are given a decimal number 30. You are given a decimal number 30 and you are asked to convert it into binary equivalent. So we have already learned that how we can convert a decimal number into its binary equivalent. We have to take help of a division method. So if we will perform the division method, then finally we can say that binary equivalent of decimal number 30 is 11110. That is binary equivalent of decimal number 30 is 11110. Okay, it is fine. Now if someone asks you that if a decimal number 30 is given to you, and you have to convert it into its BCD equivalent, and now if you have to convert it into its BCD equivalent, then what will be your result? Okay, so if we want to convert our decimal number 30 into its BCD equivalent, then we will get 0011 and 0000. See, this 0011 is for decimal number 3. This 0000 is for decimal number 0. We can re-verify it from our table also. See, this was our table. For decimal number 0, its BCD equivalent was 0000. For decimal number 3, its BCD equivalent was 0011. Okay, so if you want to convert a decimal number 30 into its BCD equivalent, then you can directly write the BCD equivalent of decimal number 3 as 0011 and BCD equivalent of decimal number 0 as 0000. Okay, I hope this much is clear to you. Now similarly, if someone asks you what will be the BCD equivalent of decimal number 455, then what you will do? You will take 4 and you will convert 4 into its BCD equivalent. Similarly, you will take 5 and you will convert it into its BCD equivalent. Similarly, you will take this 5 and you will convert it into its BCD equivalent. So if we want to refer from our table, see what is the BCD equivalent of 4? It is 0100. What is BCD equivalent of 5? It is 0101. So finally, if we want to convert a decimal number 455 into its BCD equivalent, then you will get as 0100, 0101, 0101. So I hope this is clear to you. Very easy. If any decimal number is given to you and it is asked to convert that decimal number into its binary equivalent, then what you have to do? You just have to refer this table. You just have to refer this table, and for each decimal number you have to just write its BCD equivalent. You have to just write its BCD equivalent. So I hope this is clear to you. So I hope this is clear to you. So now, coming to our next discussion, now we want to understand that what are the advantages and disadvantages of BCD code with respect to binary code. So see, here if we refer our decimal number 30, if we will refer our decimal number 30, then to represent our decimal number 30 into its binary equivalent, how many bits we are requiring? See, we are requiring 1 2 3 4 5 bits. That is, if we want to convert a decimal, if we want to convert a decimal number if we want to convert a decimal number 30 into its binary equivalent, then we require 5 bits. But see, now if we want to convert a decimal number into its BCD equivalent, then see how many bits we are requiring. We are requiring 8 bits. So from here what we can conclude, that for converting a decimal number into its binary equivalent, we are requiring less number of bits as compared to its BCD equivalent. In binary equivalent, we will always require less number of bits to represent a decimal number, but in BCD equivalent, we will require more number of bits to convert a decimal number. So this is one of a disadvantage of BCD equivalent. Now coming to the advantage of BCD code. So the advantage of BCD code is that BCD code is very fast as compared to binary code. See here, while converting a decimal number into its binary equivalent, we have to take the help of the division method. That is, it is a little time consuming to convert a decimal number into its binary equivalent. But when we were converting a decimal number into its BCD equivalent, then the process was very easy and very fast. What we were doing, we were just picking one decimal number and we were just writing its BCD code. That is, we in case of 3, we directly wrote that the BCD code of decimal number 3 is 0011. Similarly, for decimal number 0, we directly wrote that the BCD equivalent of decimal number 0 is 0000. So from here we can say that BCD code is very fast as compared to the binary code. So I hope this much is clear to you. So now moving forward, so till now in the last discussion what we learned, that how we can convert a decimal number into its BCD equivalent. Similarly, now we will learn that if a BCD equivalent is given to you, then how you can convert a BCD equivalent into a decimal number. If a BCD equivalent is given to you, then how you can convert it into its decimal equivalent. So see, here we have a BCD equivalent. Here we have a BCD equivalent and we want to convert it into a decimal number. So see, what is the process, how we can do? See, for this we have to form a group of 4 bits. We have to form a group of 4 bits, and while forming the group of 4 bits, we always have to move from right to left. So if we will move from right to left forming a group of 4 bit, then our first group will be this, our second group will be this, and our third group will be this. So what we have done, we have formed a group of 4 bits while moving from right to left. Now what we have to do, we have to just convert this BCD equivalent into its decimal number. We already know that 0001 is BCD equivalent of decimal number 1. Similarly, we already know that 0100 is a BCD equivalent of decimal number 4. And similarly, 0110 is BCD equivalent of decimal number 6. So this BCD equivalent is nothing but my decimal number 641. So I hope this is very easy. Now you have learned how to convert a decimal number into BCD code, as well as how to convert a BCD equivalent into a decimal number system. So I hope this is clear to you. Now let's move forward. Now coming to our next code, that is 8421 code. So 8421 is a part of BCD code, and one very important characteristic of 8421 code is that it is a weighted code. 8421 is a weighted code. Now let's understand what is the meaning of weighted code. So we can complete this sentence as 8421 is a weighted code because each position of 8421 code has a positional value, or positional weight. 8421 is a weighted code because each position of 8421 has a positional value or positional weight to represent a decimal number, into its binary equivalent. So now let's understand what is the meaning of weighted code, what is the meaning of positional value, and how we are using 8421 to represent a decimal number into its binary equivalent. See, suppose here we will write the decimal number and here we will write its binary equivalent in 8421 form. So see, for decimal number 0, its 8421 representation will be 0000. Here we can see that positional value or positional weight of each position of 8421 code is 0. So overall we are getting a value 0, which is used to represent a decimal number 0. Similarly, for decimal number 1, its 8421 representation will be 0001. Here see, the positional value or positional weight of these three positions of 8421 is 0. Positional value is 0. Positional value is 0. But see, positional value of this is 1. Positional value of this position is 1. So when we will combine all four, then we can represent decimal number 1. Similarly, if we will move forward, then suppose if we want to represent decimal number 2 in 8421 code, then how we can represent? We will put 0 here, that is we want a positional value of this position as 0, positional value of this position as 0, we want positional value of this position as 2, so we will put 1 here, and we want positional value of this position as 0, so we will put 0 here. So decimal number 2 is represented as 0010 in 8421 form, 8421 code. Similarly for 3, decimal number 3 can be represented in 8421 code as 0011. Decimal number 4 can be represented into 8421 code as 0100. Similarly, for decimal number 5, we can represent it as 0101. For decimal number 6, we can represent it as 0110. Decimal number 7, 0111. Decimal number 8, 1000. Decimal number 9, 1001. So this is how we can represent decimal number 0 to 9 in 8421 code. And now I hope you are understanding why 8421 code is called a weighted code, because see, in 8421 code each position is having a positional value, and using that positional value we can represent any decimal number into its binary equivalent. So I hope this much is clear to you, that is what is 8421 code, why it is called a weighted code, and how we can convert a decimal number into its binary equivalent by using 8421 code. Now see again what we can see, that for representing decimal number into 8421 code we are using 4 bits. 4 bits, it means there should be 16 combination. Out of those 16 combination, see here we are having 10 combinations. Here we are having 10 combinations which are the used combination. So similarly, if we talk about the unused combination or the don't care combinations of 8421, then see what will be my unused combinations of unused combination or states or don't cares or don't care of 8421 code are 1010 1011 1100 1101 1110 and 1111. So these are my 6 unused states or don't cares of 8421 code. We can see that the unused states of 8421 code and the unused states of BCD code both are same. In BCD code also we were getting this 6 unused states, and in 8421 also we are getting this 6 unused states. In the hexadecimal form, if we want to convert, then what is 1010? It is A. 1011, it is B. 1100, it is C. 1101, it is D. 1110, it is E. 1111, it is F. So the unused states of 8421 and BCD codes are same, and it is from A to F, and it is from A to F. So I hope this is clear to you. Now see, one more observation you can see in the 8421 code. And what is that? 8421 code is also known as a sequential code. 8421 code is also known as a sequential code. What is the meaning of sequential code? Meaning of sequential code is that if we will add 1, then we will get the next state. If we are having one state and we will add 1 to that state, then we will get the next state. For example, see, if we are having state 0000, that is this is the binary equivalent of decimal number 0. Now in this state, if we will add 1, then we will get the next state, that is 0001, which is the binary equivalent of decimal number 1. Similarly, if we will add plus 1 here, then we will get the next state, that is 0010, which is the decimal equivalent, which is binary equivalent of decimal number 2, and so on. You will get the remaining result. So 8421 is a weighted code as well as 8421 is a sequential code, because if we add 1 in one of the state of 8421, then we will get the next state. So I hope this much is clear to you. So let's move forward. Now coming to our next BCD code, that is 84 minus 2 minus 1. 84 minus 2 minus 1. So our 84 minus 2 minus code minus 2 minus 1 code is also a weighted code. We can write it 84 minus 2 minus 1 code is a weighted code. So now let's see how we can represent a decimal number into 84 minus 2 minus 1 code. See, if we are having a decimal number 0, then all the positional value of 84 minus 2 minus 1 code will be 0. Similarly, for decimal number 1, what we will get? We will get as 0 1 1 1. See, for decimal number 1, why we are writing 0 1 1 1? See, the positional value of this position will be 4. Positional value of this position will be minus 2. Positional value of this position will be minus 1. So if we will add, that is, if we will add 4 minus 2 minus 1, then finally we will get 1. So this is how we can represent decimal number 1 into its 84 minus 2 minus 1 code. Now similarly, if we will move forward, then for decimal number 2, what we can write? We can write 0 here, we can write 1 here, we can write 1 here, and we can write 0 here. For decimal number 3, what we can do? we can write 0 here, 1 here, 0 here, 1 here. This will be 4, this will be -1, so finally we will get 3. Similarly, for decimal number 4, we can just write 0, 1, 0, 0. For decimal number 5, what we can write? Put 1 here, 0 here, 1 here, 1 here. See, it will become 8, it will become -2, it will become -3. If we will add all these 3, then we will get 5. For decimal number 6, what we can do? Put 1 here, 0, 1, 0. 8 minus 2, 6. For decimal number 7, 1, 0, 0, 1. For 8, 1, 0, 0, 0. For 9, 1, 1, 1, 1. See, this will give us 8, this will give us 4, means 12. This is -2, that is 10. This is -1, that is 9. So this is how we can represent our decimal number in 84 -2 -1 code. So here also we can see that these are my 10 used combinations. These are my 10 used combinations. So see, what are my used combinations? See, if we are talking about the binary equivalent, then this represents 0, this represents 7, this represents 6, this represents 5, this represents 4, this represents 11, this represents 10, this represents 9, this represents 8, this represents 15. It means if we are talking about 84 -2 -1, then what are my used states? We can write it here. Used states of 84 -2 -1. What are my used states? It is 0, 7, 6, 0, 7, 6, 5, 4, 11, 5, 4, 11. 11 is represented as B. 10, 9, 8, 15. 10 is represented as A. 9, 8, 15 is represented as F. So these are my used states. Similarly, what will be my unused state? Here we will get 6 unused states. Unused states of 84 -2 -1. What are my unused states? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. These 6 are my unused states. So if we are talking about the BCD and the 8421 code, then the unused states were A to F, A B C D E F, A B C D E F, were the unused states for BCD code and 8421 code. Now if we are talking about 84 -2 -1 code, if we are talking about 84 -2 -1 code, then the unused states are 1, 2, 3, C, D, E. So this small things you have to remember, because there are high chances or probability that such questions can be asked in your objective exam. So I hope this is clear to you. So I hope now you have learned how you can represent a decimal number into 84 -2 -1 code. Now see, one more important characteristic of 84-2-1 code is that 84-2-1 code is self-complementing code. 84-2- code is a self-complementing code. 84-2-1 code is a self-complementing code. Now let's understand what is the meaning of self-complementing code. So with respect to self-complementing code, we can write a important statement. In self-complementing code, we can get nines complement using ones complement. See, in case of self-complementing code, we write a very important statement that is, in self-complementing code we can get nines complement using ones complement. So let's understand what is self-complementing code and why we are saying that in self-complementing code we can get nines complement using ones complement. So see, we have already discussed how to find nines complement. Suppose we have to find nines complement of 7. So what we will do, we will subtract 9 from 7, we will get answer as 2. Similarly, if we want to find nines complement of 77, then what we have to do, we have to subtract 99 from 77, we will get result as 22. But see, one issue with our machines is that there is no provision of subtraction in machine. We have already discussed this earlier also, that in case of machine there is no provision of subtraction. So we have to use complement method to perform subtraction in machines. If you want to perform subtraction, then you always have to use the complement method. Okay, I hope this is clear to you. Now let us see why 8421 code is said to be a self-complementing code and why we wrote that in self-complementing code we can get nines complement by using ones complement. See, what will be nines complement of 0? So you will say nines complement of 0 will be 9. Nines complement of 0 will be 9. What will be nines complement of 1? So you will say nines complement of 1 we will get 8. Similarly, nines complement of 2 will be 7, nines complement of 3 will be 6, nines complement of 4 will be 5. Okay, I hope this one is clear to you. So now see, nines complement of 0 is 9. Nines complement of 0 is 9. And how 9 is represented in 84-2-1 code? 9 is represented as 1111. Now see how 0 is represented in 84-2-1. 0 is represented as 0000. Okay. Now see, if we will take ones complement of 0 0 0 0, what we will get? If we will take ones complement of 0 0 0 0, then we will get 1 1 1 1. And what is this 1 1 1 1? 1 1 1 1 is nothing but my 9. And what is 9? 9 is my 9's complement of 0. If you are not getting it, take one more example. See, what is 9's complement of 1? See, 9's complement of 1 is 8. How 8 is represented in 8 4 minus 2 minus 1 code? 8 is represented as 1 triple 0. Now see how 1 is represented as in 8 4 minus 2 minus 1. 1 is represented as 0 triple 1. Now see, if we will take 1's complement of 0 triple 1, what we will get? We will get 1 triple 0. And what is this 1 triple 0? It is nothing but 8. It is nothing but 8 in 8 4 minus 2 minus 1. So here we can see why 8 4 minus 2 minus 1 is known as self-complementing code, because self-complementing code means we can find 9's complement using 1's complement. So here we can see that if we want to find 9's complement of any decimal number, then what we have to do? We have to just take the 1's complement of that representation. That is, for example, if we want to take 9's complement of 3, then what we have to do? See, 3 is represented as 0 1 0 1. 3 is represented as 0 1 0 1. So if we want to take 9's complement of 3, then we have to just take 1 complement of 0 1 0 1. That is, it will get 1 0 1 0. And this 1 0 1 0 is nothing but my 9's complement of 3, which is nothing but 6. Which is nothing but 6. So I hope this is clear to you. That why 8 4 minus 2 minus 1 code is known as the self-complementing code. 8 4 minus 2 minus 1 code is known as self-complementing code because we can get 9's complement by using 1's complement. It means if we will take 1 complement of 0 0 0 0, then we will get 1 1 1 1. That is, if we will take 1's complement of 0 0 0 0, then we will get 9 complement of 0. Similarly, if we will get 1 complement of 0 triple 1, then we will get 9's complement of 1. Similarly, if we will take 1 complement of 0 1 1 0, then we will get 9's complement of 2. Similarly, if we will take 1's complement of 0 1 0 1, then we will get 9's complement of 3. Similarly, if we will take 1 complement of 0 1 0 1, then we will get 9's complement of 4. Then we will get 9's complement of 4. So I hope this is clear to you that why 8 4 minus 2 minus 1 code is known as the self-complementing code, because in 8 4 minus 2 minus 1 code we can get 9's complement by using 1's complement method. So see what you can do. If you are asked to write decimal equivalent, decimal number, if you are asked to write the decimal number in 8 4 minus 2 minus 1 code, if you are asked to write the decimal number in 8 4 minus 2 minus 1 code, then what you can do? See, you have to just write the representation from 0 to 4. You just write the representation from 0 to 4, and after that what you have to do, you just take the ones complement of this, you will get the remaining representation. That is, for example, see, if you are asked to write the 8 4 minus 2 minus 1 representation of decimal number 0 to 9, then what you have to do, you just write 8 4 minus 2 minus 1 representation of decimal number from 0 to 4, and the rest, and for the rest representation you have to just take its ones complement. Like see, if you will take ones complement of 0 1 0 0, what you will get? You will get 1 0 1 1. It is nothing but my 8 4 minus 2 minus 1 representation of decimal number 5. Similarly, if you will take ones complement of 0 1 0 1, what you will get? You will get 1 0 1 0. It is nothing but my 8 4 minus 2 minus 1 representation of decimal number 6. Similarly, if you will take ones complement of this, what you will get? You will get 1 0 0 1. This is nothing but my 8 4 minus 2 minus 1 representation of decimal number 7. Similarly, if you will take ones complement of this, what you will get? You will get 1 0 0. 1 0 0 is nothing but my 8 4 minus 2 minus 1 representation of decimal number 9. In the same way, if you will take ones complement of 0 0 0 0, you will get 1 1 1 1. 1 1 1 1 is nothing but my 8 4 minus 2 minus 1 representation of decimal number 9. So what we have done is that, as we know that my 8 4 minus 2 minus 1 code is a self-complementing code, so if we want to represent decimal number into 8 4 minus 2 minus 1, then we can write the representation only from 0 to 4, and for rest representation you can take ones complement of above form, you will get the below forms. So I hope this is clear to you. So let's move forward. Now coming to our next code, that is 2421 code. It is also a part of BCD code. Now see, 2421 code is also a weighted code. 2421 code is a weighted code. Second, 2421 code is also a self-complementing code. Self-complementing code. Okay. Now see, in 2421 code, there will be a very interesting discussion. Sometimes students commit a mistake in 2421 code, and so we will see that what care you have to take whenever you are converting a decimal number into 2421 code. Okay. So in case of 2421 code, we will see three representation. Of converting a decimal number into 2421 code, and then we will see which representation is true. Then we will see which representation is true, which representation is not true, and what precautions we have to take while dealing with the 2421 code. So see, here we have our first representation for decimal number. We have represented in 2421 code as 0000. For decimal number 1 we have used 0001. For decimal number 2 we have used 0010. For decimal number 3 we have used 0011. For 4 0100. For 5 0101. For 6 0110. For 7 0111. For 8 1110. For 9 1111. So at first look this representation seems to be okay, because if we will look at the positional values, then we can see that using the positional values we are getting its decimal equivalent. But I will say that this representation is a wrong representation of decimal number into 2421 code. Now let's understand that why it is not a correct representation in 2421 code. See what we discussed, that 2421 code is a self-complementing code. It means if 2421 code is a self-complementing code, then if we will take one's complement of this, then we should get 9. So see, if we are taking one's complement of this, we are getting 9. Okay, no problem. Now see, if we will take one's complement of 1, then we should get 8. Then we should get 8. See, if we will take one's complement of 0001, then we will get 1110. So this one is also okay. This one is okay. This one is okay. Now coming to this one, that is, if we will take one's complement of 0010, then our expectation is that we should get 7. So what will be one's complement of 0010? It will be 1101. But see, here we are not getting 1101, here we are getting 0111. Our expectation was that if we will take one's complement of 0010, then we will get 1101, but here we are getting 0111. So as we said that 2421 code is a self-complementing code. So now you say, is the fundamentals of self-complementing code is getting satisfied in this representation? Then you will say no, because in self-complementing code we know that we can take 9's complement by using 1's complement. But here when we try to find 1's complement of 0010, then we were not getting its 9's complement. It means this representation is not a correct representation of 2421 code. Now let's see what will be my correct representation. So now let's see what will be my correct representation. Now we will try to fill this one and we will try to fill this one. So see, if we will try to fill this one 2421, see, this is same. We are writing up to 4. See, all zeros, 0001, 0001, 0010, 0010, 0011, 0100, so up to, so this column and this column is same up to this one. Now let's use this one. See, if we want to represent 0, we can write it as 0, 0, 0, 0. If we want to represent 1, then we will write 0, 0, 0, 1. If we want to represent 2, see here we represented 2 as 0, 0, 1, 0. But we have one more option to represent 2. How? What is that option? We can represent 2 as 1, 0, 0, 0. See, here also, see, the positional value of this position will be 2, rest is 0, means we will get 2. So we can see that 2 can be represented in two ways. 2 can be represented as 0010 as well as 1000. Okay, fine. Similarly, if we want to represent 3, then we can represent it as 0011. We can represent it as 0011. Okay. Or we can represent 3 as 1001. See, we can represent 3 as 0011, as well as we can represent 3 as 1001. Positional value of this position is 2, this position is 1. Combining both, we will get 3. Similarly, 4 is represented as 0100 here. Similarly, 4 can be represented as 1010. So for 4 also there is 2 representation. So from here what we can conclude? From here we can conclude that if we are converting a decimal number in 2421 representation, then there can be more than one representation. It means we can say that if we are converting a decimal number into 2421 representation, then we will not get a unique representation as we got in 8421 and 84 minus 2 minus 1. In 8421 and 84 minus 2 minus 1 code, we were getting unique representation of decimal number. But in 2421 we are not getting unique representation of decimal number, because here we are getting more than one representation of decimal number. So I hope this is clear to you. So whenever you are writing 2421, whenever you are writing decimal number in 2421 code, what you have to do, that you always write the representation only up to 0 to 4. You write only up to 0 to 4. Now you will say that, sir, how we have to write the remaining combinations? How we can write the remaining combination? So for writing the remaining combination, what we will do, we will use the self-complementing feature of 2421. We will use self-complementing feature of 2421. We know that 2421 is a self-complementing code. It means if we want to write the 2421 representation of decimal number 5, then we will take 1's complement of decimal number 4. That is, we will get 1011. Here what we will get? Here we will get 0101. Now if we want to write 2421 of 2421 representation of decimal number 6, then we have to take 1's complement of 2421 representation of decimal number 3. So here we will get 1100. Here what you will get? Here you will get 0110. Similarly, you can fill remaining also. Here you will get 1101. Here you will get 0111. Then here you will get 1110. Here you will get 1110, and at last you will get 1111. At last you will get 1111. So now if we talk about this two representation, then these two representation are the correct representation of decimal number in 2421 form, and this representation is not the correct representation of decimal number in 2421 form, because in this representation self-complementing property of 2421 is not getting satisfied, but in this two representation the self-complementing property of 2421 code is getting satisfied. So whenever you are dealing with 2421 code, you have to take the precaution. Suppose this question is asked in the conventional exam, then you always have to take the precaution that whenever you are converting a decimal number into 2421 code, always write the representation from 0 to 4, and then by using the self-complementing property of 2421 code, you can write the remaining combinations. So I hope this is clear to you. This was very important discussion related to 2421 code. So now let's move forward. We have two different ways because we can have two different ways of representing decimal symbols. Now coming to next code, that is XS3 code. XS3 code. Now see, as the name suggests, we can easily figure it out that XS3 means we have to add 3 in each decimal number for its representation. That is, if we want to represent 3, if we want to represent if we want to represent decimal number 0 in XS3, then we have to add 3 to it. That is, it will be represented as 3. Now similarly, if we want to represent a decimal number 1 into XS3, then we have to add 3 to it. That is, it will be represented as 4. Similarly, if we want to represent a decimal number 5 into XS3, then we will have to add 3 to it. That is, it will be represented as 8 in XS3. So following this rule, we can fill it up. So decimal number 0 will be represented as 3. That is, it will be 0, 0, 1, 1. Now 1 will be represented as 4. So 0, 1, 0, 0. Now 2 will be represented as 5. So 0, 1, 0, 1. Now 3 will be represented as 6. So 0, 1, 1, 0. 4 will be represented as 7. So 0, 1, 1, 1. 5 will be represented as 8. So 1, 0, 0, 0. 6 will be represented as 9. So 1, 0, 0, 1. 7 will be represented as 10. So 1, 0, 1, 1. 8 will be represented as 11. So 1, 1, 0, 1, 0 it will come. 8 will be represented as 11. 9 will be represented as 12. That is 1, 1, 0, 0. So this will be the representation of decimal number into XS3. Now see, coming to the properties of XS3. See, is XS3 a weighted code? Is XS3 a weighted code? No. XS3 is non-weighted code. XS3 is non-weighted code. Because here each position, because here there is nothing that each position is signifying any positional value or any positional weight. So XS3 is non-weighted code. Now coming to the second property, XS3 is sequential code. XS3 is sequential code. What is the meaning of sequential code? Sequential code means that if we will add one, if we will add one in this, then we will get the second representation. If we will add one in it, then we will get the third representation. If we will add one in this, then we will get the next representation. That is, if we will keep on adding one at each representation, then we will get the second representation. See, if we will add 0, 0, 1, 1 with 1, what we will get? We will get this 0, 1, 0, 0, 0, 1, 0, 0. Now if we will add 1 in this, what we will get? 0, 1, 0, 1, 0, 1, 0, 1. So this is the meaning of sequential code. Now coming to the third important property, that is XS3 code is self-complementing code. XS3 code is self-complementing code. That is, in this code also we can find 9's complement from 1's complement. That is, in this code also we can easily find a 9's complement from 1's complement. See how? See, what is 9's complement of 0? 9's complement of 0 is 9. 9's complement of 0 is 9. In XS3 code, how 9 is represented? How 9 is represented? It is represented as 1101. Now see, if we will take its 1 complement, if we will take its 1's complement, we will get 9. Similarly, same will be the pattern for this. 1's complement of 1 is 8. So if we will take 1's complement, we will get 8. Similarly, it will follow for the last remaining representations also. So it is a self-complementing code. I hope this is clear. Now see, if we want to form a table, regarding the codes which we have learned till now, see, 8421 is a weighted code or not? Yes. 84 minus 2 minus 1 is weighted code or not? Yes. 2421 is a weighted code or not? Yes. XS3 is a weighted code or not? No. Coming to self-complementing. 8421 is self-complementing? No. 84 minus 2 minus 1 is self-complementing? Yes. 2421 is self-complementing? Yes. XS3 is self-complementing? Yes. 8421 is sequential? Yes. I forgot to tell you this. When I was teaching 8421 is also a sequential code. Because if we will keep adding 1, we will get the next representation. 84 minus 2 minus 1 is sequential? No. 2421 is sequential? No. XS3 is sequential? Yes. So this was some important properties of this for code, which is very important for your objective point of view. Now, coming to next code, that is gray code. There are very small important properties related to gray codes. We will look into each properties in details. First, we will discuss binary to gray conversion. First, we will discuss binary to gray conversion. See, if we are given a binary code 1011, we want to find its gray code. So how we can find it? Suppose this is binary. Suppose this is binary. We want to find its gray conversion. So its method is copy this one as it is. Copy this one as it is. Then we will take XOR of this two. Then we will take XOR of this two. You all must be knowing about XOR. We will discuss XOR in details in coming session. But here, just see what is the meaning of XOR. A XOR B. 0 0 0 1 1 0 1 1. For 0 0 we will get 0. For 0 1 we will get 1. For 1 0 we will get 1. For 1 1 we will get 0. That is, if A and B are same, we will get 0. If A and B are different, we will get 1. We will discuss it in a later part. But here you must be knowing about its basic information. So 1 XOR 0, what we will get? We will get 1. Now we will take XOR of this 2. Now we will take XOR of this 2. So what will be XOR of 0 and 1? It will be 1. Now we will take XOR of this 2. Now we will take XOR of this 2. What will be its XOR? 1 XOR 1, it will be 0. See, very easy. Very easy. Suppose take us one another example, that is 0 1 0 1. This is binary. This is binary. We have to convert it into gray. We have to convert it into gray. So the first bit we will write it as it is. Then we will take XOR of 0 and 1. XOR of 0 and 1 is 1. Then we will take XOR of 1 and 0. XOR of 1 and 0 is 1. Then we will take XOR of 0 and 1. XOR of 0 and 1 is 1. Fine. Now, coming to second part, that is gray to binary. Coming to second part, that is gray to binary. Suppose we are given a gray code 0 1 1 0. We have to convert it into binary. We have to convert it into binary. See, here also copy the first bit as it is. Copy the first bit as it is. Now see, now we will take XOR of this. Now we will take XOR of this. Now we will take XOR of this. So what will be XOR of this? 0 and 1. It will be 1. Now we will take XOR of this. Now we will take XOR of this. What will be XOR of this? It will be 0. Now we will take XOR of this. Now we will take XOR of this. What will be XOR of this? It will be 0. Earlier we were taking XOR of this. Now we are taking XOR of this. Very easy. Let us take another example, that is 1010. It is in gray. It is in gray. We have to convert it into binary. We have to convert it into binary. So we will write 1 as it is. Now 1 XOR of 1 and 0. XOR of 1 and 0. We will get 1. XOR of 1 and 1. We will get 0. XOR of 0 and 0. We will get 0. Very easy. Now see how we can represent decimal number into gray code. How we can represent decimal number in gray code. So 0, 1, 2, 3, 4, 5, 6, 7. I am taking up to 7. That is 3 bits will be required. 3 bits will be 3 bits will be required. 3 bits will be required. First I will write this binary, then gray code. So we will get 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Now how we can get the gray code? The same process which we discussed earlier. 0 will be as it is. Then take XOR of this. It will be 0. Take XOR of this. It will be 0. Now this, write 0 as it is. Take XOR of this, 0. Take XOR of this, 1. Now here again, first write 0. Take XOR of this. Then take XOR of this. Now here again, write 0. Take XOR of this. Then take XOR of this. Write 1 here. Then take XOR of this. Then take XOR of this. Now again, write 1 here. Take XOR of this. Take XOR of this. Now write 1 here. Take XOR of this. Take XOR of this. Now again, 1 here. Take XOR of this. Take XOR of this. Easy, easy. This is the way by which you can find a binary to gray code. See, there's a shortcut also. See, there's a shortcut also. See, there's a shortcut also. See the shortcut. See the shortcut. Then it will be up to you that whether you will go for shortcut or you will go for the normal technique. See how, if we talk about the shortcut is like this. For n bit, n is equal to 3. For n bit, n is equal to 3. See, first I will write 0 and 1. 0 and 1. Okay. Now I will take mirror image of this. Now I will take mirror image of this. That is what we will get. We will get 1 and 0. Fine. Now I will write 0 here, 0 here, 1 here, 1 here. Fine. Now I will take mirror image of this. Now I will take mirror image of this. That is 1 0, 1 1, 0 1, 0 0. Fine. Now I will put 0 here, 0 here, 0 here, 0 here, 1 here, 1 here, 1 here, 1 here. Now see, are we getting the same result? See, are we getting the same result? So this is the shortcut. What I told you, first I will write what I told you. First I will write what I told you. First I will write 0 1. Fine. Then I will take its mirror image. Then I will take its mirror image 1 0. Then I will put 0 here, 0 here, 1 here, 1 here. Then I will again take its mirror image. Then I will again take its mirror image 1 0, 1 1, 0 1, 0 0. Now I will put 0 here, 0 here, 0 here, 0 here, 1 here, 1 here, 1 here, 1 here. This was for n is equal to 3. This was for n is equal to 3. Similarly, you can find for n is equal to 4 also. Similarly, you can find for n is equal to 4 also. You can take mirror image of this. You can take mirror image of this downwards. Then you can put 0 0 0 0 here up to here and 1 1 1 downside. So you will get the gray code conversion for n is equal to 4 also. So this was the shortcut. Now it's up to you whether you will go for shortcut or you will go for a normal technique when we will discuss the code converters. Now see, as we are taking the mirror image, that's why reflective, if we talk about the properties, if we talk about the properties of gray code, if we will talk about the properties of gray code, if we will talk about the properties of gray code, then it is also known as reflective code. It is also known as reflective code. It is also known as reflective code. Now see, I can delete this shortcut. I will delete this shortcut because I hope that now you have now you know that how we can use shortcut technique for finding the gray code. You can write it in your notebook. Now see, if we will take this two, if we will take this two combination, see how many bit changes are there. 1 is getting changed to 0. 1 is getting changed to 0. 0 is getting changed to 1. That is, there is 3-bit change. That is, there is 3-bit change. Now, if we talk about the gray code, see, only 1-bit change between these two. Here, only 1-bit change. Here we are getting 1-bit change. If we compare this two, if we will compare this to only 1-bit change. If we will compare this to only 1-bit change. If we will compare this to only 1-bit change. If we will compare this to only 1-bit change. If we will compare this to only 1-bit change. That is, in gray code we are getting only 1-bit change between successive representation. We are getting only 1-bit change between successive representation. So gray code is also known as cyclic unit distance code. So it is known as cyclic unit distance code. So it is also known as cyclic unit distance code. See, is it weighted code? No. It is not weighted code. It is not weighted code. It is self. Is it a self-complementing code? It is not self-complementing code. These are some important properties which will be very important for your objective exam, which will be very important, for your objective exam. Now coming to the uses of some codes which we have discussed. Now coming to uses of codes which we have discussed till now. First, if we will talk about the BCD codes, then first we discussed 8421. So 8421 is used for addition. Now if we will then we discussed 84 minus 2 minus 1, and then we discussed 2421. Both these codes are used for subtraction. Then we discussed XS3 code. It is also used for subtraction. Why? Because all these three codes are self-complementing code. Now then we discussed gray codes. Gray codes. Gray codes has gray code is not used for used for arithmetic operation. Not used for arithmetic operation. Very important points I am writing here. That's very important for your objective point of view. Not used for arithmetic operations. So where it is used? Gray codes are used in instrumentation, and data acquisition. Instrumentation and data acquisition where linear, angular displacement is measured. See, there is a link between measurement also. We can get assertion and reasoning question in ESE exam based on this statement, or we can also get MCQ type questions based on this statement. So it is used in instrumentation and data acquisition where linear angular displacement is measured, and it is used in shaft, used in shaft encoders, input output devices, analog and digital converters. Important points here I am writing. It is used in shaft encoders, input output devices, and analog to digital converters. See, I am not going in details. I am not going to brief you that how we are using it in shaft encoders, input output devices, and ADC converters, because it is not relevant for your exam point of view. In exam, you will generally get objective type questions in which the statement will be given. You just have to find out the right and the wrong one. I will see if I will get some time in measurement subject, then I will discuss little bit there. But I am not guaranteeing you because this much only is enough for your exam point of view. अब चलो कुछ क्वेश्चन देखते हैं रिलेटेड टू कोड्स। तो यहाँ पे देखो क्या कह रहा है, ऐड 8 and 9 इन BCD कोड। बेसिकली आपको क्या कह रहा है, आपको डेसिमल नंबर 8 दिया है, आपको डेसिमल नंबर 9 दिया है, इसको आप ऐड करो और रिज़ल्ट बताओ, और आप रिज़ल्ट बताओ इन BCD कोड। ठीक है, तो देखो 8 and 9 को ऐड किए तो हम लोग को रिज़ल्ट मिल जाएगा 17 इन डेसिमल। अब 17 को हम लोग BCD में कैसे लिखते हैं, तो क्या करना है, 1 को कैसे लिखेंगे 00001, 7 को कैसे करेंगे 0111, 012 4 6, बस ये आ गया आपका BCD में। ठीक है, आई होप दिस इज़ क्लियर टू यू। तो चलो आगे चलते हैं। अब देखो इस क्वेश्चन को देखते हैं। द नंबर ऑफ बाइट्स रिक्वायर्ड टू रिप्रेजेंट द डेसिमल नंबर 1856357 इन पैक्ड BCD फॉर्म। देखो आपको एक डेसिमल नंबर दिया है 1856357, ये आपको एक डेसिमल नंबर दिया है, कह रहा है कि इसको आप BCD में कन्वर्ट करो और फिर बताओ कि आपको कितने नंबर ऑफ बाइट्स का रिक्वायरमेंट है इसको रिप्रेजेंट करने में। ठीक है, तो देखो इसको हम लोग डेसिमल से BCD कन्वर्ट करेंगे ही नहीं। हम लोग को देखो पता है कि डेसिमल से BCD कन्वर्ट करने में क्या है, जितने भी आपको यहाँ पे डिजिट्स मिल रहे हैं उसको आप 4 बिट्स से रिप्लेस कर दो। मीन्स देखो बेसिकली अगर हम लोग इसको BCD में करने जाएं तो देखो ये जो मेरा 1 है ये हम लोगों को 4 बिट देगा, ये 8 है ये हम लोग को 4 बिट देगा, ये 5 है ये 4 बिट दिया, 6 4 बिट दिया, 3 4 बिट दिया, 5 4 बिट दिया, 7 4 बिट दिया। ये आ गया मेरा BCD। अब हम लोग को पता है 8 बिट्स इज इक्वल टू 1 बाइट। ये हम लोग को पता है 8 बिट इज इक्वल टू 1 बाइट। तो देखो यहाँ पे 8 बिट है, ये मेरा 1 बाइट आया, यहाँ पे 8 बिट है, ये मेरा 1 बाइट आया, यहाँ पे आया मेरा 1 बाइट। इस 4 बिट को भी अब करने के लिए 1 बाइट चाहिए ही चाहिए। तो मेरा टोटल नंबर ऑफ बाइट्स कितना आ गया, 4 बाइट्स का रिक्वायरमेंट। ठीक है, आई होप दिस इज़ क्लियर टू यू। तो चलो आगे चलते हैं।